Check. One, two, one, two, one, two. आ रहा है क्या कुछ? Check. One, two. Check. One, two, 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 one, two, three. Check. Check. One, two. Check. One, two. Check. One, two. Hello. Abbas. Abbas. Hello. Check. One, two. Check. One, two. Ready. One, two, three. Check. Ready. One, two, three. Check. One, two. Check, check. One, two. hello, hello, check, hello, check, hello, 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 check, hello,
morning, everyone. Very warm welcome to all of you who have joined us for this edition of ISM, Indian Instincts Meeting 2025. And firstly, okay, we apologize for a little bit delay, but hopefully first day jitters will go away and we'll be back on schedule from tomorrow onwards. And ISM is a conference with a lot of legacy because almost all of my academic life at least, okay, I have remembered, okay, participating in various ISMs, okay. And a lot of people have made it possible for this continuous chain of conferences to happen. I think it started with the Puri conferences in 90s, okay. My seniors, like Professor Maharana and Ashok and all these people must be remembering them quite well. And we have been handed down this distinguished conference, and hopefully it will have a bright future also. So let me just not take too much time. Okay, let me invite our director, Professor H.N. Ghosh, and our chairperson, Karthik Senabati, okay, to come to the stage.
I need to speak something here.
No, please.
Good morning, everybody. Welcome to NISER. I have to tell something of the meeting, which actually far away the kind of research I do. I am a spectroscopist, ultra-fast. But what I understand, the string theory is which can answer everything. Theory of relativity of Einstein and quantum mechanics. They are trying to solve many problems in the physics, and eventually people found that it's not everything. There are many more new physics are coming, doing a lot of experiments. So eventually, if you want to solve something, you have to take the help of string theory. So it's a, although it started by maybe late 60s or late 70s, I don't know exact time, but this physics, eventually people are expecting to solve all kind of fundamental physics in the universe, not only on the, in the globe or whatever it is the universe. So particularly I must tell that the last director of this institute was also from string theory. I can see him. And the number of faculty in our institute is string theory, I think one of the maximum number. And what it suggests that NISER actually supports this string theory work. So, to show the solidarity, I am just waiting because I cancel all other meetings. I came here to show the solidarity of this field of physics. We are here and we have a lot of faculty. We expect, end of the day, we expect our faculty will contribute such a way. We have some very good faculty, and I expect their work should be, accepted by the world top leader of the world science. And thank you very much. I'm sure there are, what I came to know that all the speakers are here, so that's a very good thing, and eventually all the other members will be coming. There is a total mess in the Indian sky, so I hope you are going to have a good time. This time of, in Bhubaneswar or NISER, it's a very good time. The foreign faculty who has come, I'm sure you will enjoy the temperature what you have. And eventually, after the meeting, I request all of you to visit the state of Odisha. It's such a beautiful place. Thank you very much.
So actually, so as a token, as a small token, Karthik, yeah, I mean, he has supported all of us to this. It's a whole departmental effort. Yeah.
So I request Kaushik, who is the session chair, to take over now.
Okay, so yeah, so the first talk is by Professor Ashok Seth, and he'll tell about scattering of D0 branes in string field theory.
Not sure if this is working. I think this slide changes and let's see. Okay. Right.
Yeah, I am also sure. So correct है नहीं, so correct है नहीं कर रहा.
I can use
Pointer is not working.
should I use this? I can use this other guy. It works. Okay, thank you. Okay, so I'll first of all thank the organizers for inviting me to speak here and to this conference. So the title of the talk is Scattering of D0 branes and strings, and I'll begin by explaining the problem. Something is it possible to put that off, or it's gone off? Okay, so let me explain what the problem is of scattering of D0 branes and strings. Okay, so I'll start with VP branes. They are p-dimensional extended objects in string theory with open strings as excitations on the word volume. Now, when we have such a DP brane present as a background, we can calculate scattering amplitudes in terms of correlation functions on Riemann surfaces with boundaries. Okay. The boundary condition on these boundaries is determined by the particular DP brane that you are considering. Okay. In particular, you have Neumann boundary condition along the tangent directions and Dirichlet boundary condition along the transverse directions. And the external states in this problem can be either closed or open strings, which are represented by appropriate vertex operators on the worksheet. Something is wrong with, I can see it here but not there. Should I, yeah, meaning, oh, the screen is, I see, it's, oh, I see, oh, you can see it, right? Yeah. Oh. No, otherwise I can go off the full screen mode and this is okay? So now it's okay. I think this is correct, right? So I'll use the up and down arrow. I think this will probably not work. Oh, this is working. Okay. Okay. So the point is that the D0 branes, the reason that D0 branes are special is because they are particle-like objects, and they cannot be regarded as a fixed background. Instead, what you should do is to regard the D0 branes as possible asymptotic states in a scattering amplitude. Okay. And so then the question is, how do we compute a scattering amplitude that involve external D0 branes and strings. Okay. The main issue that we face in this approach is that the conventional worldsheet approach does not allow us to change the momentum that the D0 brane carries. Okay. And in particular, the boundary condition presupposes a fixed trajectory of the D0 brane, okay, and we take that usually to be a static D0 brane, or you can have D0 brane moving at a certain constant speed, but it's fixed once and for all when you do the computation. Okay. So we'll illustrate this problem using the example of a 3-point amplitude, okay, with incoming particles as D0 brane and closed string tachyon, and outgoing particle as a D0 brane. Now the reason that I have chosen the closed string tachyon as the incoming particle is because it's the simplest possible calculation that one can imagine. But we could replace the bosonic string theory by superstring theory and the tachyon by, say, incoming graviton or some other particle. Okay. But the basic principle will remain the same. So here is a picture. Okay, we are interested in considering a scattering amplitude where a D0 brane and a closed string comes in, okay, which I have taken to be the tachyonic state and goes into a final state D0 brane. So leading contribution to an amplitude of this kind comes from what is called the disk 1-point function. Okay. And if we take external tachyon of momentum k, then the amplitude is given by an expression of this form. Okay, this is just a result of a calculation of 1-point amplitude on the disk. Here GS is the string coupling and M is the D0 brane mass, which is again of order 1 over GS, but I have written it separately. Okay. And the thing to note here is, first of all, that there is no delta function that conserves the spatial momentum, because space transition symmetry is broken by the D0 brane boundary condition. You put reduced boundary condition on all the spatial directions, and so space transition symmetry is broken and there is no momentum conservation involving the spatial momentum. The second point to note is that in this there is an energy conserving delta function because the time transition symmetry is not broken, but D0 brane energy does not enter the energy conserving delta function. It only conserves the external tachyon energy. Now this problem becomes much more severe at the next order. So next order will be an annulus amplitude, again with D0 brane boundary condition on both boundaries. So annulus has 2 boundaries. You can think of it also as a cylinder with 2 boundaries. Okay. The external tachyon is a vortex of particle inserted in the cylinder, and then the 2 boundaries where you have D0 brane boundary condition. Okay. This calculation can be done using worldsheet theory, and again we get an expression of this kind. Okay, there is the energy conserving delta function again, and now we have an integral over 2 variables t and x with an integrand which I have written as f of x and t. Okay. And here I have given the explicit expression of f. Okay, this you get by some explicit calculation on the of annulus amplitude. Okay. So GS is the string coupling, eta prime c will appear again and again. It's just a constant 1 over 2 pi. Okay, just a shorthand notation for writing this. Okay. Eta is a Dedekind eta function. Okay, and theta 1 is the odd Jacobi theta function. So these are well known functions. Okay. And once you have these functions, you can substitute here and carry out this integral. Okay. The problem is that this integral is actually infinite. 1 by 4, okay, this is just a way the x variable is defined. Right? So this is integrating from the boundary to the center of the cylinder, because there is a reflection symmetry x to minus 1 over x. Right? So this starts from x from 0 to half, but because of the reflection symmetry, we can make it from 0 to 1/4. It's just a way of choose. I have not told you what x variable is, right? But this is the way it comes. You just think of this as a cylinder with, and you are integrating along the length of the cylinder. Okay, so let's examine this for fixed x and large t. Okay, the behavior of this function f, and that is easily done because the asymptotic values of these functions are well known. And once you do that, you find that the f of x and t has an expansion of this form. Okay, so the leading term in the expansion is t to the minus half times e to the 2 pi t, and then there are the order 1 terms in in the expansion for large T. Okay. And if you substitute it here, you will see that the result is divergent because you have to integrate T from 0 to infinity, and clearly this is divergent. Okay. And even the second one is divergent because you get dt over T to the half. Now, we will discuss this in more detail later, okay, but let me just point out at this stage that the leading divergence as T goes to infinity and as x goes to 0, it has also a divergence from the x equal to 0 end. Okay. These turn out to be due to open string tachyon on the D0 plane, okay, and these will be absent in superstring theory, and as we will see, they can be managed using bosonic string field theory. Okay. But the most dangerous terms, right, which are present also in superstring theory, are the subleading terms for large T. So if you go to the subleading order, okay, this is the term that you get, okay, and we have a divergent integral of the form integral dt T to the minus half, okay, and this diverges from the T equal to infinity end. Okay. This divergence again we will see that can be traced to massless open string modes that propagate in the loop, and they will be present even in superstring theory, right. So these are the divergences you have to try to understand how to manage. Now, we will see that this divergence is infrared divergence. Okay, I have already told you here that it is because of the massless open string modes. Okay. And as always, the infrared divergences signals that we have not chosen the external states correctly. Okay. And in this case, it is clear what the error is. Right? The error stems from the fact that we have treated the external D0 plane as a fixed object with fixed boundary condition which do not move. So this problem has been known for about 30 years. This is known as the D0 plane recoil problem, okay, first introduced by these authors, okay, and then there have been many papers on this, okay, trying to look at it from various angles. Okay. But the question that we will be interested in is how do we resolve this and get an unambiguous finite answer, right? It's not enough to show that argue that the answer divergences will cancel and the answer will be finite, but we want an answer that is unambiguous. Okay, it should in string theory everything should be unambiguously calculable, and hence we should also get an unambiguous result. Okay. And we will see that this problem can be solved using string field theory, and just let me at this stage just give the result, the form that we get. Okay, we have to do some numerical calculation to get the result, and this is the result that we have. It has a full momentum energy momentum conserving delta function. This is the leading term, and this is what we get after some numerical integration in the subleading order. Okay, we will see how this comes. No, they are not the same order in G string because M is 1 over G string. Yeah, so this M is missing from here. So this is the disk and this is annulus. Okay, after you pass it through string field theory. Okay, so let me now describe the physical origin of the problem and how we resolve it. Okay. And so for this we will take a toy model. Okay, but don't ignore the toy model because this will become the real model. Okay, eventually. Okay. So a toy model that you want to consider is a problem where a non-relativistic particle of some mass m, which we will eventually identify as a D0 plane, interacts with a scalar field sigma of mass say small m, okay, which will be the closed string state or closed string tachyon, and we will take these to happen in d+1 space-time dimensions. And we will denote by chi of t the position of the non-relativistic particle, the D0 plane, at time t. And here I have written down an action, okay, a possible action for this. Okay. So the first line is just the kinetic term for the field sigma, okay, which I have taken to be a scalar field. Okay. This part is just the kinetic term for the D0 plane, for the particle, right? The half mx dot square, right? This is what we learn in classical mechanics. And then this is the interaction term, right? And this is the important point because this tells us how this field sigma interacts with the degree of freedom of the particle. Okay. And the main thing to notice is that the argument, x argument of sigma, right, which was here, is replaced by the particle position. which basically says that the interaction between the external field and the particle is through the value of sigma at the position of the particle. Okay? That's this. This f of the grad is just some polynomial in the derivatives. Okay? And what we mean by this symbol is that you first take sigma tx, apply all these derivatives. Right? This could be just 1 plus grad square plus grad to the 4 and so on. You apply all that, okay? And then eventually evaluate this at x equal to chi, okay, the position of the d0 brane. And this action has transition symmetry, okay, but it's in a spontaneously broken form. Okay. So the space transition symmetry here takes a form where you shift x by a constant a, but at the same time you shift chi by the negative of that constant. Right? And this is a reflection of the fact that the symmetry as written here is actually a spontaneously broken symmetry, because one of the variables gets shifted under this symmetry. Yeah, these are the collective coordinate formulation for any particle, exactly. Okay, so first we will try to compute the one-point function of chi using Feynman diagrams, right? And because that will illustrate where the problem is in the worksheet approach. Okay. So if you want to use Feynman diagrams, you just expand the action in powers of chi, okay, which means basically that here we expand this in powers of chi, Taylor series expansion. So this part remains exactly the same, and in the second line I have given the Taylor series expansion in powers of chi. And now suppose you want to do a Feynman diagram, right? So here is a possible Feynman diagram. One-point function of sigma will have a contribution like this. So here the thick line is the sigma line and the thin line is the chi line. Okay. So this interaction vortex, for example, will give a sigma chi coupling. Okay. And if we now apply the usual Feynman rules, right, you will find this overall constant over here, but this loop, okay, this is a 0 plus 1 dimensional variable, right? Chi depends only on t. So this loop will give an integral in the over the moment energy space of this form, and this is clearly infinite. Right? And this is the kind of infinities that you will encounter also in the real d0 brane problem. The remedy is that you have to treat chi as collective mode and not via perturbative expansion. So you have to take the external states to be momentum eigenstates, which you get by your quantizing chi as a free particle quantum mechanics. Now there are various ways one can approach this problem. The approach that we took, in fact this is the one we found to be the easiest, is that we treat chi using Hamiltonian formulation, okay, and in that process we just treat sigma as a background field. Then you calculate the relevant matrix element of the interaction term between the incoming and outgoing d0 brane state, and then take the matrix element as an interaction term involving sigma, and then proceed to quantize sigma as usual. So here is an illustration of how we do it. Okay. So we will first of all normalize the momentum eigenstates of the d0 brane as in the usual way. Okay, the incoming state of momentum k and the outgoing state of momentum k out has this inner product. Okay. We introduce a Fourier transform of sigma tilde of sigma. Okay, this is just a technical point because it's easier to work with sigma tilde. Okay. And now we simply take the linear term, linear interaction term that we had here, this term over here. This is the only term that couples sigma to chi, right? We take this term and calculate the matrix element of this between the incoming and the outgoing d0 brane state. Okay. So we first replace sigma by its Fourier transform, right? That's what we see here. So the what comes inside has become this e to the minus I omega t plus k dot chi, okay, from here. Next, we take this chi of t and use the Hamiltonian evolution, right, by writing this as chi of 0 and e to the iht, e to the minus iht, where h is the Hamiltonian of this d0 brane system. So this e to the iht and e to the minus iht gives you the energies of the outgoing and incoming d0 brane states, right? So which are just here. Okay. Minus I omega t was there already here. Okay. And then you have the matrix element between k out e to the I k dot chi at t equal to 0 and k in. And this matrix element of course is the simple quantum mechanical matrix element, and that gives you this momentum conserving delta function over here. Okay. So this delta function comes after integration over this t, right, because of this factor over here, and this delta function just comes from the matrix element. Okay. So at the end, this is what we get. Okay. So this is what I have written here. So effectively, after you quantize the d0 brane, we get an interaction term involving sigma, that is basically a linear term in sigma of this kind. Okay. And from this we can read out the one-point function of sigma, okay, of energy omega and momentum k, and that's the coefficient that appears here, right, f of I k, and then this object over here. So this is the result. Okay. So the main task then is to find analog of f of I k for the d0 brane tachyon scattering problem, and we will do this using string field theory. Yes, exactly, that's what we will do. We will compute this. I mean, this is the general structure that we have written, right? But basically the idea is that we will try to compute this f using string field theory. Right? That's where the string field theory inputs will come in. Otherwise, it's a completely general form of the action. Well, there are of course higher order terms, okay, but those are not important. Maybe I should have said it here that you see, I have not included a term that involves in the original. Let's go back. Here, I have not included a term that contains linear derivative, time derivative of sigma, right? Because time reversal invariance basically prevents that from occurring here. You could have had, say, second derivative, del t, the ddt square of sigma, okay, but those can be fieldly defined away, because you can see from here that the equation of motion for sigma relates the second time derivative of sigma with the second space derivative of sigma, and using that we can basically replace all second time derivative of sigma in terms of second space derivative of sigma. So this is completely general up to linear order in sigma. Then there can be higher order terms, okay, but those will not be relevant for the particular scattering amplitude that we are trying to compute. So in that sense, it's completely general, and all you have to do is to read out what this f is from string theory. Yes.
So that it's divergent, like I had divergent, but
Yes.
now you are working. Sorry. Now you are working in a sense not expanding in power of pi, but considering like it's exponential of like some using some transitional. Is it only the difference? So in a sense, if I do the first approach and resum all the loops, I should get the same result here?
In principle, if you resum all the loops, you should get the second one, except that each loop is divergent.
Okay.
Right? So it's not clear how to, that you have to first, before regulating, you cannot resum the loops, right?
Yeah. Yeah.
So that's the main problem.
Okay.
Whereas in this approach, right, you just do it at one go. And this, in the language of string theory, will mean that you are resumming, right, infinite number of diagrams, higher and higher genus, right, because you are including more and more loops, right, so which are higher order amplitudes. Okay, so now let me give some brief introduction to string field theory. So in the worldsheet description, if we have an n-point scattering amplitude, then it takes a form like this. So it's an integral of some integrand In over the moduli space of Riemann surfaces with n punctures. So this In is computed using correlation function of n vertex operators correspond to these n external states inserted at the punctures of the Riemann surface, and then besides this you also have to insert some universal operators which involves hosts, and if you are doing superstrings, also picture changing operators. Okay, but these are completely universal. Coming back to annulus one-point function, there you saw that there are integrals over x and t, and these are precisely the coordinates of the corresponding moduli space of Riemann surfaces, right? Moduli space of, in this case, the annulus with one puncture. String field theory is a slightly different approach to computing string amplitudes. It's a regular quantum theory of infinite number of fields, and it's designed so that it formally reproduces the amplitudes that we get from the worldsheet theory. As in any quantum field theory, the amplitudes on string field theory will be given by sum over Feynman diagrams. And the way string field theory is designed is that each Feynman diagram gives an integral of exactly the same form that we saw here, except that the domain of integration is restricted to a sub-region of the full moduli space. And when you sum over all Feynman diagrams, you get back the full amplitude. That's the way string field theory reproduces the usual string amplitudes, at least formally. Now here you should also add that the decomposition of the moduli space that string field theory provides is not unique. And it's not unique because we will see an example of this also later. The string field theory comes with an intrinsic set of parameters. Different choice of these parameters correspond to different ways of dividing up the moduli spaces. Okay, so that's why it's not a unique decomposition. But one can show that these different string field theories that are labeled by these different choice of parameters are actually all related by field definition. And hence, all physical results will be independent of which version of string field theory we use, even though the result of individual Feynman diagrams will depend on version of string field theory that we are using. Now here is some more detail on how exactly we make connection between string theory Feynman diagrams and the usual worldsheet amplitudes. And these come via what we call the Swinger parameter representation. So the Swinger parameter representation of an ordinary propagator is given here. An integral from 0 to infinity of this kind. Okay, you can do this integral and you can clearly verify that as long as k square plus m square is positive, this is an identity. Now, these S variables in fact become the worldsheet modular parameters. Okay, and the divergences that you see in the worldsheet modular parameter integral are precisely the divergences that arise as S goes to infinity end of these integrals. Now, if you look at this integral, you see that for as long as k square plus m square is positive, there is really no divergence. But when k square plus m square is negative or 0, then this integral diverges. And that's basically the origin of all the problems that we see in the worldsheet integrals, all the divergences that we see in the worldsheet integrals. And the way string field theory handles it, that for whenever k square plus m square is less than 0, then you simply use the left hand side, right? Because left hand side is not divergent, right hand side diverges. So you simply use the left hand side and hence we remove the divergence. But when k square plus m square is 0, then we have genuine divergence because these correspond to essentially to massless states or some on-shell internal states. And there we have to basically remove these contributions from the propagator and treat them as we treat the collective modes of the toy model. Okay, so that's the basic philosophy that we'll be using in our analysis. Okay. So these are the main culprits. So with this, let me now turn to the specific problem at hand, the D0 tachyon scattering. Okay, and we will see how we can use string field theory to resolve these problems. So before going into the details of the calculation, let me describe the kinematics of the D0 tachyon scattering. Now usually whenever you look at a 3-point function, 3-point functions in fact quite often vanish due to kinematic constraints on the momenta. And this in fact is also true for just the normal 3 graviton amplitudes. Okay, once you put all the kinematic constraints, you find that the 3 graviton amplitude is identically 0. And the standard remedy to this is that we allow the external momenta to be complex but on-shell. We are still computing on-shell amplitudes but take the external momenta to be complex. Then the 3 graviton amplitude is non-zero. You can calculate it in string theory and you can, for example, use it to construct the effective action that gives the same tree graviton amplitude. Okay. So for D0 D0 tachyon amplitude, we do exactly the same. So the incoming D0 brane we take to have energy momentum of this form. So energy is taken to be the mass of the D0 brane, and the momentum is taken to be some k1 vector with k1 square equal to 0. And you see that this can be possible only if k1 is allowed to be complex, right? Because otherwise it's just square of an Euclidean momentum. Incoming tachyon we take to be energy 0, momentum k, and with k square equal to 4. This is the on-shell condition for the incoming tachyon. And we also need this condition because the outgoing D0 brane also has to be on-shell. So once you fix the incoming momenta, the total outgoing momentum of the D0 brane is m k plus k1. The energy is still m. And in order that this is on-shell, you also need k plus k1 square equal to 0. Now, of course, you can start from this and then make a Lorentz transformation to go to other frames, and you can show that any other choice is equivalent to this by Lorentz transformation. Right? So this is a completely general choice of the incoming D0 brane momentum, incoming tachyon, and outgoing D0 brane momentum. And we will be working with this choice. So with this, let me turn to the Feynman diagrams. Now, Feynman diagrams for annulus one-point function of closed string tachyons are given by some of these. Okay. Maybe I should have said it at this stage that given the general formalism, right, the linear term in sigma comes from the disk one-point function, right, which we already have computed. It's finite, right? Except that instead of having just energy conserving delta function, now by this general formula over here, by this general formula that we found here, right, this Fik will involve in particular this one-point function, but by the logic that I explained here, it should have the full energy momentum conserving delta function. Okay. But the real challenge is to compute the F from the annulus one-point function, and that's what we are doing here. So here are the relevant Feynman diagrams that we need for computing annulus one-point function of closed string tachyons. Okay. So here the convention is that the thick lines are external closed string states, right, closed string tachyon states, and the internal lines are open string states, and you are supposed to sum over all open string states propagating in the internal lines, okay, in a particular gauge. You have to gauge fix, and then you compute the propagation of all open string states. Okay. And the other convention that we are using is that the cross here denotes the 3-point function induced from disk, and these correspond to 1-point function from the annulus. Right? That's the convention. These are contact interactions, okay, but the divergences come really from the propagators, as you can see, and we will see these. So let's look at these diagrams again. Now, let me explain the sources of the divergence. So let's suppose that there is a tachyon that is propagating along propagator 1. Okay, m square equal to -1 and external closed string. Okay, I will take the, you remember the kinematics, the incoming tachyon has 0 energy. Okay, it has spatial momentum k, but of course on the disk, the spatial momentum is not conserved, only the incoming energy is relevant. Okay, so it has energy 0. So by energy conservation, then this tachyon that the open string state is propagating here will also carry energy 0, right? So that's what I have written here. Okay. So this propagator is really 1 over -1, right? Because m square is -1, and now we use the usual Schwinger parameterization to rewrite this. Okay. And we see that because of this plus sign over here, which comes from because there is a minus sign here. Okay, you have m square equal to -1. This is divergent. Okay. This we can rewrite as in terms of this variable q1, but nevertheless it's still divergent. Q1 equal to 0 gives a divergent result. Okay. Just keep this in mind because we will see this in the integral that we will encounter, or that we have already encountered. Now let's look at the tachyon along propagator 2. Here. Okay. Here we will get d omega, there's an energy integral, okay, and then you have the propagator over here. But now the idea is that we are supposed to rewrite this propagator in the Schwinger representation, right? So that's what is here, and the omega integral will be done by the weak rotation. That's the role of this I epsilon. Okay, so the omega integration, you should really think of this as from minus I infinity to I infinity. Okay. So after you do that, then the omega integral can be done, okay, by taking it to be minus I infinity to I infinity. It's a convergent integral, okay, and we get a result of this kind. Okay. And we see that this is divergent, right? As for large t, it has an exponential growth and 1 over root t, so this is divergent. Okay. But we know that this side is perfectly finite. Finally, we consider a massless particle along this propagator 2, right? That's here. Again, you replace this by the Schwinger parameter integral like this. Okay. And after you do the omega integral, okay, from minus I infinity to I infinity, right? That's the origin of this factor of I, and we get dt times 1 over square root of t, right? That's the result of the omega integral over here. Yes, but this is also not a genuine divergence. Last one is a genuine divergence, right? That's the main point. So that's the sense in which I said that tachyon can be handled, right? Because these are, once you think of this as a normal propagator, right, it's not a genuine divergence. It's a massless one, that's a problematic one. Why are you trying to write all of this? Yeah, we'll see. We'll see because we'll have to reinterpret what we had in the open string, in the expression, that integral that I showed you. So here it is. Okay. So let me, I have written the same things here again, right? Minus 1 as integral over Schwinger parameter, this one as integral over Schwinger parameter, and this one also as integral over Schwinger parameter. And now the point is that the divergences that we see on the right hand side are exactly the kind of divergences we came across earlier, right? Once you identify q1 as x, you see that this is quadratically divergent, dx over x square, right? If you remember, we had dx over sine square 2 pi x, right? That's exactly the kind of divergence that we encountered at x equal to 0. dt e to the 2 pi t over square root of t, right? This again we have seen before. Let me show you in case you have forgotten. Here, right? dt t to the minus half e to the 2 pi t. Okay, now you see that once you identify, once you compare with that, this you can identify as because of the tachyon propagating in the loop. Okay. And you also had dt to the minus half, right, which you will see. Okay. Yeah. So the point is that for these kinds of divergences, or for these kinds of divergences, right, we simply use the left hand side. Yeah, because that's what string field theory started with, and it just to make connection with world sheet theory, you have to do this. But we don't have to use world sheet theory, we can use string field theory, and in which case these divergences pose no problem at all. Okay, you just replace it by the left hand sides, and that's perfectly fine. The problem is with these, because here the right hand side is divergent, but left hand side is also divergent, because they have the divergence at omega equal to 0. So this term has to be treated separately, and this is exactly the kind of divergence we saw in this toy model, that if you try to do Feynman diagram expansion. It's this one. And here we know that we cannot, there is no shortcut, we really have to do this collective coordinate quantization and work out this. So that's the remedy, and we will now see what we get. Subregions of the moduli space? Yes, yes. In this, basically what we will see is that the subregion in which there is a propagator, this propagator, right, that contains the appropriate degeneration near x equal to 0. Okay. These contact terms are basically everything away from the degenerations, right? The contact term has no divergence, right? It's just an ordinary integral. And the way you choose your string field theory parameters is that the near degeneration, right, is what gets contribution from Feynman diagrams with propagators. Okay? And when this is going to infinity, right, this Swinger parameter, that corresponds to basically x going to 0 limit in the worldsheet theory. When this is going to infinity, that corresponds to t goes to infinity limit in the worldsheet theory. Right? That's the way the subregions are appear in this analysis. Okay, so the strategy then is that we construct an effective string field theory action by summing over all Feynman diagrams except those that include the internal yi lines. Okay. So we take the string field theory Feynman diagrams, and as long as you remove the internal yi lines, there is no divergence. Right? We saw that we can get perfectly finite answer. Okay. And this will give an effective action of sigma and yi. Okay. And this effective action will be free from divergences because massless open string states have been removed from the propagators. The second step in this analysis is to look for a field definition from the yi variables, which are the string field theory variables, to the chi variables, they are the collective coordinates. Okay. It's not automatic that yi's will be themselves chi i's. Right? In general, when you write down an action involving sigma and yi, right, they will not have the structure that we see here. Okay. But what is guaranteed is that there must be some field definition from yi to chi I, because from physics we know that the d0 plane position, okay, in space is described by the open string modes, the massless modes of the open string, right, which are the transverse directions. Okay, so there should be some field redefinition that takes you from yi to chi I, but that's something that you have to find. Yes. Yi's are the open string modes, which move the d0 plane. Alpha I minus 1 on vacuum, right, where alpha are the bosonic string oscillators, right. So those are the states, right. So those will be like for some string fields on the d0 plane, right. Yeah, so you fix a base, I mean you fix your worldsheet theory, right. So thus there are states on the d0 plane which is the alpha I minus 1 on vacuum, right. Alpha I minus 1 is the oscillator of the xi coordinates, xi are the transverse coordinates. So those are the ones which are supposed to move in the transverse direction. Right? The coefficients of those are string fields. Right? Those are the ones you call yi. Yeah, basis is fixed. Right? The worldsheet fixes the basis. So yi's are some fixed objects. Right? Now, when you go from one string field to another string field, the yi's are related by field definition. Okay? But roughly all shell, you know that these yi's are the motion of the d0 plane. Yeah, that guarantees there is a field definition, right? But that field definition is something that you have to find, right? Because the action that you arrive at is different from the structure that you have here. Okay, then you have to look for the field definition, and this is important because what happens is that this field definition, right? There is a field definition, but during this field definition there will be a Jacobian factor, right? So the string field theory puts the result as integral dyi, okay, not as integral d chi I. But because there is a change of variable from yi to chi I, there will be a Jacobian which you have to take into account. Okay. And that Jacobian you can rewrite in terms of an exponential, and you can think of this as an additional correction to the effective action. Okay. And indeed this can also correct your function f, right. So if this log of j, for example, has a linear term in sigma, okay, then this will correct f, and it does in the actual calculation. Okay. So we take string field theory action and then the effective action that you get from the string field theory calculation, and then you look for a field definition that changes yi to chi I and brings the action in this form. Once the action has been brought to this form, we have obtained f, and then we can use it to get the d0 tachyon amplitude, because we already know from here how we can calculate the d0 tachyon amplitude, and that's here. So now I am going to give the results. So the result is given as a sum of two terms, the f0, which is the disk amplitude, and the annulus. f0 we have already seen earlier, it is half gs times m, Okay. So m is of order 1 over gs, so this is really like order 1 term, and then this will have an explicit factor of gs. Now, if annulus is given as a sum over Feynman diagrams, okay, and because it's given as a sign of sum over Feynman diagram, this depends on the string field theory parameters, and the way we have chosen our string field theory, that it depends on two parameters, alpha and lambda tilde, and also an arbitrary function f of one variable. Okay, so these are all things that go into the formulation of string field theory, and the idea is that different string field theories labeled by these are related by field definition, and so the final result must be independent of these parameters. Okay. And it is very useful to have these parameters around, because the independence of these parameters is a highly non-trivial check that your result, you have not made any mistake in your calculation. If the results didn't become independent of these parameters, then that indicates that your calculation is wrong. Do I have to say anything else here? Yeah. Okay. So, and because the result is supposed to be independent of all these parameters, but we work in the limit of large alpha and lambda tilde just to simplify the analysis, okay, because then we can drop some terms which contains inverse powers of alpha and lambda tilde, okay, and because of this, in the final result we have to take the limit of large alpha and lambda tilde, okay, but that's just a technical point. In principle, you could do the exact calculation for finite alpha and lambda tilde, and the result will be completely independent of alpha and lambda tilde. Yeah, we are still testing it because there are also a lot of positive powers of alpha and lambda tilde. Okay, those have to all cancel. Okay, so that's the test. So here is the form. Okay. That because you are taking this alpha and lambda tilde to the infinity, we have to express this as the limit. Okay. Eta prime c is the say 1 over 2 pi that we saw earlier. And then this is given by a sum of many terms, right, many diagrams. Okay. So A, B, C, D are the 4 Feynman diagrams that you saw here. Okay. However, the yi propagator has been removed, so these are all finite results now. Okay. Then there are some additional Feynman diagrams because you have to do some change the gauge fixing that the usual worldsheet approach uses. So these are the ones that are coming from this change of gauge, okay, because the ghost propagation in the internal state, and also the what we call the out of single gauge propagation. Okay. Here you see a Jacobian, right? This is the contribution due to Jacobian, and in fact this also has non-trivial dependence on alpha, lambda tilde, and f, and that's crucial in order that the final dependence on alpha, lambda tilde, and f drop out. Right? So the Jacobian is a necessity. It's not just something that you have to do, but without this Jacobian you will not even get a result that's independent of the string field theory parameters. Okay, here are the forms, various forms you see. These are all finite integrals. Okay, you can see that because of this fact that the omega prime integral is from minus I infinity to I infinity, they are all finite integrals. Okay. There is a quantity Tc that appears here, right? This is recorded to the closed string tachyon. So it turns out that the naive integral, okay, also encounters divergence from the t goes to 0 end. Okay, and that can be traced to the presence of closed string tachyon. These divergences will not be there in superstrings, but it's there here because of the bosonic string has a closed string tachyon. Okay. But these can also be treated using string field theory. Okay. But in fact, in this case, you can also do it by a more direct method, okay, which is called the Witten psi epsilon prescription. And the procedure is that we take this Tc in the following way, that we, instead of integrating from 0 to this value, we integrate from some small number, say t naught to this value. Okay. For t less than t naught, you change variable from t to s, which is 1 over t. Okay. And then the s variable we integrate from 1 over t naught to 1 over t naught plus I infinity. Okay. So instead of going to infinity, you are supposed to integrate, naively you are supposed to integrate s, which is 1 over t, from the cutoff s naught to infinity. Okay. Instead of that, you integrate from s naught to s naught plus I infinity. Okay. You are still going to infinity, except that you are going in the imaginary direction, and that you can show is equivalent to using the I epsilon prescription in the Feynman propagator of the tachyon. This term is a closed string tachyon. Okay. But with this prescription, it's a completely finite integral here. Okay, because upper limit is fixed, lower limit is fixed. okay, is finite. This is finite. Here are more of these, right? So all of these are results of string field theory calculation. All are finite integrals. And now the test of independence. So what we can explicitly check is that this is independent of alpha, lambda tilde and this function f up to terms that scale as inverse powers of alpha and lambda tilde, right? So for the positive powers, we have explicitly verified that it's independent. In principle, we can fix the missing terms uniquely by requiring that the full answer is independent of alpha, lambda tilde and f. Either you do the calculation exactly, right? That's of course the more direct approach. Next approach is that we know that the result should be independent of alpha, lambda tilde and f. Okay, so you have already got the ones that contains non-negative parts or what contains positive parts. So only negative parts are allowed. Okay, and you can simply demand that the negative parts will be fixed so that the result becomes independent of alpha, lambda tilde and f. This gives a unique answer in principle. We have not done that. Okay. What we did do is to just numerically evaluate these integrals by taking alpha and lambda tilde to be large and just get a number. Okay, and we have to and then test that different choice of alpha and lambda tilde give you the same number. Now, let me just say that to get this, right, you have to take alpha and lambda tilde of order of 10 to the 6, right, because you can see that there are 6 significant figures in this. Now, when you take alpha and lambda tilde to be 10 to the 6, right, the individual terms here, okay, like FD for example, this you can show goes as 4th power of alpha and lambda tilde, right. So, alpha square lambda tilde square is I'll finish soon. So, alpha square lambda tilde square, right, is a term in this expression. So, that's 10 to the 24. Right. So, what we are doing is that we are trying to calculate a number, right, like this, okay, by adding up terms which are of order 10 to the 24. Okay, so you have to use high precision to get this number, but once you use high precision, you can check that independent of the choice of alpha and lambda tilde, we get to this within the desired accuracy. And let me just say that this procedure can in principle be generalized to higher point amplitudes and or superstring theories, because the procedure is quite simple. The calculation of course is more complicated because, as I said, for superstring theories for example, we also have picture changing operators that you have to insert, right, but there is no further divergence that is present. All the divergences are treated exactly in this way. Okay, so I'll just finish with my conclusion. So what we see is that string field theory can be used to solve the long-standing problem of scattering of D0 bands and elementary string states. And while we have done the analysis for 3-point function in the bosonic string theory, that's the simplest possible example you could find. In principle, this can be generalized to higher point functions and also in superstring theories. Now, one caveat in this analysis, okay, that this treats the D0 bands as indestructible objects, right? Because if you recall how it is treated the D0 band, right? We thought of this as a particle, right, which can scatter, and the strings can scatter of that particle. The particle can change its momentum, right? But we didn't allow, for example, annihilation of 2 D0 bands or a D0 D0 bar pair, or creation of a D0 D0 bar pair from collision of strings. Right? Those will occur in high energy collision of strings, right? The strings have to have carry energy which is of order 1 over G string, okay, and that will require different approach, right? That is not going to work in the approach that we have suggested. Okay. Nevertheless, there may be some other way, right? There one by which one can actually describe the pair production of D0 bar pair, okay, which is an open problem. Okay, I'll stop here. Thank you.
Okay, so there'll be time for questions.
Hello. So could you once again explain like removing the propagators to get these variables yi? How is that? Because in your original thing where you have to sum over all diagrams, the massless propagators were there, right? So
yes, exactly. So once you write in the string field theory language, right, we know exactly what is the contribution from the massless propagators. Right? So we just subtract them off. We just don't include them in the Feynman diagram.
Okay. So the rest result just ensures that you have everything.
Exactly. Everything else is finite, right? We just subtract off the massless propagator contribution from the Feynman diagrams, right? And that subtraction, how much you subtract, depends on these parameters alpha and lambda tilde. Right? But the divergent part goes away in each case.
Okay. Thank you.
Yeah, this is about your last remark. Like, can't we get like pair protection by some kind of crossing? Like,
Yeah, in principle you can, right? But even for crossing, one needs a relativistic formula, right? The way we are treating this is that because the d0 branes carry mass of order 1 over gs, right? The momentum transfer is also expanded in powers of gs, right? So that we are thinking of this as expansion along the non-relativistic background. If one could get a relativistic formula for this, right, then indeed, yeah, we should be able to get it by crossing.
So, but the Lorentz invariance is there in the string field theory. Right?
Yeah, Lorentz invariance is there in string field theory, but the way we are treating the d0, because you are doing a GS expansion, right, it automatically gives an expanded form of the amplitude.
Okay.
Yeah, somewhere in this talk you used string field theory, right? But
Yes.
I didn't see any string field. So which
Yeah.
string field theory did you use, or?
Yeah, so I didn't say which string field theory I used. Basically, this is what is called the SL2R vortices, right? So it specifies what the off-shell 3 string vortex is, 3 open string vortex, and the off-shell closed open string vortex, right? They are the parameters alpha and lambda tilde and f those entered, right? And using those, so the result of it, that's why the result of each of these Feynman diagrams, the Feynman diagram A, for example, okay, I have given the result here, Fa. Okay. You can see that depends on the lambda tilde and alpha, right? Because the interaction vortices depend on this. So these interaction vortices give the contribution of the tachyon and the heavy open string modes, but we remove the massless contribution.
And is it possible to do these calculations in different string field theories and just to check their internal consistency?
Yeah, I mean, different alpha and
different-
lambda tilde are different string field theories. Right?
Yeah, I thought that's like a family. Oh, that's, I mean, different formulations of different formulations of closed string field.
I think closed open string, we need the interacting theory of closed and open, right? The standard formulation is based on what is called L infinity formulation.
Okay.
Right? So all of these are within the
But
L.
if there was another formulation, you could pose the same problem there.
Yeah, and it should give the same result. Right? But at least within this family, okay, we can see that this is the.
And this family has these parameters lambda tilde and alpha.
Yeah, lambda tilde alpha, and then also there's another function f,
Yeah.
right, which is in this family. So all the interaction, off-shell interaction vortices depend on these parameters, right? That's why we can see that because the tachyon is off-shell, right, that which is propagating, okay, that's why you have this highly complicated dependence on lambda tilde and alpha. So it's not a small dependence, right? And the result is at the end, all of these dependencies would go away.
Ashok,
Yes.
could you try to use supergravity perhaps for n d0 brines to compute the scattering of gravitons of a stack of n d0 brines and try to compare to the constant that you computed?
I think in low momentum transfer probably it will work, right? If you do supergravity. The point, this is really a stringy calculation, right? This particular calculation, because the external tachyon, right, carries momentum of the order of the string scale. So this probably you cannot do using supergravity, but you are right that if you are trying to calculate a graviton tachyon or d0 brane scattering at low energy, right, you can probably, it should probably agree with what you get from supergravity. But the stringy corrections you will not get from supergravity, right? Whereas this one will give the full stringy corrections, right? It will not require that the external energies are small compared to the string scale, right? But you shouldn't have external energy of the order of the 1 over G string, right? Because then you will start producing d0 branes.
But if you had a stack of n d0 brines, how would this computation be effective? Would just be.
I think this will just put the Chan pattern factor.
That's all.
Yeah, that's all. Yeah, I don't think that there will be a change there.
Any more questions?
If you were to try to do this calculation analytically, not numerically, is anything known about like what is the number space, like the transcendentality of, is it like multiple zeta values or something? Is anything known about
Yeah,
that?
I don't know. The point is, I'm sure one can figure it out, right? I'm just not an expert in this analysis because, I mean, but the integrals are very much there, right? I mean, one can just examine these integrals, and it's not even impossible that there is an analytic expression that one can find from here, right? It's just that we don't have it. Right? So, yeah, so I think the answer, your question can be answered because you have explicit integrals for all of this, right? But I don't know the answer.
Okay, if there are no more questions, let's thank Ashok once again. And now we disperse for tea, and the registration desk is also open. So let's reconvene at 11:45.
इसको ये कैसे करें ऑन हाँ उसको कैसे ऑन करें वो लोग ऑन करेंगे हाँ अच्छा 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 सो दिस इज ऑन फुल स्क्रीन राइट नाउ अच्छा ये कॉलर माइक लगा पाओगे तुम कैसे लगाते हैं कॉलर माइक एक पॉकेट में जाएगा एक
some metric, which can be a distance in your function space, a constraint, and so on. And the idea is that you want to tune, so your structure will depend on some parameter, and you want to tune this parameter to improve the approximation. And so as you see, like in this box, in classical programming, you have data, and you give also the rules to process the data, and you get the results. Here, with machine learning, you give the data and the results, and it will give you the rules to get to that point. Okay? So now I will focus on neural network in this talk. So what is a neural network? So it's a sequence of layers which implement computations. And the layer each output, as I said, is a different data representation, and they are correspond to transformation parameterized by weight. So you have many types of layers, like dense, convolution, and so on, so it's not very important here. The main point is that it's just a way to change the representation of your data and to iterate this process. So it looks like this. So you start with your input data. Then you feed it to some layer which performs a transformation. You feed it to another layer, and so on until you get your predictions. Now you can feed this prediction to some objective function, and the objective function can depend also on the input and on the true results. But these two are optional. Like you can choose to, I mean, depending on the problem, you may not give the true results if you don't know them. So this is called unsupervised. If you give the true result, it's called supervised learning. From this objective function, you get a score. And now you try to improve this score using optimization. And so you update the weights of the network to get a better, and you evaluate again. And if the score gets better and better, you continue until it doesn't improve. And this gives you something which hopefully is close to the result you're looking for. Okay. So why do we want to use neural networks? So the first reason is that they generically outperform any other machine learning algorithm, except maybe the tensor networks. The inputs are flexible, so you can give complex number, graphs, language, as we know, and so on. Also now with like this modern approach to programming, the neural network you get in your code are differentiable in the sense that the full code you get can be differentiated. So it's very useful if your constraints are like integrals, differential equation, and so on. It's also solving for the full function, so it's not like a point-by-point like optimization, but you get a function. And this function, in some cases, will interpolate, and in some cases, will also extrapolate. So you get even more than what you have inputted, which you cannot do in general with a fit. It's also proven mathematically that neural network can approximate more function than just fit. And also, in the case of a classification, you get a probabilistic measure on your space, which can be nice, for example, if you want to do Monte Carlo. Other advantages are like transfer learning. So it means if you train your neural network for one task and you want to solve another related task, you have a chance. So some technique to reuse most of the neural network, so you spare a lot of time for training. And also the representation is very small, so it's just a few like kilobytes, so you can easily send the information of your neural network to other people so that they can reuse it. Okay, so now I will move to the minimal area string vertices. So how is it? So it's vertices which satisfy three conditions. So the metric on the surface should have a minimal area under two constraints. First, there is a bound on the shortest closed geodesics, which is called the systole. And then there is also bounds on the height of internal foliation. So I don't want to enter in the mathematical details of all this and to see what it corresponds to. I will directly move to the case which we're interested. So yes, and just to say that once you get this metric, you can directly read out the local coordinates and vertex region. So the metric is really what you want to obtain. And now if you look at tree-level amplitude, you don't need this vertices. You can take some limit, where in fact you take this internal foliation to be 0. And so you get a metric which is built from a Strebel quadratic differential. So this is a subcase of, a limit of this case here, which is a bit simpler to handle. And the point is that it's fixed up to moduli dependent parameter. And this corresponds to contact interaction in the sense of string. So it's not like space-time contact, but it's as contact interaction as you can get with string theory. And it's in this sense that this representation is kind of optimal for the string field action. So what is the state of the art? So analytic solution we have for n equals 3, which is easy. So it corresponds to Wheaton's vertex. We have a numerical solution for n equals 4 and 5 from Muller. but some of the data for NA5 has been lost because the data was too big and not easy to fit or represent. And so now it's not available anymore. And there is also like a convex program for any G and N, but it has not been implemented, and it has not been restricted to the vertex region. So it means that this condition 2 has not been added. Okay. So here the purpose will be to try to improve on this and give a general algorithm which should work for any n, so that we can try to build the vertices up to some large n. So what is a quadratic differential? So it's a function. So it's a form like this. So phi z dz square, and the parameterization we use here for the phi is as follows. So we see that we have double pose with residue -1 at each of the punctures, so which correspond to the moduli. And then we have a simple pole also at each puncture with some parameters ci. So the ci, I will call them accessory parameter because they correspond to limit of the accessory parameter we have in the Liouville theory. And we can also show that we need 3 constraints for regularity at infinity. So we will have n-3 ci to find, and it corresponds also to the number of moduli for the sphere, where for the n-puncture sphere we have n-3 moduli. Okay? And now the point is that if you know phi, it induces a metric of this form. And as I said, if you know the metric, you know the local coordinates and vertex region. So it's why we focus on this metric. And the point of this metric is that you have semi-infinite Fred cylinder around the punctures, so which correspond to external strings, because you can really see your strings as like the cylinders which come from infinity, arrive on the surface where they interact with each other, and then some strings just go out again. So I will not enter in the details of this like Strebel differential. Maybe Rajesh will do in his talk. But so here the only thing I want to say is that it's a very hard mathematical problem to solve for them in general. And the point that a necessary and sufficient conditions with S to get them is to solve this equation. So we need the imaginary part of some function L between some pairs of points Zij to be 0. So here the Zi are the zeros of phi, and this L is some kind of complex length between 2 points. So it's complex because you see this phi of z is a complex function. I don't have an absolute value. And here I'm integrating over a general path in the complex plane. So in general, this will give you a complex result. But now what we are requesting is that between zeros of this phi, this L should really be a real distance. And so this will give you a set of, for any fixed moduli, this gives you equation on the CI, so in general you can solve them. So now one of the issues is that it's an over-constrained system, so you have too many equations. So when you solve, you have to filter out some of the equation if you want to use Newton's method. And it's what Meyers did. So for n equal 4 and 5, and as I said, he gave a fit just for n equal 4, so to which we could compare. Okay, now for the vertex region, the point that you want that all lengths of non-contractible curve are larger than 2 pi. So I don't want to go again in the details, mathematical details. But the way it translates for the case of n equal 4, on which I will focus, is that there are 3 distances, which I will introduce later, which should be larger than pi. Okay? And so from here, you can introduce also indicator function, which will be useful for later. So this indicator function theta tells me if I am inside or outside the vertex region. So it means that if I have an integral over the vertex region, I can just replace it by an integral over the moduli space with the insertion of this indicator function. And you will see later why this is useful to do so. Okay, so now let me move to the machine learning part. So first we need to solve for the C lambda. So now I'm just focusing on the n-3 function. So yes.
Can you tell me about the metric that is being induced by the quadratic differential, about the semi-infinite cylinder, that part?
Yes, so if you look at the form of the metric, so here in general it's this form, but if you go close to the local coordinates, I mean you move to the local coordinates, the metric will take this form. So here you see that it would diverge for 0 and infinity. So it will mean that infinity, I mean, you can see your surface if you do some conformal transformation as some tube which arrive on your surface. And so you would... Closer, so yeah, it will be a tube, so which is your external string. hope it helps. Is there any more questions? No? Okay. So now to solve. So we want to find the C lambda. So lambda here runs over the independent number of moduli. And we want to represent this C lambda by a complex neural network, which will depend on the C lambda. And then we have some parameters W and B, which will be weights called weights and biases, and they are complex matrices and vectors. So here is something also which was a bit harder when we set up this study, is that complex neural network were a bit studied, but they appear almost nowhere in the literature of machine learning, because like startups want to make money with the real world, and the real world has not so many complex numbers, so they don't care too much about these complex numbers. I mean, complex neural networks. So it was a bit like harder to try to really dig and find how to set up the architectures. And so here the way we trained was to use all this function I have shown. Okay, here there is no equal, it's just superior. So I'm just taking the square of each function and adding them to each other because I want something to be positive definite. And when I have this, I can just try to minimize with gradient descent to find the optimal value for W and B. And we know that for a fixed moduli, we have a global minimum for any n where the C lambda are given by Strebel differential. So in this sense, it's a very well-posed mathematical problem, so we can expect to have a very good accuracy with this technique. And for the training sake, it's just a uniform sampling in the moduli space minus disk on each of the punctures, because here we know that the Strebel differential is singular. So we want to just stay away from the singularity. And we know that in any case, the vertex region will be away from this region, so it's fine if we don't have them in training. So here is my training set. So you see I've taken like some points, I think 100,000. But it works even, like you can get a very decent result if you just use 1,000 points in this area. So it's really an efficient algorithm. Now I'm introducing some notation for an equal 4. So I will just call the single moduli psi. The C1, I will replace it by, parameterize in this way, and I will try to solve for this A. And the 3 distance I was mentioning before is the distance between the 3 independent, between the first 0 and the 3 others. We have a few analytic solutions, so we know the solution at 2 special points, so A equal 1/2 and this Q here, and we know also the solution on the real line, so this was also new in the paper. So as you see, given the little number of exact solution, we cannot do supervised learning, so it's why we had to come up with this unsupervised version. So here it's a very brief slide to give some information on the general process. So we had a fully connected neural network with this serial activation. As I said, 100,000 points with some ADAM and so on, so I don't go in the details. Now the statistic on the loss, so this objective function we try to minimize. So the average value is 10 to the minus 7, which is basically the machine precision. So we could not expect to, in any case with this approach, get much better. The median is also 10 to the minus 8. In the minimal case, so it's 10 to the minus 11, but again, here we are below machine precision, so it doesn't make too much sense to pay attention here. And the maximal error is 10 to the minus 5. So as you see, it's extremely precise. And as I was mentioning, with just 1,000 points and 100 epochs, so here it trains in like 10 minutes on my laptop, you already get a mean loss of 10 to the minus 5. And now if we compare what we get with a fit from Muller, we have 5 to the 10 minus 3. So as you see, we are really reproducing the earlier result from Muller, which are a bit precise. Yes?
This nonlinearity is acting separately on real and imaginary part doesn't seem to preserve analyticity.
Yes, but it doesn't matter. Like, since the loss function kind of encodes this, it's kind of coming there in any case.
So we can just forget about analyticity while we do this?
Yeah. Okay. It will give. So one example I will show is that, for example, because there is a single solution, so if the solution is analytic, it has to find it.
No, but what if there is also a non-analytic solution which obeys your constraints?
So here in this case, it's proven that you have just a single solution. The solution is unique, so
solution, not even without imposing analyticity, is also unique.
I think so. I mean, I will need to check the theorem, but I don't think the theorem assume.
Because once you give up analyticity, becomes very flexible, right?
Mm. But so I'm not. Okay, we need to. I'm not even sure that this A is analytic, but in Xi, maybe depending on Xi and Xi bar. But this I will need to check. I forgot.
Okay.
But what I will show after is that, I mean, there is a slide, but for example, like there are some symmetries and it just learns them because the solution has a symmetry, so it has to come with them. So often, it's something nice when your problem is very well posed, is that you don't necessarily have to give too much information for it to find the solution. Then, okay, if you give the solution, you can go faster, maybe, and so on, but it's not even necessary sometimes. So here are some plots to show the... so here the plot in the lower right corner is a plot of the function in the complex plane. So here is what I was saying, is that we didn't need to have a fit, we have this neural network, and it will be defined in the full complex plane. So we can just start to plot it. Now that we have this function, we can try to do things like symbolic regression to extract an analytic formula also. So it's something you can do. Here it's a distribution of the loss. So as you see, it's really peaked around this 10 to the minus 7. Training goes very fast, so we don't need to go to, you see, like around 500 epochs, it's already converged. And the interesting part is here. So here we compare the neural network with the solution on the real line. So as you see, like imaginary part is really 0, except like at starting at -1, it starts to be a bit non-zero. Inside the training region, which is like this box, we almost perfectly agree with the analytic formula, and the only case where we don't agree is at 0. Sorry, -1/2 and 1/2. It's like there is some, I mean, effect because of the punctures at 0. No, so it's at 0 and 1. So it's because of the, it's where you have the punctures, so it's why you have some difference effect. And here what you observe is that it's also extrapolating outside the training region. So here we didn't give any samples or any training here, but it still managed to match the analytic solution. Okay, so here it's just to show that it learns the symmetries of the function. Here it's to show like how we can extract the local coordinate patches. And now, given the time, I will go fast. So for the vertex region, we have to train a neural network. So here it's supervised, and we want to do a classification. So we want a neural network to tell if we are inside or outside the vertex region. Again, it works very well. So we reach like 99.3% accuracy. It's even better on the test set. What you can do is that you can plot the probability to be inside and outside. So as you see, like it's extremely sharp. So there is just a small region where the probability is not 0 and 1. And in fact, you can use this probability to find the boundary of the vertex region. So it's also something very nice because it just there. You don't have to, add some processing. It gives you the boundary. Now you can use all this information to compute this VN. So here I will not enter in the detail, but just to say that here everything is parameterized in terms of your neural network. And here is what we get. So like in these previous papers, I had 72.39. If you use the fit, you go to 72.41. So using a different method to compute the integral with a neural network, we got these values, so which are well, very close to the original values. The full pipeline is just 4 hours on my laptop. So as you see, it's quite fast. Okay, since I'm a bit short on time, I will skip this part. What I wanted to just explain is that you can use quantum-inspired algorithm like this tensor network. So tensor network were used to compress states. Now the point is that people develop technique to also like encode a function in the form of a tensor network. So it's called a tensor train. And the point that once you have encoded your function as a tensor train, you can use all the technique developed in quantum mechanics to solve problems. So with this, you can solve like algebraic equations, differential equations, and so on. And it's very efficient because you can do multi-dimensional integration in a simpler way, so you don't need Monte Carlo. And you can also, you have also a multi-scale resolution, so it's much more precise than neural network. So we conclude. So here we gave a new method to construct the endpoint string vertices. The implementation for network 4 reproduce the known results. And we also outline a general method to compute a geometrical function from a variational agents. What we want to do is to increase the precision, generalize to n equals 5 and more, and explore also tensor network. Then when we have this, we want to study the clustering tachyon potential and try to settle this issue. Then we would like to generalize to compute the quadratic differential for the Feynman region so that we can have just one pipeline to compute general amplitudes. And also, obviously, generalize this to higher genus surface so that we can compute loop correlation to string theory from first principle. Thank you.
More questions?
So when you construct the vertex regions in string field theory, they would depend on the parametrization, right? Because the full amplitude may be independent of the parametrization, but the vertex region is dependent on it, no?
Yes.
So in your thing, are you fixing a particular parametrization? Like when you're doing the machine computation via machine learning, are you fixing some parametrization that allows you to get the...
Yes, I'm using this minimal area parametrization. So everything I did is with this parametrization. So the fact that you get this shape here, yes, here, it's really because it's minimal area vertex. So this is a consequence of parametrization. If you use another thing like this SL2C, it's the graph I had here. Yeah, this one, so you see it's a different shape. So it's same information, but different. And as you say, like, once you compute the full unchained amplitude, there is no difference between the two.
This parametrization is known to be something special, or does it have any particular significance, this minimal area parametrization?
Yeah, so there are various special points. So as I was saying, it's kind of, if you move to this minimal area and zero internal foliation, you will get like contact interaction for string theory. So as contact as you can get. Also, some people studied like the coefficient of the tachyon potential. There is some like guess that it could be like they would take the minimal value using this parametrization. So you have some nice properties with this. It's also a limit of the hyperbolic geometry. So they have some like nice meaning. Yes.
Okay. Thank you.
Okay. If there are no more questions, let's thank Harold once again. The next talk is by Sachin Jain, and he'll be telling us about ideas for boundaries in twistors.
Same problem?
Titles again. The titles again. Maybe 200 is also. Go to the
This works? Yeah. Okay. Yeah. So let's start. Yeah. Okay. Thank you very much for this opportunity to speak here. Bhubaneswar is like my home place because I did a PhD here at IIB Bhubaneswar, and NISER was a small campus over there which would fit at one corner of this big auditorium. So I'll be talking about my recent work that appeared like this, like few days ago, with two collaborators. They are my student, but more like they lead the project, Arham and Dhruva. They are here in the audience. So I'll talk about areas for boundary Whiteman functions. I'll discuss importance of Whiteman functions in twistor space. I'll also discuss why we want to do it in the twistor space. We'll see some interesting factorization properties, conformal block of the dual or the CFT that comes out, and an interesting double copy that we see between 4 gluon and the 4 graviton amplitude at the tree level. There are other collaborators, Ashwini, who is here, Deep also here, Brajesh and Vibhor. Dhruva and Deep are presenting poster on the twistor space. So my talk, I'll leave a lot of technical details to Deep and Dhruva to explain, and I'll also present some part they will explain. Arhum is presenting a little different topic, large scale structures. So this is Arhum, he is here, Dhruva, Ashwini and Deep, these are the people. Other 2 people here, they are not here, so I did not put the, okay. So first I'll give you a brief motivation why we are working on, CFT is well understood in the Poisson space. There are a lot of works. I'll give a little bit of motivation and work in progress why CFT in momentum space, spinor helicity or twistor variable might be interesting and can lead to some orthogonal set of or interesting set of results which has not been understood in the Poisson space yet, which I'll show already some interesting results which are not possible to get in the Poisson space. We'll show here 3-point function results in the CFT also resembles 4D flat space result. This I'm talking about purely CFT motivation, and this results CFT correlation function in twistor or helicity variables are quite simple than the Poisson space analog. However, the 4-point function is work in progress and very, very difficult to understand momentum or spinor helicity variables. But twistor space seems to be a very, very nice place to explore them. And the ADS space is just a first step. ADS space is just a first step towards achieving that goal. So this talk is just, we want to really solve the CFT 4-point function in the twistor space. But we start with a simpler case of ADS computation and writing them in the CFT languages. So here is a brief diagrammatic description. So Poisson space CFT, all of us know. If I do Fourier transform, that's like momentum space CFT. But this direct Fourier transform is not very useful and very, very difficult to do. So rather, one would calculate the momentum space CFT correlators independently. Similarly, the twistor space actually sits in between these two. So there are certain things simple here. Twistor space has both the world, So in that way, we expect something really nice to happen in the twistor space. Twistor space can be related to Poisson space by something called Penrose transformation, and momentum space effectively by doing Fourier transform of the Penrose transformation, which is Witten transformation. This is a simple definition of the twistor. So it's an element of a fundamental representation of the double cover of the 3D conformal group. So twistor is a fundamental representation in this group. It acts twistor transform linearly under the conformal group. That is a great property of the twistor. Another interesting property is that the conservation or conserved currents, conservation becomes very, very easy in the twistor space. They become like a holomorphicity condition, okay? Sometimes you can also think about them as a highest weight condition in a representation. So here is a little more map between twistor and the Poisson space. It's a non-local map. Point in the space-time maps to line in the twistor space. Null line in the space-time maps to point in the twistor space. So here is a cartoon of this map. So already you see that maybe objects like Wilson line, null Wilson like correlation function in the CFT, which are not that easy to compute directly in the CFT, twistor spaces might become very, very easy because it just maps to the points. We have not achieved that yet, but this accommodate the scalar correlator, how to compute them, where they use something called infinity twister and other things. Also, they generalize for non-conserved current. So this is a beautiful paper. Momentum space, okay, the scalar things are fine. There are divergences, etc., but one can deal with that. 3-point spinning, Poisson space results are there, but it's a bit messy, you know. Momentum space of spinor helicity, as we know from the scattering amplitude also, that it should make the spin structure easy to handle. And the twister space also does it. It actually makes it very, very intuitive and very simple looking expression that we will see. 4-point function, Poisson space, bootstrap that people have done. Scalar thing is very well understood. Spinning thing, there is a lot of structure that comes and very, very difficult to handle. For example, if I ask, how am I going to write down even TTTT 4-point function? What are the structures? There are so many structures, maybe 100, more than 100 structures. But you know, in the twister space or in the spinor helicity variable, these are the things that will become very, very easy. So I'll, yeah, sorry. Yeah. Impose the conservation directly. It's automatic. You don't have to worry about that. So I'll briefly start with a Poisson space, describing Poisson space results. This was I'll be mainly concerned with the 3D CFT. 4D CFT is something that work in progress and is a little different than the 3D CFT approach that I'm going to discuss over here. 2011, a paper by Prakash Gyombi, they showed that any general 3-point function of conserved currents contains 3 different parts which can be written in terms of arbitrary coefficient. These are the OP coefficient, you can say. But they can be written as some free bosonic theory answer, free harmonic theory answer, and a parity odd answer, which appears in the interacting theory, which you cannot calculate from the free theory. That is the conclusion that they made. Okay? And that is also true. You can see in the Poisson space, you cannot get any more insight into that. Individual structures are quite complicated, but people wrote down some generating functional for this. These are the parity even, boson and the fermion. These are the parity even structure. They wrote down some generating functions. This is not exhaustive list, but there are a lot of work over the past few years to make good progress along this direction. And by now we have understood at least until the 3-point function very, very nicely in the momentum space or spinor helicity variables. Okay. So the point again, I just want to emphasize, directly Fourier transforming the Poisson space answer is quite difficult and it's not very useful. Another point, in momentum space for the spinning coherer, there are a lot of degeneracies, meaning there is a structure X and there is a structure Y. It's very difficult to say they are not independent, okay? But if you really work very, very hard, then they will become, you know, you might be able to show that they are actually dependent on each other. In the spinor helicity variable, if you just convert this momentum space to spinor helicity variable, it turns out that this, at least up to the 3-point function, these degeneracy structures go Yeah, degeneracy in the following sense. Let's say, in a CFT, I need to write down independent structures. If I write down a structure A and a structure B, if I subtract them, whether this is 0 or not 0, that is what if it is 0, then these two structures are degenerate. In the Poisson space also they appear.
It means you have many structures which are apparently different, but actually they are equal.
Write down something called a correlator, non-homogeneous and the homogeneous correlator. Non-homogeneous correlator is something, if I take a conservation equation, del dot, one of the indices, if I conservation equation, then I get the Watt-Takase identity. Okay, Watt-Takase identity, as you know, these are the delta functions, which becomes only non-zero at the when two operators coincide with each other. And the homogeneous part is just solution to this equation. The right hand side is just 0. The homogeneous part, okay, it just automatically conserves. It is interesting. It turns out that the free bosonic answer that we discussed earlier in the Poisson space, it breaks up into simple form, non-homogeneous plus homogeneous, and the free harmonic answer becomes non-homogeneous minus homogeneous. And the parity odd answer in the spin helicity variables are very conveniently just factor of plus minus I times the homogeneous answer. So in fact, the full 3 correlators that was in the Poisson space thought to be all independent can be just constructed out of the free bosonic answer. It is very easy to find out what is the non-homogeneous part. It is easy to find out what is the homogeneous part, and multiplying with plus minus I is very easy. So you get the parity odd part. So all the 3 structures just comes out very easily in the spin helicity thing. Another interesting result that came out, there is an interesting nice double copy relation that if you have a 3-point function, 3-point function which are multiplied, then it becomes another 3-point function with this spin summed up. In the Poisson space, if you try to find out such analog, it will be complicated, integral thing, and which you cannot make sense. Like given the expression, you cannot get these expressions. Okay, so this is another interesting thing about the CFTs in the spin helicity variables. Okay, here is another application. So once you apply these results to Chern-Simons matter theories in 3D, it turns out that there is an interesting anionic behavior that comes out, that you start with the free Fermi theory, you tune with the Chern-Simons matter coupling, and you reach the bosonic answer, and at any coupling inside, so free bosonic theory, free fermion and the free bosonic theories are parity even answer. This contains both parity even and odd. Just by tuning a parameter, you get all the answers. This is a very interesting anionic map that comes out because of the spin helicity structure. In the Poisson space, 4 or higher point function computations were very, very limited. But using the spin helicity techniques, what we were able to show that we could map all the 4 or the higher point function to free theory answers. So in principle, we know all the endpoint spinning correlator in the Chern-Simons matter theory at large n in terms of the free theory answers. Yeah. Yeah.
So there, this last equation, can that be used to get all the structures at a given spin?
Yeah, structures meaning you can just start with spin 1, spin 1, spin 1. Yeah, you can just play around.
If I have spin 7, 8, 9, then can I just keep this, generate all structures of that type?
Yeah. You just have to be a bit careful with the out of the, there is some ordering, but ordering meaning there is something called outside the triangle versus inside the triangle. There is some little issue, but in general you can get most of the correlator.
And what do you think is the meaning of this equation?
Meaning this we are not, just to remind you, I'm not talking about the OP coefficients over here. I'm talking about just the structures.
Yeah, even at the structure level.
Yeah, so it is same as the flat space scattering amplitude, where if you have multiplied two gluon amplitudes, it becomes a graviton amplitude. It's that kind of a double copy. Sorry, when you say meaning, is there something more?
Yeah, double copy, but there you require some change of some structures, right? Because you have to remove color factor and add something else and so on. Here it just comes out.
No, here it just comes out, and in fact, this is cleanest for the homogeneous case. For the non-homogeneous case, it turns out Bowman, etc. In the twistor variable, this also comes out.
I see.
So you get this kind of double copy structures.
Okay.
Yeah.
Is it the same as the position space double copy or it's not?
A position space CFT correlator, there is no double copy. You cannot, it's a non-local integral transform, meaning people did not know about it. You use this to transform in the position space and see if you can make sense. It's very difficult to just do the integrations also. You cannot also verify. But this predicts that in the position space, there is indeed a double copy also. But it's a, just a Fourier transform which will be convolution.
I see. Even at the integrand level, you can't see it. I mean,
no. Okay, so one line summary here that what I wanted to say that using in the position space it was not possible, but in the spinalicity variables what we were able to show is that we are able to map CFT 4-point or higher point spinning correlator in this interacting theory to the free theories. Yes.
I had a question related to the double copy. Does it extend beyond 3-point?
Very good question. So we'll see. This is one of the things that people have been trying to figure out in ADS space, etc. At the tree level, is there a double copy or not? For example, you can also ask in a generic CFT, definitely it is not going to be there because the 4-point also have OP coefficient, and there is no such reason for the OP coefficient to obey such a constant. But I believe in the free theories, because OP coefficients are very simple and 1, they are all identical. So in the free theories, there is a spin like higher spin block. So there it might exist, but in general, in a generic CFT, it is not going to exist. But ADS correlated, they might exist and they will exist. And in this talk also we'll see at the end.
Okay, thank you.
Yeah. In terms of conformal block, you can ask that question. This is like a channel by channel. But I'm saying in the full correlator, as you pointed out, I'm going to talk about full correlator. Only thing that can happen is that, higher spin blocks, which sums up everything, there might exist this double copy. Yeah. Here is another interesting thing that came out of this construction is that, there is a Chern-Simons matter theories are dual to, there is a bulk dual to them, that is Vasiliev theory. And in the Vasiliev theory, people thought it's a local, unitary, nice theory of higher spin things. But recently there has been a lot of discussion whether it's really a local theory or not. For example, people claim that the 4-point contact diagram in this set of theories are identical to exchange diagram. So the local interaction behaves like a non-local interaction. So these are in some sense non-local theories. That's a claim. It's not yet resolved very, very nicely. So we tried to make sense out of these things from the CFT perspective. And in the process, people also then conjectured that people also, discovered a theory called chiral higher spin theories, which is a subset of full Vasiliev theories, higher spin theories. And they claimed that it will also be a dual to some sector of the Chern-Simons matter theory. Directly in the position space, it was not possible to identify those things. But in a paper with Dhruba and Skvortsov, parallelly a paper that appeared by Ofer, Rohit, Tripko, we are able to show that if I take the coupling constant of Chern-Simons matter theories to the complex plane and take some particular limits, as we have discussed over here, you can precisely map these 3-point functions to the chiral or anti-chiral sector. Okay. So you can just see that, like if I take this limit, one of these things will drop out and only one of these things will remain. So it will go to the chiral or anti-chiral sector. So yeah, all these results I wanted to emphasize because it gives me or gives us encourages us or gives enough motivation to explore the momentum space of spinalicity variables because, sorry, I cannot see. Oh, 10 minutes, okay. Because there are a lot of results that were not possible to get in the Poisson space. Here it is actually possible. But the main difficulty remains. What we want to do is to get to the 4-point function in these variables, either momentum space, finality variable, etc. And one of the main difficulties is that one has to solve a second order partial coupled differential equation. Yeah.
As you know, 4-point function contains infinity of dynamical information, right? It contains P coefficients for all the blocks. So for 3-point function, I understand when you say that you want to get to it, modulo P coefficient, you just have the structure. But now 4-point function has all sorts of things.
Yeah.
So what do you mean you want to get to the?
Yeah. Sorry, I should have clarified. In the Poisson space, there is a for 4 scalar, there is an expression that some prefactor times f of u comma v, right? Cross ratios. In the momentum space, if you want to get to such an expression, if you just want to find out something which solves the conformal word identity, it runs into something called simplex integrations, shown by Skenderis and collaborators. It's a for 4-point function there are 3 integration representation. It's not something like algebraic expression that solves directly. Like in the Poisson space, if I have a function of f of u comma v, that's solved. That is conformal things are solved. Momentum space, there is no such statement. So you cannot. It's very difficult to find out a function explicitly. I cannot start with an answer. Okay, maybe these are the kind of function f of u v which will solve the conformal word identity. Even that statement does not exist. It's very difficult. I see. Yeah, sorry. So, okay, let's start again. So, in the spinning variable, special conformal generator become del 2 del lambda bar. It is very much tempting to do a half Fourier transform to convert them into first order differential equation. Because this is del 2 del lambda bar. Let's do half Fourier transform with respect to lambda bar, then it will become a first order differential equation. This is the same problem we can consider in the case of twisters. The problem is that we have been talking about the Euclidean CFT, and the lambda bar and lambda are not independent. They are complex conjugate of each other, or Hermitian conjugate. So you cannot simply do a Fourier transform. However, what we noticed in a paper with Dhruva Deep, that if we consider the SUSY supersymmetric generalization, at least in the Grassmann variable, if we try to do this kind of half Fourier transform, the results or the computation drastically simplifies. At least it was very easy to handle the Grassmann part of the calculation, but still the momentum part was not that easy. Very recently, a beautiful paper by Baumann, Pimentel, Mathis, and Rost appeared, and where essentially they pointed out that the idea is to go to the Minkowski space. And interesting thing is that if I go to the Minkowski space, lambda and lambda bar now become independent, and now we can do a Fourier transform with respect to lambda bar. Then, as it is clear, this K will become first order differential equation. Okay. As we discussed in the twister space, twisters are like a fundamental representation in the double cover of the conformal group. In terms of this, so what we have done, there are variables like lambda and lambda bar. What I'm going to do is to do a half Fourier transform with respect to lambda bar or lambda. I'll call that to be lambda mu or lambda mu bar or mu lambda bar, depending on what I'm doing half Fourier transform with respect to. I'll define the twister to be lambda mu bar and the dual twister to be mu lambda bar. This will be the same definition that I discussed earlier. Now the conformal generators becomes like this, and as we discussed that the conservation in the twister space becomes automatic, so the non-homogeneous and the homogeneous pieces, they become identical, okay? So the 2-point function you can calculate, it's just a polynomial just like in the Poisson space. 3-point function, it's tempting to write down that it's like a polynomial thing, but it turns out it's a wrong answer. It gives if you convert this to Poisson space, this polynomial answer gives you something wrong. But given this kind of differential equation, this is well known that the polynomials are the solutions that we have been taught. Even Mathematica, you give to Mathematica, it is going to give you the polynomial answers. Okay, so it turns out something very beautifully discovered by one of the students that in mathematics literature they call something called weak solutions. Weak solutions are such that it's like a distribution solution, distributive solution. And it turns out that the actual solution that you need to take are bunch of delta functions. These are defined like this, okay? And this produces correctly the Poisson space answer or the Momentum space answer. So a polynomial answer is not good, but this delta function solutions are actually good. Converting to supersymmetry actually become very, very easy. So one defines a super twister, and in the super twister, all the results, just you change all the result by their super twister generalization, and then that's the answer. We don't have to do anything. Yeah. Sorry. Triangle constraint? No, it will be a different delta function then. It will be a different delta function. It will be related to sine functions then. Yeah. Okay, so I'll now, since I have only 2-3 minutes, I'll just be very quick with the last part. The last piece of the story is that in the twister space, what the results that we get, which are automatically conserved, you can show that the Whiteman functions, rather than the time-ordered correlator, because these are real-time correlator, Whiteman functions are the correlator which which are conserved automatically. Okay, so what we are computing essentially are the Whiteman functions, and it's a simple proof to show that given the time-ordered correlator, what identity can be produced by the fact that the Whiteman functions, this is a time-ordered correlator, these are the Whiteman functions, and just these theta functions are good enough to produce you all the water identities. Okay. So I'll skip to the area space. In the area space, then all our target is to, now again the same question, we want to go to the 4-point function, but let's try to solve the simpler question, which is the area space thing. We are just going to compute in the area space the Whiteman function, and there is a work by Steinman which actually tells us in the flat space how to do it. Also there are parallel works, more path integral approach to computing Whiteman functions by Loga and Skenderis, Van Valris, Loga, Godwin, and other collaborators. Here we are not going to follow this path integral approach. We are just going to follow the algebraic approach, and it's a simple calculation to show that if I try to now calculate the 4-point function, in the 4-point Whiteman function, it turns out that actually it takes a very, very complicated form in the area space. If I work in some special kinematics, just one second, let me, if I work in some special kinematics, it turns out that the 4-point function of scalar operator in the dual CFT takes a very, very interesting and simple form. These are all written in the twister space. Okay, this is a 4-point function answer in the twister space. One can also calculate the 4 gluon amplitude, MHV kind of amplitude. They turn out to be simple sine function with some expression over here, and these sine functions are precisely the flat space amplitude that people computed in the 4D scattering amplitude. You can calculate the 4 graviton amplitude, and then they take this following form, and if you try to use something called Swinger parameterization, which is just simply the delta function and 1 over x written using the Swinger parameterization, you can show that the 4 gluon and the 4 graviton amplitude become just the square of each other. So this is the double copy. In some sense, this is like one of the cleanest double copy that we found in the area space. Just last part is that we have computed these things in very special kinematics where things become the 4-point function etc. factorizes. You might argue that it's a special kinematic result, but we have also shown that using this special kinematic result, you can analytically continue to the any general kinematics that you want. Okay, So these are as good result as possible for any general kinematics. Of course, the exact details will be a little different. The connection to the CFT conformal block, look at Dhruva's poster. He will explain it very clearly. So the future direction would be to compute higher point function. Since we have been able to do it in the twistor space, the Park-Taylor amplitude of BCFW recursion kind of relation seems accessible now. And of course, the main question that we have been discussing is the CFT bootstrap program. Here in the momentum space, there is no analog of the OPE, but using in the twistor space, what we believe that there would emerge some other geometric picture to be, this crossing symmetry thing might be related to some kind of a geometric picture, hopefully, and then we will be able to implement this bootstrap program. Okay, thank you.
A few quick questions.
I have a question about the double copy. The relation you wrote with the correlators.
Yeah.
Not this one. This is the usual thing, right? Way back with the CFT correlators. On the right-hand side, what do you have?
Yeah, sorry.
On the right-hand side?
Yeah. These are also 3-point functions.
In the CFT or ADS?
CFT. These are all CFT. Here, these are all CFT.
Then why do you call it a double copy relation? Because typically they relate a gauge theory object.
I'm talking about the
square to a gravitational object.
This is like a structure. One structure, a spinning structure, another spinning structure. They multiply. They give. It's not yet like a theory to theory double copy in that way. It's just I'm talking about the spin structure. That is a nice double copy thing. So just to clarify, this part is just the purely ADS CFT. The ADS part, the double copy in the ADS part I showed, is just a stepping stone towards doing it in the CFT. Okay.
Okay. Yeah, thank you.
I have one question. In a paper by Pellegrinos, Costa, and others, where they used the embedding formalism, it's pretty much known that what are the all possible terms that can appear in a 4-point function of spinning correlators. So, but the structure constants, they are undetermined because only the spin structure is known. So I need to understand that when you are using this twistor space, are you trying to get all those possible types of terms that can appear in the 4-point function?
The first thing is to find out the structure, and the coefficients will be dependent on the theory. So right now you just have to build the formalism first, and then you might want to apply to some particular theory. That is later. But all I just wanted to say that even the first step does not exist, like in the Poisson space, as you pointed out.
Okay.
I just wanted to ask a question about this last line. So if one wants to compute conformal blocks, one can write them as products of 3-point function, right?
Yeah.
Operator. You use this sort of a relation to compute conformal blocks by now reducing the of 3-point functions to some other 3-point function and so on?
For the conformal block, what happens is that in the Poisson space, those are like a product, and then there is an integration. In the momentum space, they are literally like multiplication kind of thing. Here, this is like a P1, P2, P3. Here again, P1, P2, P3. But in the conformal block, I would ideally like to have P1, P2, P3. Again, P1, P2, P1 plus P2, P1 plus P2, and then P3 and P4. So it will be a little different. This will not be just returnable in terms of a 3-point function, conformal block thing. This is identical momenta. So in the Poisson space, this will be like a convolution kind of thing. But there is something interesting that I did not get time to show. But in the Whiteman function that I talked about, or the ADS computations, they factorize and they precisely go over to the CFT conformal blocks. CFT Whiteman conformal blocks. In the same language you asked.
So you said that
in momentum space, even the 4-point structure is not known, but like in position space, it is known. So what goes wrong with just taking the Fourier transform of that?
Yeah. So, you would imagine that you can just do the Fourier transform. So, if you try to do it for the 3-point function, say like, as you can imagine, there are 3 integrations, complicated D4P, D4P, D4P kind of integration. It's not easy to do, like at least, going to the 4-point function, it will be also very difficult. You might get a formal expression in terms of Fourier transform, but you cannot do something more with that.
Okay, so let's thank Sachin once again. And before the next talk, this announcement about about those who are presenting posters. They are requested to go to the 3rd floor of the library building where we are having lunch and dinner, and please set up your posters there. The arrangements have been done. No, after the talk, before lunch. Yeah. Okay, so the next talk is by Amos Yaron, and he'll give us a platter of fish.
Check your slides if they're full screen.
No, it's okay. I'll just use the keyboard. Is this working? Is this working? Is this working? Yeah, okay. I'll just use the keyboard, it's okay. So thank you for, I'd like to thank the organizers for inviting me. It's always a pleasure to be here in India. You're probably wondering about this title. So this is a children's book that my kids really liked. And I use this title in place of my actual title, which is Steady States in Conformal Field Theories. And the relation is that you'll see that we need these diagrams, which we call fish diagrams, in order to characterize the steady states. So this is work that I've been doing on and off for some time, and I'm going to show you some new preliminary results. And if I have time, I'll also say what else can be done with this further. So the problem we're interested in is the following. We have 2 semi-infinite heat baths, and at some time we connect them. And the question we want to answer is what's going to happen at late times. So if we allow them to interact, the system is going to thermalize, and we're going to get some intermediate regime, which is in thermal equilibrium. And the question is, what is that intermediate steady state going to look like? So this, like I said, this has been studied for some time. There are many works. I'm not going to be able to talk about everything that's been done. I'm going to highlight sort of what we did. The essential problem is to solve energy momentum conservation given some initial discontinuity. So if we're solving a differential equation and the initial conditions are continuous, we know what we're doing. But if there's an initial discontinuity, we have to be a little more careful about how we solve the problem. So this is what we want to solve. And one sort of first guess that you might use if you want to solve a problem like this is to say, well, the configuration is just going to, this discontinuity is just going to move along the spatial coordinate with some velocity s. We lift this a little bit. Okay, so the only dependence on the space and time coordinates is through the step function, and if you can't see the animation, but if you can imagine that if you evolve this in time, this discontinuity is just going to move. And to check whether this is a viable solution, we can just take this equation, plug it in here, and see that we get 0. So the only dependence on x and t are through the step function. So if we take a derivative, we'll get a delta function. And so in order for the conservation equation to be satisfied, what we need is that the coefficient in front of the delta function will vanish. And so we get a set of equations which look like this. So we know what the stress tensor is on the right and the left side. We know all its components on the right and the left side. And S is the velocity of this shock wave. And you see we have two equations for one variable. So this is overdetermined. Generically, we won't be able to find a solution to this set of equations. So this single moving shock wave can't be a solution to this equations unless we tune the stress tensor on the left and right heat paths. This one? Yes.
That will already assume some kind of continuity. Applying Noether theorem itself will be a problem, right? Noether theorem we explicitly assume field vectors with some continuity problem. So how do you derive that equation?
Well, so physically, I would say that whether you have here a step function or something very like a step function is not going to change much. I can always take the limit that I'm getting close to a step function. I think that if I put background fields to derive this, I would still get conservation. So this equation, as an equation, is valid as long as I treat this kind of solution in a weak sense. So I need to really think of this as a distribution that I integrate.
The solution part I understand, but the derivation of the conservation itself using Noether's theorem, that will require some continuity on the functions that I'm differentiating. So T mu is.
Yeah, I mean, I'm not sure I really need it to be continuous, the solutions, in order to, the stress tensor to be to derive Noether's theorem. But beyond that, I would just say I can, physically, I want to consider a configuration. There's no leakage of energy anywhere. So this has to be satisfied if I actually run this. So you might, so I'm not entirely sure what you'll get if you try to derive this as Noether's theorem and assuming you have this. I think in the way you want to derive it.
I was wondering what is the meaning of a conservation equation in that.
But this is, you take two heat paths and you put them together. There's no leakage of energy and you let the system go. Physically, it's never going to be like a real discontinuity, but this should be a good enough approximation. Okay. So this isn't going to be a good solution to the equations, not even in the weak sense. So we'll go to the next thing we can come up with, which is to say that maybe we can have two shock waves, one moving to the left and the other moving to the right, and together we can get something that looks like a solution. Okay, so we're assuming that the energy density is going to be fixed on the left and fixed on the right, and we're going to get some intermediate regime between the two shock waves where it has some value that we don't know yet. And the same thing for the energy flux. And now we want to solve this. So let's first solve for the shock wave that's moving to the left. So I'm focusing only on the left, and we get the same set of equations that we had before. They look like this. But now there are parameters that are not fixed: the value of the energy density at the center, the value of the energy flux at the center. This is going to be determined by the other two by some constitutive relations. And we have this parameter S, which tells us what the velocity of the shock wave is. So we have 3 variables and 2 equations. So we have a 1-parameter family of solutions. Okay, so fix S, and then we can fix the energy density in the central region and the energy flux in the central region. So the solution is a curve in parameter space for the energy density and energy flux in the central region. Let me draw it for you. And so we get this fish diagram. So this axis here is the value of the energy flux in the central region. The horizontal axis is the energy density in the central region. Here, this particular plot is for a configuration where the energy density on the left is some E0, and the energy flux on the left is 0. So each point here corresponds to a different value of the shock wave. So here, for example, we see that a solution with an energy density of 1.5 in the central region and an energy flux of, I don't know, 0.3 in the central region is a valid solution. These black lines here correspond to the end of parameter space. Causality enforces that enforces this inequality, so nothing can live outside this edge of parameter space. And now we're going to get different types of fish diagrams for different types of for different values of the energy density and energy flux in the left region. Okay, so as we change the value of the energy flux, the fishes get a little skewed. What we could always do is just use Lorentz invariance to say that we're moving together with the left heat path. So we can always just choose our Lorentz frame so that the energy flux in the left heat path is 0, and this is what we get for the general result for the shock wave on the left. Where is what? The what? The curves. Oh, the curves. The curves are. I'll show this in the next slide. So the curves are the solution. So here you're fixing everything with an L, and so you have what these equations are telling you, or what is S? What is the central value of the 0, 0 component of the energy momentum tensor, and what the central value of the 0, 1 of the energy flux is. So this is what you want to solve for. X, the pressure term is going to be determined by the other two via constitutive relations. So you have really three parameters that this equation has to fix. One is the shock speed, and one is the value of the energy density in the central region, and one is the value of the energy flux in the central region. So you have 3 unknowns and 2 equations. So you have a 1-parameter family of solutions, and that's what the curve represents. Sorry? There is no real boundary here.
No. In the fish diagram.
Yes.
The straight lines are where the things end.
They don't. The tail goes off to infinity.
Or they start.
The equations of?
What is S? How does the S change in the fish diagram? That's what I was asking. Not here, but in the.
Yeah, in the fish diagram. Yeah, it goes from -1 to 1. You're asking what is its exact, where is its value?
Yeah, so, okay, it starts off from -1 here.
Well, starts or ends, I mean, it goes off to infinity here and here. The diagram goes all the way to infinity.
So the shock speed goes to infinity?
No, it's 1. The diagram is in the energy density and energy flux plane. And the shock speed is only between -1 and 1.
Okay.
So it sort of stretches out as you take S to 1. Okay. So now we can do the same thing for the right shock. So for the right, the equations look exactly the same, except that we're swapping R and C because we're going from the central region to the right region. So we get, again, a fish diagram. So here is the left shock, and here is an example for a right moving, the right side of the shock wave. Here I chose parameters so that the energy density on the right side is half the energy density on the left side, and there's no flux on both. So again, each point here corresponds to a different solution for the left shock. Each point here corresponds to a different solution for the right shock. So this point here means that if we're right here, then the value of the energy density in the central region is 0.2 and 0.7, and same for here. So if we want to match the shocks so that we get a consistent solution, we have to look at where the red and blue fish intersect. So the intersections are the points where we get a legitimate energy density and energy flux in the central region. Okay, so in this way, these diagrams tell us how, we can of course do everything algebraically, but these diagrams tell us how the state in the central region can behave. And now, as we change the value for the right region, we keep the left region fixed because that's from Lorentz invariance, we can do that. We're going to get different types of solutions. And note that what we really need to know is where the waist of the red fish is. So this intersection of the red fish, once we know where it is, we're going to know how it's going to intersect the blue fish. Okay, so this is a nice story. Unfortunately, these shocks are all not always compatible with entropy production. And I don't have time to really show the computation, but you can ask, is entropy produced in these shock waves? And entropy is always produced by shock waves. And if you compute it, you'll see that in this part of the curve, we get positive entropy production. But in this part of the curve, we're going to get negative entropy production. And of course, that can't happen. So it means that these types, the upper part of this curve is not a legitimate solution to the equations of motion. And we need to look for some other solution which is more physical. So the next solution we look at is called a rarefaction wave. So you see if you set, so it's constant on the left, constant on the right, and then there's a region where it sort of opens up a little bit like a fan. At t equals 0, we still get this discontinuity, but now there's a very heuristic presentation of it, but it roughly looks like this. So we get some opening up of the interior region by this, what's called a rarefaction solution. And now we can say, okay, maybe in the regions where shocks aren't allowed, we can have a rarefaction type of behavior. So a single rarefaction solution is not a valid solution for the exact same reason that a single shock solution isn't a valid solution. It turns out that there just aren't enough degrees of freedom for it to solve the equations for generic left and right values of the heat paths. So we can just glue them together. Okay, so we do the same thing as before. We glue two together, and then we look at first the left region, and then the right region. And if I draw, and we find that if we look at this region only, there's again a one-parameter family of solutions, and it actually looks also like a fish. You might think that what I drew here is exactly what I had before, just dashed, but it's not. It looks very similar, but it's not the same thing. Especially if you look at the extremal regions of the curves, you see it's a different curve. It's very similar, but it's not the same thing. So this diagram represents valid values for the central region for a rarefaction wave, and this is what we've seen before. This is a shock wave. So for the shock wave, we said that the upper part of the fish diagram has negative entropy production. Bottom part has positive entropy production. For rarefaction waves, in the absence of viscosity, there's no entropy production. And so if we ask, what do we expect to happen in a realistic situation? Well, we expect to have the lower part of the shock wave dominating in this region, and the upper part of the rarefaction wave dominating in the upper region. Okay, so this is what the left part of the shock or rarefaction should look like. And now we could do the same thing for the right moving part, and what we get is something like this. Okay, so now to understand what's going on, if our right moving heat path is located right here, then we're going to get either a shock rarefaction or a rarefaction shock solution. And as we move around the values for the right heat path, we're going to get, in this case, a rarefaction type of solution. So we could have a rarefaction moving to the left, a shock to the right, and any of those four combinations. Now, since what's really important here is just once we know where the waste, where this intersection point of the red fish is, once we know that, we know what sort of intersections we get. So we can draw a phase diagram for the type of solutions that we'll have. Okay, so this is the phase diagram of the type of behavior that we can expect when we put these two heat paths together. Whenever the value of the right, so we fix our left heat path by moving together with it, and whenever the value of the right heat path is in this region, we're going to get a rarefaction shock solution. Whenever it's in this region, we're going to get a rarefaction solution, and so on. So this is going to tell us what type of solution we're going to get, and to actually compute what the steady state looks like, we look at the intersection points of the red fish and the blue fish. So if I were an experimentalist, I could now go to the lab and check whether this whole story is true, and I'm not, so I can't. But the next best thing I can do is just test this with holography. So in holography, we know that if we want to describe a thermal state, a configuration where the energy density is constant, then this is going to be dual to a black hole. So this is my picture of an ADS black brane. We have the radial coordinate, this is the boundary, and this is supposed to represent an event horizon. And what we want to do is start with an initial configuration where the energy density is discontinuous. So what we can do is we can just take two of these black hole solutions at different temperatures and glue them together at t equals 0. Okay, so in general, this thing is not going to stay as it is if we evolve it forward in time. 10. This configuration is not going to stay the same way it is as we evolve it forward in time. The Einstein equations are going to tell us that this can't be a solution for all times. So we need to solve. We can't solve this analytically. There are too many. This depends on both the x direction and the radial direction and the time direction. So we couldn't solve this analytically, but we could solve it numerically. So we just put it on the computer. Of course, on the computer, there's not going to be a sharp discontinuity here, but a smooth one. But that's what we did. And what we found is that the behavior of this black brane is going to be very similar to the behavior of these shock or rarefaction waves. So the black brane evolves in such a way that a steady state is generated in the middle region. And now we can use the duality to map the solution to the energy density and energy flux. Okay, and this is what we get. So I'll start with this graph here. This axis is the energy density, and this is the spatial coordinate, and the graph is moving forward in time. The plot. So initially, we have this almost discontinuity, and then as we move forward in time, we get this intermediate steady state. And in this particular case, we have a shock wave moving to the right and a rarefaction wave moving to the left. If you look at this very carefully, you'll see that the profile of the rarefaction wave is changing with time, even though it's a little slow. And the profile of the shock wave eventually stabilizes and remains constant. So here, the distinction between rarefaction and shock is hard to see because we didn't start with a sharp profile, but with something smooth. But still, you can numerically you can test whether this is going to stabilize and, or this, and see that this is really a rarefaction and this is a shock. So this solution corresponds to a rarefaction shock solution, and the dashed line is the prediction that we have by looking at the intersections of the red and blue fish. And this is very similar. Here we're looking at the energy flux. So this is a configuration where at t equals 0, the energy flux is 0, and the left and right heat path have 0 energy flux. And you can see that when the steady state is generated, there's energy flux. There's a non-zero energy flux in the central region. Yeah. Say it again.
What is happening at the level of horizon in the bulk? Because you are starting with, in a sense, some sort of the discontinuous horizon.
Yeah, so I mean, this is really a coordinate-dependent statement. When we run the numerics, what we really do is we use a coordinate system where the horizon is at a fixed value of the radial coordinate. So to say that the horizon is moving or not is a coordinate-dependent statement. But if you use, say, in some sense, natural coordinates, then yeah, you'll see that the apparent horizon is really changing its location in this kind of way. But this is a coordinate-dependent statement. We didn't really try to find the event horizon. That's more complicated because we also need to know exactly what the end result would look like. And we didn't try to push that backwards.
But I mean, earlier you showed 4 regions, RR, RS, and all, right? Do they have a definite meaning from the bulk perspective?
Well, from the bulk perspective, it just means that, so these 4 regions they tell you, given the values for the right heat path, what is the configuration going to look like. So in the black hole, the evolution is going to be different depending on what you do with your right heat path. And this, I think, is it's related to entropy production. So in the black hole, you cannot produce negative entropy. The Einstein equations won't allow it. So it's all encoded there in the entropy of the black hole.
Hi, I have a question. So can we think it as a Oppenheimer-Snyder collapse in some radial sense?
No, I don't. Well,
because the density is changing there because it's self-gravitating. But apart from that, can you think it as?
Well, maybe in some sense. I mean, our initial configuration is such that there's a horizon already at t equals 0.
Okay.
So there's a horizon at all. We start with a black hole. It's just not uniform.
I see.
So maybe there's some sense in which you can do that, but a priori it doesn't look like it.
Okay. Thanks.
5. Okay. Yeah. So I'm about done. So this is my summary slide. There's a little title summary up top. So this is really what I wanted to focus on. I have five minutes. So I have so this is our current main result. But I think there's a lot of things that you can do with this, which would be interesting. Let me say a few words about what we plan to do next. So if we're in this region, we're going to get a rarefaction and shock solution. Here we're going to get a 2-shock solution. You can ask, what will happen when we're exactly on this curve? So when we're exactly on this curve, this is this very special point where a single shock solution is allowed. Okay, so on this point, we can have a single shock solution. At this point, we have a single rarefaction solution. So those are non-generic points. Okay, so in this case, if we're really right here, we should get a single shock solution, just something moving to the right or to the left. Now, if we have a single shock solution, we can, instead of saying that we're going to move together with a left heat path, we can say, let's just move together with the shock. Okay, so we're in the reference frame of the shock solution. And from that point of view, there's nothing moving, right? We're sitting together with the shock. There's some energy flux here and energy flux there, and the shock is just standing still. So this is a stationary shock. And that means that we should be able to see a stationary black hole configuration. Okay, so this is an unusual configuration. We have a black hole. It's not going to be homogeneous and isotropic. It's going to have this discontinuity or something close to it. It's going to be, the discontinuity is going to be smoothed out by viscosity. So we get this funny kind of black hole solution where there should be some sort of entropy production here, but it's still time independent. I'm guessing that there's probably some entropy leaking off to infinity, which is going to save this type of configuration. Okay, so this is, I think, an unusual type of black hole solution that has to exist if this whole story is true. Another thing, another viewpoint on this, which is interesting, has to do with some exact results for this in a 2D CFT. So in a 2D CFT, because the stress tensor decomposes into holomorphic and anti-holomorphic parts, you essentially always get a shock wave solution. There's no rarefaction wave solution. And you can compute what the steady state is going to look like, and you get this formula for the steady state. So what you're seeing here, T is the temperature of the left and right heat paths, V is the velocity of the right heat paths, C's are the central charges of the CFT. I wrote here the general solution, so we can also have some U1 symmetry, and mu left and mu right are the chemical potentials associated with this U1 symmetry, and K is the, are the levels of the U1 current algebra that are associated with the symmetry. Okay, so now imagine that I set the velocity to 0 and I don't have charges. You see that the left heat path, the energy flux multiplies the left temperature by C minus and the right temperature by C plus. So that means that if C plus is going to be much, much bigger than C minus, we can get that the energy flux is in the wrong direction. Okay, it's going to, because of the gravitational anomaly, it looks like it's going to flow in the direction, in an unexpected direction. Okay, so this is, if we could do an experiment, this would be a signature of the gravitational anomaly. And so in 4 dimensions, we don't have a gravitational anomaly, but we have a mixed gauge gravitational anomaly. And usually that reduces to a gravitational anomaly if we reduce to 2 dimensions and have a magnetic flux piercing that dimension. So hopefully, with a mixed anomaly, we should see a similar effect if we add a magnetic field. And this, again, is something that should be hopefully measurable. And if we can measure it, it would be the first, I think, ever place where one can actually test the existence of the mixed anomaly. So this is maybe a little hopeful, but this is where we're heading to. So I'll stop here, and thank you.
Hello. Yeah. So do you have a clear idea of what happens in the bulk? So you have a horizon and then you have a discontinuity. When you have a rarefaction, does it mean that the discontinuity is there in the horizon, but the gravitational wave which come out smoothen it out when you calculate the stress tensor in the boundary? Or
so the challenge, I think, is to, it's related to the previous question. How do you, it really depends on the parametrization. So you have to ask the question in a way which is, so first of all, I don't know how to answer this, but you'd first have to ask the question in a way which is parametrization independent. So maybe you're asking if there's, you know, a discontinuity that somehow smooths from the boundary to the horizon or something like that.
Maybe let me rephrase the question. Let's say if you look at the gravitational waves in the bulk, which will happen in the higher dimensional examples, right? When you have the metric will have a wave which comes out, right?
Well, the boundary, the value of the boundary metric is fixed.
Yes. Yeah, but the normalizable mode will change. That's the stress tensor.
Yes.
And that's just a gravitational wave coming out. Because
okay, I can
use a time-dependent solution of Einstein equation. Okay. Fine. So now, is it localized or is it? does it spread out?
I don't know. I don't know. I don't
Okay.
know.
Yeah.
Yeah, maybe this sort of like is also in line of this question, but in the case where you only have shocks, it seems like you could potentially analytically solve this by some cutting and gluing procedure in the bulk, where you have to just, you know, planar black holes that you paste together along some like null defect.
Yeah, so what I maybe, I was a little vague about this. If you have a fluid that has no viscosity, then the shocks are just going to, they're really going to be discontinuous shocks that just move. If you have viscosity, the shocks are going to be smoothed out by viscosity. So you could do the analysis, because everything far from the shocks doesn't really change, you can do, the analysis you do can be in an inviscid kind of setup. So you get the right steady state and the right values at the heat baths, but the actual profile of the shock is something that you can't solve once you have viscosity. Now in gravity, because in gravity you have some inherent viscosity, then you're not going to, even if you start off with an initial shock, gravity is going to smooth it out.
Hello, my question is about your fish diagram, in which the upper portion contributed as a negative entropy and you threw it away, whereas the lower portion had the positive entropy.
Yeah.
But like, why would you do that? I mean, as a whole, you can say that the lower portion must have dominated so that the overall entropy is positive. For example, even in the thermodynamic systems, when the hotter part loses energy and the colder part gains energy, so the entropy of the colder part is positive and larger than the coming from here. And we talk about the overall entropy, which is positive. So why did you throw away the top part?
So I use the notion of an entropy current, of a local entropy production. So in hydrodynamics, we assume that there exists a local version of the second law, which says that locally you have the entropy production plus the net flux that's leaving has to be non-negative. So instead of a conservation law like you'd get with charge, you get some current whose divergence has to be positive locally, and we do that because sort of causality enters into this whole description. So if for some reason you don't have a local version of the second law, but you do have a global version of the second law, it means that you play with something here and over there, all of a sudden the entropy is going to compensate for it. So we don't think that would be likely. So I'm using a local version of the second law which prohibits that.
Nice. Thanks. And another question is like, what allows you to model this heat flow in terms of a CFT? Because the analysis you did, it was independent of the size of the system. Is that why?
So I think we could do other things with non-CFTs. For the CFT, what was helpful here was the equation of state. The equation of state that relates the XX component to the TT and TX components of the stress tensor. That was very easy to do.
And it was traceless. That's why.
And yeah, because it's traceless. But I think you can do similar things. We're working on this. I think you can do similar things for non-conformal theory. I don't know how far you can go with some generic equation of state.
Thanks.
Hi. So this question is about the boundary part, not the bulk. Can you describe this in terms of this reaction diffusion equation and the wave solution of that, effective description of that? Motion of these shocks or this front that separates.
What do you mean?
It's a diffusion equation plus a nonlinear term which have.
Yeah, so here, right, so if you have diffusion, the behavior is going to be different from what I've shown. So the diffusive behavior is going to look different. If you have, for example, if you take two non-relativistic fluids at the same temperature, but at different densities, then you're going to get diffusive behavior, which is different from what I've shown. So you really need some sort of propagating non-diffusive modes to get this type of shockwave behavior.
We can talk about.
Okay, so if there are no more questions, let's thank Amos once again. And yes, lunchtime, and there'll be poster sessions in the same place as the hall where we are having lunch. Let's we are running a little late, so let's reconvene at 3:15.
रुको रुको अभी इसी पे छोड़ो, अभी ठीक लग रहा है, 1 मिनट। तो मैं बोल रहा हूँ कि हम जब सेट, हाँ प्रॉपर कट रहा है, थोड़ा कट रहा है नहीं अभी, आई थिंक इट इज, थोड़ा सा कम कर लेते हैं। हाँ 220 हम कर लो, हम सबका चेक किए थे। तो कहाँ कैसे करते हैं वो? ये खाली कंट्रोल कंट्रोल जब आप ये ना करेंगे, कंट्रोल प्रेस करिए वैसे। ओह अच्छा अच्छा, यहाँ पे वो आ जाएगा, देन इज इट ओके? हाँ आ रहा है, सब आ रहा है, ठीक। लेट अस गो, उनको कॉलर माइक बस पकड़ा दो।
Okay, welcome to the second session of the first day. So we'll start with Mrityunjay Verma from IIT Indore. He'll talk about flat holography and momentum space.
So either you will have to hold it and
Okay, I can just keep it. Should I start? Yes. Okay. So let me begin by thanking the organizers for giving me this opportunity to talk about this work here. So, so this work is done in collaboration with Raffaele Marotta, who is in INFN Napoli, Arvind Shekhar, who is in Southampton, and Vijay, who is in Edinburgh. So some work with Raffaele and Arvind appeared today, and some work with Arvind and Vijay will appear in some time. So, so let me begin with some introduction and motivation. So we know that this black hole areala indicates that holography should be an integral feature of any quantum theory of gravity. And using the insights from string theory, this has been quite successfully incorporated in anti-de Sitter spacetime. However, in spacetimes with zero or positive cosmological constants, understanding holography has been quite elusive so far. But these are like important examples, I mean these zero and positive cosmological constant cases, and especially in the asymptotically flat spacetime, the holography is expected to be especially rich. For example, so one motivation was given by Ashok last summer, and by looking at the dependence of moduli of the boundary field and the bulk field, he argued that holography in flat spacetime will have like much better structure, or it will be more complicated than the ADS. For example, Ashok argued that if you consider flat spacetime, then you may consider some large interior regions which resemble vacua, such as this type 2b on ADS 5 times S5, or ADS 3 times S3 times T4, or even M theory on S4 times ADS 7. And so this means that holographic dwell in the asymptotically flat spacetime should know about all these possibilities. So this makes flat holography quite a rich like subject. But at present, unfortunately, we do not have any satisfactory approach for constructing such a UV complete holographic theory. So in the absence of UV theory, we can see what we can do in the IR. And in fact, some progresses have been made in the low energy sector, this IR sector of the bulk. So for the massless bulk field, the expected natural location. So you have massless field, it reaches like null infinity. So the expected natural location of the dual data is the null infinity of the asymptotically flat spacetimes. And the asymptotic symmetry group of asymptotically flat spacetime is an infinite dimensional extension of the Poincare group, which is well known to be this BMS group. And building on this fact, there are two closely related approaches for analyzing the physics at the null boundary of such spacetimes. So in the first approach, known as celestial approach, one makes connection between the bulk scattering amplitudes and the correlators on what is called celestial sphere at infinity. And on the other hand, in the second approach, which is known as Carolian approach, one relates the bulk dynamics to a Carolian conformal field theory, which lives on the null infinity, the full null infinity, Scri plus and Scri minus. And both of these approaches are complementary ways to analyze the theory at null infinity in asymptotically flat spacetimes and have been argued to be equivalent. Here I shall focus on the Carolian conformal field theory. So these are the theories defined on the null hypersurfaces. And one way to study these theories is to consider Inonu-Wigner contraction of conformal algebra, which is SO2, D. If we send the speed of light to 0, then so consider the CFT generators D, L mu, nu, P mu, and K mu, and break these indices say mu into the spatial part, say Ij,
and it's a zeroth component. Then this CFT generator break into like this way, and if we send C going to 0 in this CFT, so left hand side is the CFT algebra broken written in terms of these broken this DLIJ, BI, P, H and KIK. So if you send speed of light to 0 in this, you get this algebra, and this is called Carolean algebra, Carolean conformal algebra. So these theories are defined on the null hypersurfaces, and hence they have a degenerate metric, and they lack the standard time evolution. So due to this, the properties of these Carolean theories are quite different from the standard QFTs we are used to. So in particular, the standard analytic properties of Poincare invariant QFTs do not directly apply to these theories. On the other hand, the bulk theories have well-defined analytic properties. So if these have to have like some sort of like dual feature, then for this duality to work, we need to know how the bulk analytic properties translate into boundary analytic properties. And in position space, so our experience with quantum field theories, traditional quantum field theories tell us that analytic properties are not that manifest, not quite manifest in position space. Momentum space is like much better language for studying the analytic properties. So for example, the physical properties such as locality, causality, unitarity, they can be translated into some nice analytic behavior of the momentum space correlator. So for example, locality translates into some kind of polynomial boundedness, and causality translates into behavior under some analytic continuation, and unitarity translates into some cutting rules of the momentum space amplitude. So this hints that for Carolean conformal theories on the null boundaries, we can hope to get some insight about the analytic properties by analyzing them in the momentum space. Moreover, the connection between asymptotic symmetries, soft theorem, memory effects, flat spaces, matrices are also most naturally expressed in the momentum space. So here I shall discuss how to systematically study these Carolean conformal theories in momentum space in arbitrary dimension, and I shall be making use of only symmetries, and we shall see what we can say about these theories just using the like Carolean conformal symmetries. So I should just comment one thing, that usually, I mean, still it is not clear whether these two approaches, this Carolean and celestial, they define an independent they have an independent description at infinity. I mean, it seems, I mean, okay, one could just argue that these are just some different way of like expressing the bulk physics, but okay, it's still ongoing debate. So one can just take this analysis as studying Carolean conformal field theories, irrespective of whether they are dual or not, of this flat space, asymptotically flat space times. So in that spirit, one can just work. So this is the brief outline of my talk. So I will start with some review of what is known about correlators of these theories in position space. Then I will show how to study them in momentum space, and then I will discuss CFT algebra, as I mentioned, it is this Carolean conformal algebra can be obtained from CFT algebra by Inonu-Wigner contraction. So we can also ask if we take the this contraction for the CFT correlator, what we get. So I will discuss that also in momentum space. Okay. So from the algebra, one can write down, so since I shall be focusing on the symmetry aspect of the theory, so I will consider what we can learn about these Carolean conformal theory just using the word identities. So word identities encode information about all the symmetries. So from the algebra, one can write down these word identities. So this 2-point function in these theories take this form. So we have two terms. So first term is proportional to, so here, okay. So here I should say, so this, I'm denoting this coordinates by u and x. So x is the spatial direction, and u can be thought of as the null direction. So this is the 2-point function in this Carolean conformal field theories. And so we have, so unlike standard conformal field theories, where you have only one term. So if we were considering only, say, standard conformal field theories, we will have like this first term, where this both the conformal dimension must be same. In the Carolean theories, the symmetries allow these two different structures. So the second structure is it's a local term, and it only depends on this null directions use. And for the second term, these conformal dimensions need not be same. On the other hand, the 3-point function can have 5 different structures. So again, in the if we were considering standard conformal field theories, there will be only one term. But here we have these symmetries allow 5 different structures. So for example, first term is ultralocal in the spatial directions, and this function g1 depends on these coordinates u1, u2, u3. Then we have g2, which depends on only these spatial directions, and then we have these mixed branches, which depend on both u and x. And word identities restrict the form of these functions. So for example, this first branch g1, it's not completely fixed by word identities. So what happens is this dilatation word identity implies that this is an homogeneous function of degree, this degree 2d minus 1 minus the sum of this conformal dimension. So it takes this general form, and one can show that spatial conformal transformation is trivially satisfied for this branch. So this is the most general structure one can have for this branch. So this is a function of these ratios u1 2 by u2 3, and there is this prefactor. And an example of a function which is consistent with this is given by this. So this is the, if we were just imposing a scale invariance, this is what one would also get in the standard conformal field theories. So this is also true here, but it's of course only true for these u directions. Yes.
Any of the result, or that is not
relativist, yeah, so I will discuss that.
So let's say since you are going to discuss, let's say it is possible, then at the relativistic CFT at least 3-point function is totally fixed, but you're saying
no, so okay, so there is still a limitation on how much you can get from taking this limit. So I will discuss that limitation also.
Okay.
You cannot get everything from taking this relativistic limit. Okay. So, so this is just one example of a function allowed by these word identities. But in general, I mean, you have this arbitrary function. The constraint on G2, the second branch, it coincides with those of an Euclidean d-1 dimensional CFT. So we can immediately write down its form. It's the standard 3-point function d-1 dimensional Euclidean CFTs. And then other branches are also completely fixed. Up to, okay, so they involve both this u and h direction, and they take this form. Okay, so once we have this position space expression, we can ask what is the expression in the momentum space. And Sachin argued in the morning session that momentum space is useful for many purposes. So it's still a useful question to ask what is the momentum space expression for these correlators. Yes. Sorry, which one?
The branch which is not fixed, the u, I mean all the u's basically.
Yes.
So you must have one trivial, I mean, identity, right?
Trivial, yeah. You mean the special conformal this.
So is it just that k which is, I mean, which does not give you any extra stuff?
Yes. Yeah. Okay. So what you can show that this ki, once you impose this dilatation, this ki will also be satisfied for this branch.
Yeah, and one more thing, if you just go back one slide. No, so the word identities. What's the boost here? The boost, you have said that boost matrix equal to 0?
Sorry?
Have you set the boost matrix equal to 0? Because
By-
there is a, I mean, matrix that you need to have. If you're looking at this, you're just looking at the singlet sector in some sense. Are you just looking at the singlet sector?
No, okay, so I'm not understanding. Okay, this boost matrix. So
Yeah, there is a boost, I mean, matrix
I
in
mean,
some sense.
so this BI, what people call this BI as the, I guess, boost, I mean, in this direction. So you mean this?
Usually this is, I mean, this would have a sort of multiplet like structure there.
Okay.
So you're not looking at that.
Yeah,
at the
yeah,
moment.
yeah.
Okay,
Yes.
thanks.
So I mean, so here, I mean, you can see there are these two delta functions. So it's completely localized in this x direction. Sorry, can you speak louder?
So you have classified these terms according to the ultra locality?
No. Okay. So you can write down. Yeah. So one. Yeah. This is one way to think about it. But then you can. Okay. When I come to momentum space, there is a like a more natural. I will give a more natural answer.
Just a clarification, what is this small d? Is it total space-time dimension or just
Yeah.
space part?
I mean dimension in which this your Carolian
Full
theory-
space-time.
No, Carolian theory is living. So okay, I mean if you are putting it on like some surface, say some d-dimensional hypersurface, that is that dimension. But I mean if you are using this theory as embedded in like some high dimensional, then of course it will be different.
Yeah. So what will be like, for example, d equal to 1? Because
D equal to 1.
Yeah. In
Okay,
that
I'm
all
not
these
sure
other
I will-
terms vanish.
Yeah, so I'm not applying it for d equal to 1. Yeah, d equal to 2, yes, yeah, d equal to 2 I think should be fine. But still I think you will get it will be still a special case. Sorry?
When d is equal to 2, this x1, x2, x3 are two dimensional
Yeah, just,
vectors.
yeah.
So what does
so my
delta 1 of x1 to means?
Delta 1 of...
I mean, if you said d is equal to 2, you get a delta 1, I mean one-dimensional delta function.
Right.
That of x1 to means? So x is a vector, it's a two-dimensional
Yeah, x
vector.
will be a vector. So you are setting d equal to 2. So one direction is null direction and other is just...
No. I mean, the point is that I think what you have, well, I mean, if you put d is equal to 2, then this...
Yeah.
No, but then d is equal... No, that cannot be the...
Yeah.
Because the thing is that in, if you have a four-dimensional bulk, I mean, I don't know about what you mean by d. So this d is, so if the bulk is four-dimensional, then what is the d here?
So d will be 3.
D will be 3.
3, yes.
And d...
Yeah.
No, but then there are more general things actually. I mean, then you have not got everything. Because the thing is that suppose you have a four-dimensional bulk,
yes,
and then you can talk about, you can write Z1, I mean, in terms of the Z1 bar.
Okay, so okay, I'm working, okay, these x's can be translated into z bar, I guess.
Yeah, but then you can take a delta function, which is, say, delta of Z12.
Okay.
But Z bar is unconstrained, and similarly it's delta of Z13.
Yes. So okay.
But then Z bar is
I
still
think
unconstrained.
it can be translated into this language, and it will
Yeah,
be
but
one
then
of
this
these.
power of delta function is not right.
Okay.
So this is the, so you have missed one structure here. And that structure is very important because that's what the S matrix
Try to
gives
solve
you
the word
actually.
identities. Then
No, but that also solves the word identity.
Okay. So okay,
I mean, we have solved it.
okay, maybe I can discuss with you, but
So you miss that. So that structure is very important because that gives you the three-point function. I mean, well, I mean, you have to go to the split signature, but that's a very important structure.
Okay.
Okay. I mean, that is the because of the scatter. Its relation to the scattering.
Okay.
In the bulk. Yeah.
So.
No, I mean, if you say d is equal to 3, they have only delta 2, but in d is equal to 1, you have delta. I mean, in d if you have four-dimensional bulk, then the three-point function also has delta, not delta square.
And that structure is very important because of this fact that it is related to the scattering in the bulk. So
Okay,
that also solves the word identity.
Yeah, okay. I mean, my feeling is it will still be like translated into this, but okay, I can discuss with you. Yeah.
It's not matching.
Yeah, okay, okay, let's discuss later.
I just have a question.
Yes.
So again, this is the lens of this flat space holography. So you, only one of these terms probably corresponds to the flat space scattering amplitude, right? 3 point.
Yeah, I mean, some other will be probably related with the some maybe soft limit.
4, that term is not there actually. Because you can see if you take d is equal to 4 and look at the 3-point scattering amplitude, that should have a single power of delta. I mean, if you go back to your 3-point function,
yeah.
So if you say d is equal to 3, I mean, which corresponds to the 4-dimensional bulk,
yes.
Then you have delta square of x12.
This one.
But in 4-dimensional bulk, you have a structure where you have delta of z12, delta of z23, and z bar is unconstrained, and that's the 3-point function in the bulk.
Okay.
So that structure is not missing here actually. I mean,
I think it still needs to be translated and seen. I mean, what happens.
Yeah, but that also solves the word.
Yeah. Okay. So in this coordinate, I mean, okay, my claim is this is the most general structure one can write down. But okay, I mean, I will look into this. Yeah. Okay. So let me go ahead. So okay, anyway, so this direct Fourier transform of position space correlator is not always well defined. So for example, if we consider the Fourier transform of one of the branches, say this G3, then it will involve this integral. And this will be singular when you set delta 1 equal to d minus 1 by 2. Okay. So in this limit, if you expand around like this point, then one gets this log term. And this result shows that this regularized transform will acquire a log K1 contribution. So in general, the renormalization of the theory is required, and that adds some contact term to make the Fourier transform well defined. And even if the contact terms are not needed, the explicit Fourier transforms are usually quite involved. So it is often easier to obtain the correlator in the momentum space directly. And this is the approach I shall follow here. So we can introduce this momentum space correlator in the standard way, and one can write down the momentum space word identities, just analog of the position space one, but now in momentum space. And for the 2-point function, the general form of correlator takes now this form. So again, this due to translation invariance along this spatial direction, we have this overall momentum conservation or this delta function in spatial components of momenta, and along energy directions we have these two structures, delta of omega 1 plus omega 2 and delta of omega 1 delta omega 2. Again, in the first branch, delta 1 can be different from delta 2. For the 3-point function, using this H and Pi word identity, a general expression can be written in this way. So again, we have this 5 different structure, and they involve different this dependence in the energy direction. So they have different analytic behavior in the energy space. And these other word identities, they restrict the form of the function Fi. So again, for F1, one can show that it should be a homogeneous function of degree this delta 1 plus delta 2 plus delta 3 minus 2d. And the most general solution takes this form. The word identities for F2, they coincide with the constraint in again d minus 1 dimensional CFT, and 3-point function in standard Euclidean CFTs are known. They can be written down in terms of what is known as this triple K integral, where this capital K is the modified Bessel function of second kind, and this small k represents the magnitude of the momenta. So the second branch is proportional to a triple K integral. The other branches, so the general form of F3 takes this form. So there are 2 terms. One involves both magnitude of spatial momenta and this omega energy direction, and second term only depends on energy. And again, in this spatial case, delta 1 equal to d minus 1 by 2, which was problematic, for Fourier transform, one can show that these two solutions coincide and an additional solution emerges, which involves this log term. So this log solution is valid for arbitrary values of this delta 2 and delta 3, and it only requires delta 1 to be specific. And similarly for F4 and F5 also, one can write down the general solutions. So okay, so this was this analysis was just using the symmetries and word identities. And there is another approach which Sachin was asking. So can we take some relativistic limit of standard conformal field theories? So one approach to study this flat holography is by taking a flat limit of ADS CFT. So in the large radius limit, ADS locally resembles the flat space-time, and ADS correlator resemble the flat space S matrices. On the boundary side, the flat limit corresponds to Carolean limit, where we send the speed of light to 0. And in the momentum space, the flat limit of bulk ADS theories have been studied for massless as well as massive theories. In fact, one of the paper with Vijay, who is in the audience, will appear soon. And here I shall describe how this Carolean limit works for the boundary theories. How much time do I have? 5, okay. So now, since we were considering this Inonu-Wigner contraction of SO2, D, so we are considering in effect Lorentzian CFT. And in the Lorentzian CFT, the Whiteman and time-ordered correlators involve different I epsilon prescription. In the Carolean limit, the notion of time ordering disappears, and both type of correlator are expected to be proportional to each other. So here we shall show how this works in momentum space. And the limit in the position space for some branches have been considered before. Here I will show how you can get all the branches. So the 2-point Whiteman function in momentum space is given by this expression. And here I have taken out this factor of C outside. So if we want to send C to 0, so if suppose omega is not 0, then we can set this C to 0. But if omega is 0, then sending C to 0 gives you like a diverging result. So in the Carolean limit, we can write these two different kind of like terms. So we expect this kind of structure. So one proportional to this omega to the power 2 delta minus d, which just follows from setting C equal to 0 here. And the second branch, which is proportional to delta omega, with some power of this C to the power 1 upon C to the power alpha. And this function G can be fixed by integrating both sides over omega. And the two branches are then obtained by rescaling with different power of the speed of light. So you recover this two branches we had obtained earlier with these coefficients. On the other hand, the time order correlator is given by this expression. So in this case also we do expect these two different kind of behavior. So we can write down a similar expression here. And again, this function G tilde can be fixed by integrating both sides over omega. So due to I epsilon prescription, we can take care of this I epsilon prescription. We can consider this contour. And if we perform the integration over omega, we again get these two branches. Okay, this should be omega. So, and these are like proportional to, these prefactor differ, but it's the same behavior. So now to answer Sachin's question, so we can also see some limitation of this flat limit approach to study flat holography by this exercise. So we saw that Carolean conformal symmetries allow for a branch which has different this Carolean conformal dimension, which was delta 1 was different from delta 2. But in CFT 2-point function, we always have delta 1 equal to delta 2. So by taking a Carolean limit of this CFT correlator, so we this limit inherits this restriction and cannot access the most general Carolean structure allowed by this word identities. So this is a limitation. Again, maybe I will quickly rush. So we can do the same analysis for the 3-point function also. We can consider say the Whiteman 3-point function in CFT in momentum space is given by this expression. And so for example, let me just say how this branch emerges. So this branch with delta of omega1 plus omega2 plus omega3, we can directly take the limit c going to 0, since none of the external 0th component of the momenta vanish. And if we rescale to show that it agrees with the result we had, the expected result, if you rescale this k mu with this p1 k mu, then one can show that it takes this form, which was the expected behavior. Of course, f here is like a fixed function here, because one can explicitly evaluate it. Okay, these other branches are also like one can easily recover. For example, to recover this branch, which involves these 3 delta functions, we can integrate both sides over omega1 and omega2, and taking care of all this step theta function, etc. One can show that one gets this structure, and this one can show that this is equal to a triple K integral. So this is the structure we expect from general analysis also. This also you can do, the other branches one can also do in the similar manner. So the time ordered case can also be handled similarly. Here additional complication is you have this I epsilon prescription. You can choose appropriate contour and take the limit, and you get the same result. So, so this is the conclusion. So we have discussed the momentum space representation of the Carolean conformal field theories, and we systematically studied all the branches of 2 and 3 point function in momentum space in arbitrary dimension, making use of symmetries only. And we also considered the Carolean limit of 2 and 3 point function in momentum space and obtained all branches. Okay, I have not discussed the bulk and boundary connection in using this momentum space language. This is still a work in progress, so this will be discussed later. So thanks.
Questions?
Yeah, I have a couple of questions actually. So the first one is, you said there's no distinction between Whiteman functions and time-ordered correlators in this limit?
In the Carolean limit.
In the Carolean limit. Yeah. But if I take a general spinning Whiteman function, it's far more complicated.
General spinning?
A spinning Whiteman function.
Okay.
In addition to having total energy singularities, it also has singularities where some of the momenta magnitudes are flipped. And in general, it's quite a distinct expression in the time-ordered correlator, right? So do you still expect that all these things go through?
Okay, this analytic behavior is still not very clear in the Carolean limit. So how exactly it shows up, it's still, it needs to be investigated. So that, okay, I cannot comment anything about that.
And also just a related question. So in the relativistic CFT, let's say in 3 dimensions, you get solutions apart from the usual thing that's the Fourier transform of the position space counterpart. Things that are also inconsistent with the OPE, right? So for those things, if you take a Carolean limit, you'll also probably obtain some additional solutions to the Carolean Ward identities, right? So
additional solution, I'm not sure, but yeah. So you mean one needs to regularize the those expressions?
Yeah, but like these other solutions in the context of D-zeta, for instance, would be the alpha vacua correlation functions.
Okay,
right?
okay.
So do these have a sensible flat limit?
Okay, okay. I have not thought about this D-zeta connection. So
thank you. Just a comment.
Yes.
Saying when the bulk is 4 dimension,
yes,
I think this the thing that you are defining is not very useful.
Which one?
P space.
Omega space, you mean?
Just Fourier transformation.
Yeah, okay.
Because of the I mean, you have to basically treat the holomorphic factorization. I mean, otherwise we would have.
So you are thinking from more this celestial approach, right?
I mean, there is no celestiality. It is just some word identities and
yeah.
So the thing is that the thing I said, I mean, in 4 dimension, if the bulk is 4 dimensional, then the most interesting part of the 3-point function is the one where you have one dimensional delta function, which tells you that the holomorphic part is just there is no anti-holomorphic, only trivial.
Yeah. So I mean, of course, we do have this. I mean, terms with 1 deltas, but.
But those are the most important terms in 4 when the bulk is 4 dimensional. Most important in the sense that I mean.
You mean this kind of.
They're all, I don't know, I mean, if bulk is 4, then your D is 3, right?
Yes.
So you don't have any 1-dimensional delta function here. These are all 2-dimensional delta functions, right?
Yeah, delta 2. Okay.
So you don't have any one-dimensional delta function here. So if you go to 4 dimension, then you have more solutions to these.
They will localized spatial momentum direction. Is that what you mean?
Well, I mean, these are actually, this is how, well, I mean, 3-point function, I mean, it is the S matrix of like 3 massless particles, which will not exist unless you go to the split signature, which you can do, and there you get one delta function. Say you have z bar, you get say delta of some z bar, and then z is unconstrained. Okay, so for those kinds of things, you will get one-dimensional delta function.
Okay, I will discuss with this.
Yeah, but that you have missed.
But I mean, if you like just analyze.
But those will not be there in higher dimension. So what you are doing is actually true exactly in higher dimension, not in 4-dimensional bulk.
Okay, I mean.
No, sorry, Shamik. For d equal if the bulk is 4-dimensional, isn't his d minus 1 equal to 2?
So d is saying d is 3.
No, I think his d is 2, right? Because you have a delta of d minus 1 of x12.
I mean, that's what I asked initially.
Yeah, so,
what is your d?
So 4-dimensional bulk means your Carolean theory is 3-dimensional.
3-dimensional. But you had a delta function for x12.
Yes.
And for the 2-point function.
But the point is that x12, x is a vector.
Yeah, x is a vector.
So delta of x12, I mean, what do you exactly mean by that?
So he had for his 2-point function, he had delta.
No, not 2-point function. Go to the 3-point function.
Yeah. But first at the 2-point function level.
No. The 2-point.
He has a delta d minus 1 of x12.
Yeah.
So if your d is
no, see, the 2-point function is fine.
No, I'm just worried about the value of d.
No. The 2-point function is fine because in 4 dimension it has to be delta 2. Because that will take both z1. I mean, there it's just 1 point because a particle when it moves, it does not change its direction of motion, so it stays at 1 point, and it is delta 2. So d must be 3 actually. In his language, for 4-dimensional bulk, d has to be 3, because otherwise the 2-point function will not match.
Right.
So the thing is that in d is equal to 4.
You're saying this should be delta 1.
So this
delta 1, I mean, those are the 3-point function of 3 massless particles in split signature. I mean, which is the most important part because that's, I mean, it appears everywhere like BCFW. So that's the most important. Well, I mean, it depends on your point of view, but if you are just talking about scattering amplitude, if you think of that, then there is a delta d minus 2 also there. I mean, which has to be there for d is equal to 4, but not in higher. Yeah, I mean that. So this structure is 2 for d greater than, I mean, bulk dimension greater than 4. Yeah, no. I mean, I'm just talking about the global. I'm just talking about the global thing actually. I'm not talking about any local conformal, just global. So yeah.
Okay, we should. Yeah, fine. Let's thank Mrityunjay again.
Yeah.
Okay, let's move to the next talk by Boris about BPS black holes and generalized error functions. Yes, please go.
Okay, well, thank you very much. It's great to be back in India after almost 10 years. So many thanks to the organizers for having me. So my talk will be based on some work which appeared last summer with my PhD student Rishi Raj, who is a former graduate from IIT Madras. But it's actually based on a rather long sequence of previous works, going back to some joint work with Ian Manchot and Ashok Sen back in 2010 or so, just at the end of Ashok's sabbatical in Paris, where we started discussing quantum mechanics of multi-centered black holes. So the motivation comes from trying to understand the macroscopic entropy of black holes, this is familiar to everyone. And by the mid-90s, that's been understood how to deal with this issue in the case of supersymmetric black holes in string theory. And one of the key insights was that black holes in 4 dimensions are oftentimes black strings in 5 dimensions wrapped on a circle. So that circle could be the circle from the torus in type 2 string theories or from the N theory circle. But at any rate, it shows that there is some conformal field theory living on that black string in 5 dimensions, which gives black holes after you wrap it on a circle. And so by applying Cardy's formula to the spectrum of this CFT, one can compute the growth of the number of states and get quantitative agreement with the Baker-Shahn-Hawking prediction. So by now, the goalpost has moved a bit further, which is not only to compute the asymptotics of the number of states at large charge, but to actually try and compute them exactly. Compute the number of such BPS states for fixed charge, fixed and finite charge. And I guess the motivation is mostly because we can, it's fun, and moreover, it leads to very fruitful connections with mathematics. So over the years, such precision counting was achieved for simple internal manifolds like 6 torus or K3 cross T2, which leads to n equal to 4 supersymmetry and higher in 4 dimensions. And in those cases, people were able to identify this number of BPS states, or rather the index, which counts them with sign, as Fourier coefficients of various modular forms, either classical or Jacobi or Siegel modular forms even. So this was quite impressive, and you could make precision tests of this Baker-Shahn-Hawking entropy, try to compute subleading corrections. And one of the key lessons in these cases with high supersymmetry was that in general, this BPS index depends not only on the charge of your black hole in 4 dimensions, but also on the moduli of the internal manifold. And they will typically jump across some codimension 1 walls in moduli space, corresponding to the appearance or the decay of certain multi-centered black hole solutions. So in the simplest case occurs when the total charge gamma 1 plus gamma 2 can be decomposed into the sum of 2 positive charges, gamma 1 and gamma 2. And it could be that on one side of the wall, there's just a single spherically centered black hole of total charge gamma 1 plus gamma 2. But on the other side, let's say on the side sigma plus, there will be in addition some bound state contribution from 2 centered bound states with charge gamma 1 and gamma 2, which carries in addition some degrees of freedom from the relative motion, which you can predict from the supersymmetric quantum mechanics. And so it gives rise, it explains this very simple wall-crossing formula, sometimes called the primitive wall-crossing formula. So that's for n equal to 4 supersymmetry or higher. These 2 body bound states are actually the only ones which can contribute to the index. And it was shown by Dabolkar, Moti, and Zagier that if you subtract the contributions from these bound states and zoom onto the contributions of single-centered black holes, then what you get some Jelling series, which instead of being modular are actually mock modular, or in general would be some mock Jacobi forms in this context. So that means they have some anomalous transformation properties under the modular group, coming from this SCFT point of view. But the anomaly is very well determined from the degeneracies of the constituents of the black hole. So this whole story is basically been beaten to death in n equal to 4 supersymmetry and higher. But the case with the n equal to 2 supersymmetry is still quite challenging and interesting. So this is what would happen if you take type 2 string on the generic Calabi-Yau threefold. And in that case, there's no limit on the number of particles or black holes which can form bound states. So the wall-crossing, the chamber structure, and the wall-crossing formula is actually much more complicated. But on the other hand, it's a very well-defined and interesting mathematical problem that goes by the name of computing Donaldson-Thomas invariance for this, the Dirac category of current sheaves attached to this Calabi-Yau threefold. So it's a topic which mathematicians have looked at with great interest. And in particular, so Bridgeland and Thomas and Bridgeland have defined such invariance for arbitrary choices of so-called stability conditions, which extends the notion of Kähler moduli in string theory. So at any rate, in this mathematical context, there was an understanding of the general Walk-Crossing formula for such indices. And even though the answer is much more complicated, it can still be understood from the quantum mechanics of multi-centered black holes, as we showed in this earlier work with the Ashok and Jan Manshot, which I will come back to later, basically applying localization methods to this quantum mechanical problem. However, in contrast to the cases with the higher supersymmetry, we still don't know yet a general way of computing these indices for general charge in any chamber, except in some very special cases. So, however, we can still make some predictions for arbitrary Calabi-Yau threefold by using this M-theory intuition, and the idea that these four-dimensional black holes are black strings in 5 dimensions. In this case, there would be an M5 brane wrapping some divisor or 4 cycle inside the Calabi-Yau. And so the number of BPS states will be determined by the elliptic genus of the SCFT on that 5 brane, on this 5 brane reduced along the 4 cycle. More precisely, because of spectral flow symmetry, you can decompose the elliptic genus as a sum of theta functions of these elliptic parameters times some vector valued function of tau, which can be identified as the Jennings series of BPS indices where we have fixed the D4 branch charge. This enters in the choice of the divisor. And you also fix the D2 branch charge, is this index mu here, which runs over a finite set of values, basically the discriminant group associated to the homology of your Calabi-Yau threefold. So the prediction is that this is the Jacobi form, and as a result, these HP mu's are vector-valued modular forms under SL2Z. This would follow just from the modular invariance of the SCFT, except that you have to make one big assumption, that is that the spectrum of the SCFT must be discrete. And well, that's true for like an isolated divisor, but if the divisor class is reducible into a sum of effective divisor classes, in other words, if the D4 branch charge is not primitive but can be decomposed as a sum of lower charges, then after a very long detour, which I cannot cover here, with Sergei and Jan, we predicted that this vector-valued object HP mu should actually be a mock modular form of higher depth. So the logic involved studying incident corrections to moduli spaces. It was rather roundabout, but the final prescription is very explicit and precise. Namely, even though these functions HP, so I'm going to drop the mu here for simplicity. So even though these HP of tau are holomorphic, they are not modular, but you can repair them by adding to them the product of the Jennings series for the constituents for any possible splittings, weighted by some non-holomorphic theta series, which depends both on tau and tau bar, such that the result here is, in fact, modular. It's no longer holomorphic, but it's vector-valued modular, as predicted by the naive analysis. So I don't really have time to explain the details of the constructions of this theta series here, but it will suffice to say that it extends. So a prescription which was found in Sveger's study of mock theta functions at the time of his PhD under Zagier. So Sveger's understood that the Ramanujan mock theta functions were special cases of indefinite theta series, namely theta series associated to lattices of signature n-1, 1, so with one negative dimension here, direction. So the theta series, if you were just to sum over vectors in a lattice with such a signature, would be divergent. But what the ones which appear in Ramanujan's story and also in our story is that inside this sum of the lattice vectors, you have some products of differences of signs which ensure that only vectors with positive norm square will contribute, as a result of which this theta series will be convergent. However, it will not be modular in general, because under the Poisson resummation, which you usually use to prove modularity, this will not be invariant. But there was a simple trick to fix this modular anomaly found by its figures, which was to replace the sine function by an error function. So an error function, if you remember, I guess I have a picture somewhere later in the talk, but it's just interpolating from 0 to 1 smoothly. So it's a kind of a regularization of a step function. And so if you also include a factor of square root of the imaginary part of tau in this expression, then you can actually show that the second expression is both convergent and modular. So this is the simplest signature n,1 case, but in this, which would arise in the contributions from two-centered black holes in the story which I'm started to explain. But as long as you have more than two centers, the signature of the lattice increases to some number r. And so what you have to do is to generalize this, this prescription. And what we found in work with Banerjee and Yan was that a very similar trick still worked, where you have to replace in every, so in general we have product of signs, product of differences of signs in the series. And you just have to replace them by a higher order analog of the error function. So here I have a formula that says that the usual error function is the convolution of a sign with a Gaussian. You can do a similar prescription to take a product of sign functions with some coefficients m here, and just convolve it with a Gaussian in the r-dimensional space. And you can show that the theta series that you will get by this replacement will also be modular. But the price to pay, again, is to insert some non-holomorphic dependence in the tau modulus. So, and the main question I want to answer in this talk is, where does this non-holomorphic dependence comes from a physical point of view? But let me first say that this prescription was actually tested in various setups. One in the case where your Calabi-Yau manifold is a kind of so-called local del pezzo surface, so it's the canonical bundle over some surface. In that case, the counting of these d4, d2, d0s on the surface is the same as the counting of Waffa-Witten invariants. So for the twisted n equal to 4 super Yang-Mills theory on that surface. And then there were earlier work about non-holomorphic anomalies, holomorphic anomalies in this setup, which is correctly reproduced by the prescription which I outlined. And more recently, we have actually been able to test it in some compact Calabi-Yau examples, such as the quintic and other one-parameter manifolds, where using some recent progress on wall crossing for one-parameter three-folds with the help of some mathematician, we could actually compute a few terms in this Q-series expansion and confirm modularity, both modularity for 1 unit of d4 branch charge, as well as the smog modularity for 2 units, just in a couple of cases. So basically, my goal now is to move to some kind of lower brow discussion and just come back to the quantum mechanics of multi-centered black holes and try to understand the origin of these non-holomorphic contributions. And as I will explain, they can be traced to the contributions of scattering states, not only the bound states in the quantum mechanics, but also scattering states. But maybe that's a good time to pose for questions, if there are any so far. Okay, so let's look at the quantum mechanics of a system of n black holes, or more generally n dyons in four dimensions. So these dyons are going to carry some charge gamma I, and they will have some non-trivial product, Dirac product, which I denote by gamma ij. So it will be the product of electric from one times magnetic from the other minus the reverse. And so back in 2002, Frederick Denef proposed this description in terms, well, of a Lagrangian with 4 real supercharges. There's just the usual kinetic term, including also this auxiliary field di. There are some first order term in derivatives coupling to the position, to the velocities, as well as a potential, which is written here in this auxiliary form. So if you eliminate the auxiliary fields here, you would get a potential which would be the sum of this ui square over 2mi. And this so the potential is the sum of quadratic contributions, which are basically given by this quantity here. So the sum of the gamma ij's over the distance from I to j, in order to be in a supersymmetric vacuum, must be equal to theta I for any I. So if these equations here are actually recognized as the equations which determine the relative positions of the centers if you look at supersymmetric solutions of n equal to 2 supergravity. So at least the ground states correspond to these multi-centered black hole solutions. And the claim is that this quantum mechanics describes the low energy dynamics of these centers. So there are, among the parameters here are also the masses of the centers. This is just the absolute value of the central charge in n equal to 2 supergravity. And then there are these real parameters theta I, which encode the dependence on the moduli, the vector multiplet moduli in supergravity. And they are just given by the imaginary part of the central charges up to a phase, which is actually the phase of the total central charge. So this is, well, it's a simple problem to state, but in general, it's hard to solve. But in the two-centered case, it's still very easy and doable, and it's kind of quantum mechanics 101 type of exercise, very similar to the hydrogen atom. So if you work in the center of frame of the system, and I'm going here to denote by 2q this Dirac product between the two charges. So you see that the Hamiltonian has a kinetic term, which involves this monopole field strength at the origin of the center of mass. So it encodes this kind of Lorentz interactions between the two centers. It has this potential, which is theta minus q over r squared. And then it has some helicity-dependent coupling, which comes from these fermion terms in the action, which I forgot to mention, but will play actually a rather crucial role in the story, which I'm going to explain. So it's the mass m here is the reduced mass of the system. And yeah, so if you look at the definition of this parameter theta, you will see that theta square is actually the binding energy in the system. So Z of gamma 1 plus gamma 2 would be the mass of the bound state, and this will be the mass of the sum of the masses of the two constituents at infinity. So this Hamiltonian actually, so it describes, because of these sigma matrices here, it describes 4 degrees of freedom, but 2 are bosonic and 2 are fermionic, of course, as expected for supersymmetry. Okay, so in this system, we can very quickly see that depending on the sign of this product Q times the parameter theta, they may or they may not be supersymmetric bound states. So if Q theta is positive, there will be some zero energy state, at least classically. Whereas if it has the opposite sign, there will be no such bound states, either BPS or non-BPS. Thank you. But I know in either cases, there will be scattering states corresponding to energy above this infinite value. So there will be bound scattering states coming from infinity and back. Anyway, at the level of, here we can actually completely solve the system. You can go to a basis of monopole harmonics, reduce it down to a radial equation, which very much looks like the hydrogen atom, and check that indeed there are supersymmetric bound states exactly under this condition, and the number of such states is actually given just by 2j plus 1. So it's a representation of SU2 or SO3 whose dimension is given by this Dirac pairing, actually. Okay, so that's this, of course, has been known for a long time. You can also actually compute the density of states on the continuum. And one of the key points here is that even though supersymmetry requires that there should be as many fermionic and bosonic bound states, it does not require that the spectral density for fermions will be equal to the spectral densities for bosons. In general, they will be, in fact, different. And here you can compute both of them separately. You can just solve, you can compute the phase shift by standard methods, and then compute the Witten index by just summing over all the degrees of freedom, and this will give the density of states for each degree of freedom separately. Now, because of supersymmetry, there's actually some numerical considerations that take place. And outside this complicated gamma function ratio, there just remain some algebraic expressions. And if you, there are two parts to the answer. One is just the bound state contribution, which, as I said before, is 0 on one side, and then 2q, there's a factor of 2 missing here, 2q on the other side. This is the heaviside function. But there are also non-vanishing contributions from the continuum, starting from this binding energy to infinity of that form. And you just can compute the integral, and you find exactly this error function behavior. So the point is that the discrete spectrum jumps. The contributions from the continuum, which is this part here, also jumps because it's this complementary error function. But the sum of the two is actually a smooth function given by this error function interpolation. And well, I should have mentioned here that this parameter r is the radius of the circle, is the same as, well, 2 pi r is the same as beta, and turns out to be the same as imaginary part of tau in this modular, in this generating series for BPS indices. Okay, so that's a very simple story because it's just quantum mechanics in a potential. But once we go to beyond two constituents, it's no longer solvable. But nonetheless, we can still count supersymmetric ground states by localization, and we can also hope to actually compute these contributions from the continuum. That's the new thing in this paper from last summer. So just to remind you about the bound state part, so we notice that this moduli space of BPS solutions, which is a set of solutions to these so-called DNF equations, modulo translations, has actually an even dimension, 2n minus 2, and it carries a natural symplectic structure, which was found by De Boer and friends. And basically, it has the virtue that the angular momentum carried by this multi-sided solution is the moment map associated to the action of rotations on this phase space. Okay, so if you're interested in just bound states, you can truncate the system to this phase space here. And the BPS states would be some harmonic spinors on this phase space. And to compute, to count them, you have to evaluate the Dirac index, or more generally the equivariant Dirac index, where you put some fugacity y conjugate to the angular momentum in one direction. And, but yeah, in the unrefined case, it would just be the symplectic volume of that phase space. Now, it's still a complicated phase space, but because it has this action of rotations, and under the assumption that it's compact, then you can still compute its volume, or more generally, the Dirac index by localization, as we pointed out with Ashok and Yan. So it's pretty clear that so you have to look at fixed points with respect to rotations along the fixed axis. And it's pretty clear that if you have n centers, the only way they can be invariant of the rotation is if they all sit on the same axis. And so out of this 3n-dimensional problem, you're just down to an n-dimensional problem, a 1D version of Denev's equation, which is to solve for these equations here. Well, except for overall translations, there are just isolated fixed points, which correspond to critical points of some potential. So by the usual Dusteman-Ekman type of theorem, the index, or Atiyah bot, if you like, the index of that Dirac index on that phase space would be a sum over fixed points. So the fixed points you can just enumerate according to the ordering in which they occur along the z-axis. So we can define this fc of gamma I theta I as the number of solutions with a particular ordering, with some plus or minus sign determined in this way. And dress every of these solutions with the corresponding y to the j3 or to j3, and then sum over all solutions and divide by some one-loop determinant, and that should be the Dirac index. But in fact, it will be the Dirac index if the phase space is compact. In some cases, it's not. There's this issue of scaling solutions. Okay, thank you. So you have to repair. This prescription would actually not work because particularly would not have a smooth y goes to one limit, which would be the symplectic volume, because we miss some boundary contributions. So with Ashok and Yan, we divide some way of repairing it. But in this context, there's actually a better way of doing it, which is to replace this count of collinear solutions by a count of so-called attractor flow trees or planar trees, which counts planar attractor flow trees. I don't really have the time to go into this, but let me just say that it's an alternative prescription for computing these coefficients, which ensures that there will be a smooth classical limit. And in fact, it's the one relevant for if you want to compute these indices at the large volume attractor point, as opposed to counting single-centered black holes as we were trying to do with a shock. At any rate, for two centers, the two are just the same because the phase space is just a two-sphere. It's just the direction of that dipole that you can choose. And so there are just two fixed points, the North Pole, South Pole, and, well, of course, you have to be on the right side choice of sign. And in this way, you get just the expected counting. But as I explained in the next couple of slides, you can also, using localization, compute the full Witten index. So how do we do this? Now we go back to this path integral. And here we're going to rely on a very nice observation in a paper that goes back to Sunil's work 83, was also studying indices of systems with continuum. And the authors pointed out that, in fact, in such quantum mechanics, the path integral, or the Witten index, localizes on time-independent configurations. So rather than having to sum over the trajectories of these n centers, we just sum over the zero modes, so time-independent configurations. So we have this xi for each centers, we have the fermions, and we have these auxiliary fields di. And the exponential, we just have removed all kinetic terms, we're just left with the potential, so the d term, in other words, as well as the fermion coupling. And here there's some kind of diagonal, you have to get rid of the center of freedom, so you have some non-trivial matrix here, which is the reduced mass matrix, but it's not essential. Okay, so I'm getting to the end of my talk here. So the key, so basically what we need to compute this integral, and if you integrate out the fermions, of course, you're just going to get a determinant, which would seem to, which is a complicated functions of the radii. However, the key observation is that the product of the flat measure times this determinant takes actually a very simple form, which is based on this observation that the full bosonic configuration space, so arbitrary locations, you can think of it as being foliated by these BPS phase spaces, but with arbitrary values of these stability parameters ui, namely you just define the ui as being this sum of gamma ij of xi minus xj. And now, rather than scanning over R3 and minus 3, you can just scan over these values of ui, so you get n-1 directions. And the non-trivial, the crucial observation is that the Jacobian in the change of variable, together with this determinant, actually just produces the symplectic volume of that phase space on the nose. So this is, you can check it for yourself for two centers, and in general, it follows from this simple identity between complex and symmetric matrices. So at any rate, if once you use this, the problem becomes actually very simple. So well, first of all, if you integrate out the di's here, you're going to you produce a Gaussian factor which is centered at where the ui's are equal to the physical parameters theta I. And then it's multiplied by just the symplectic volume of this BPS phase space. So the symplectic volume, I remind you, is the classical limit of this equivariant Dirac index. So it also has, but in particular, it's locally constant, right? It has a wall crossing behavior as a function of u, but on each patch, it's actually constant. And so you see immediately that the result is going to be the convolution of a locally constant function by a Gaussian, and therefore those are the generalized error functions of the title. So let me just say that here I explain how to get the index, but actually the more useful is the refined index, and we haven't quite yet shown it, but it's plausible to assume that it's obtained by just replacing the volume by this equivariant Dirac index. So there are some details to understand here, but this assumption seems to be consistent. So in other words, what we've been able to is to rewrite this Witten index as a convolution of the usual index counting bound states with a Gaussian weight, which is this term here. Okay, and of course at 0 temperature, the Gaussian integral gets picked around, localizes around the physical values of these U parameters, and therefore you reduce to the index counting supersymmetric bound states. It's very easy to check that this prescription works for n equals to 2, and so in one line you get the result which previously involved these constellations of gamma functions and so on. But it works for arbitrary number of centers as long as you know how to count the number of these collinear solutions or these planar trees. Fortunately, we know how to do it for arbitrary number of centers. There are some recursive equations. So in fact, we can write down explicit answers for arbitrary number of centers. Here, I just gave the answer for 3 centers. Actually, one permutation for 3 centers. And you see that involves these generalized error functions of degree 2, as well as degree 1 error functions corresponding to the contributions of the continuum for the bound states, well, for the scattering of 1 particle, let's say 3 against the bound state of 2, let's say 1 plus 2. Okay, I think I'm really running out of time. Let me just say that when we go back to the comparison to this modular completion of Trending series of Dorrance and Thomas invariants, we have to work in the large volume attractor point. So it's a point where actually all the bound states disappear. And as a result, the only contributions you have are these complementary error functions, which are really the contributions from the scattering states without any bound state contribution. Okay, so I'm basically there. So there are some subtleties which I've put under the rug. But basically, we have found in this way a shortcut as well as to this non-holomorphic, so this prescription for the modular completion of Trending series of DT invariants. And more importantly, we also found a physical understanding of this non-holomorphic dependence for arbitrary number of centers. So this opens the way of testing this mock modularity to higher D4 brane charge. So part of this work was done, in fact, earlier last year by Alexandrov and his student, who computed explicit solutions of these modular anomaly equations. But it remains to compute actual solutions. I mean, once you know these solutions to the inhomogeneous problem, you have to fix the homogeneous solutions, like the modular ambiguity. And for this, we need to know more, have better ways of computing the first few terms in the series. And in practice, it reduces down to a lack of control on higher genus GB invariants. So I'm not covering this part of the story, but let me say that we expect that progress on this side would have implications for the topological string amplitude and vice versa. Okay, sorry for running a bit over time, and thank you for your attention.
We can take a couple of quick questions over there.
So this index that you talked about, is it calculable from the Mukai vector of these coherent shifts, or?
Yeah. So this, in mathematical terms, the charge gamma is actually the Mukai churn vector of the corresponding sheaf. So
and you also get the square root of the Todd.
Well, I mean, that's a matter of choice, how you pick your basis. I mean, the integral basis would be given by exactly what you say, but it's not necessary to work with integral charges. So it's.
I see. So you work in the Q-valued cohomologies.
I mean, we just work with the K-theory lattice. That's where the charges take place. And mathematically, you have indeed to compute the Euler number of moduli space of stable coherent sheaves for that particular Chern vector.
And is the number n related to the rank of the coherent sheaf, or
no,
it's different?
No. So the number n was the number of constituents, the maximal number of constituents in the splitting of the total Chern vector into a sum of positive Chern vectors. So the notion of positivity is actually rather subtle. If you are in quiver quantum mechanics, it's just having positive dimension vectors.
So that's not related to the zeroth.
It's not the same as the rank. I mean, the rank would just be the first entry in a Chern vector. And in particular, one important fact is that in this Calabi, in this picture of coherent sheaves, you could have bound states with positive and negative ranks, so
Precisely.
D brane, anti-D brane.
Precisely.
And it's very hard to determine a priori what are all the possible constituents.
That's why I asked here.
Yeah, that's right.
I see.
Hi, I have a question here on the left.
Oh, here, sorry.
What's the issue with computing for when you have charge D4 greater than 2? What is the technical issue that you can't compute?
Okay, so so what we like to do to test this kind of modularity conjectures is to compute the first few terms in this Q series, which means the number of bound states with the minimal values of the D0 brane charge. And well, physically, we expect that these bound states will be some D6, anti-D6 bound states, like Denef and Moore have argued. So this you would be able to count by, you know how many D6, with a single D6 charge, you know that they are counted by the topological string amplitude. That's what was lurking behind the last sentence in here. So you would think that it comes from basically the square of Z top. That's this kind of OSV conjecture. But that's actually not mathematically proven, and in fact, in many cases, it's wrong. So only for the first term, you can use this D6, anti-D6 picture. And you need much more elaborate machinery to compute higher terms in the Q expansion. I mean, I could give a full lecture, but not in half an hour. and for this, you need to control wall crossing in great detail. Yeah, so that's in general an open problem for many parameter Calabi-Yalls. In the one parameter case, we developed this strategy in this paper with the Pesbachs and others, but in general, it's an open problem.
Okay, let's thank Boris again.
Thank you.
Okay, so the final talk before tea is by Swapnamoy Mondal on spontaneous breaking of extremality, conformational entropy in heat brain systems.
Hello. Okay. So first of all, many thanks to the organizers for all this support. Very happy to be back at ISM after, I don't know, at least 6 years, 10 years, something like that. I'll also talk about black holes, but these black holes would be non-supersymmetric. So on the downside, I'll not have nice mathematics. On the upside, if you wish, these are, morally speaking, somewhat closer to reality. This term I invented, I'll explain what I mean by this. The talk would be based on a paper I wrote last year and upcoming one, hopefully this month, which I am writing with Pranav Rai. He's an AI guy with physics background and still loves physics. So I'll start by defining the broad questions and how I've done some progress in answering those. So two main questions. So first is that as per semi-classical black hole thermodynamics, we know that extremal black holes should carry 0 temperature, and as per statistical mechanics, we know that that means that the underlying quantum system should have a very highly degenerate ground state. So just recall that in the black hole entropy formula, the Wittgenstein-Hawking entropy formula, you have Planck length in the denominator, and you have exponential of that in the degeneracy. So it's a huge number. It's extremely unlikely for any quantum system that you can think of, any class of quantum systems, be it textbook, potential wells, or many-body quantum systems, or in QFTs, to have such a highly degenerate ground state, unless you have very much fine-tuning or some symmetry. Speaking of symmetry, supersymmetry, of course, serves the purpose, but we are talking about non-supersymmetric black holes. in more recent years, people have looked at this problem more carefully, and people found that in the black hole side, if you are careful enough in taking into account various quantum effects, there is significant modification in the low temperature thermodynamics. A lot of people have worked on that, I believe, including some in the audience. The upshot, for me at least, of these works is that in the entropy you get a log T term with some positive number here, which means that, strictly speaking, if you take T goes to 0, you get minus infinity. The nicer way to look at it is that the density of states, exponential of entropy, that vanishes as you take T goes to 0, which is incompatible with a highly degenerate ground state. So this suggests that there is no degeneracy. But if you are a D-brane person like me, you would like to see an explicit D-brane construction, a microscopic Hamiltonian, and you will like to see this explicitly. Note that there is no underlying Hamiltonian here. This is like black hole stuff. In this talk, I'll explicitly construct a certain D-brane description from more or less first principles, where I'll explicitly show that there is indeed a unique ground state. So if you wish, this is kind of expected, but to my knowledge has not been done. There is another question that you might ask that, okay, let's accept that there is a unique ground state, and if we sacrifice supersymmetry, there is no strong reason why that ground state should be extremal either. Note that in this word line theory, extremality means having a ground state that is 0 energy, exact 0. That's also a very fine-tuned situation. What is not obvious is that the nature of this non-zeroness, it's quantum or classical. I will argue that at least for these class of black holes, it's actually classical. That is, you have a potential which its nature is such that the minima will have positive energy, which is to say that a theory that is meant to describe an extremal black hole fails to admit an extremal ground state. I thought it deserves a name, and I call it spontaneous breaking of extremality. Think of a better name. I'll end with a question, this talk, perhaps a proposal. We'll find that although we do not, of course, since we do not have a degenerate ground state, the standard way of thinking about black hole entropy would not work. But we will find that some concepts which are quite common in some condensed matter systems, they turn out to be useful. I'll come back to this. Okay, this I talked about already. Okay. Since we are talking about microscopic description, you might first think of using CFT, the most well-known microscopic descriptions, as Boris mentioned that very often 4D black holes are thought of as some effective strings in a 5D, and the low energy theory of such effective strings turn out to be, you can take them to be CFDs and explain black hole entropy. The thing is that in CF, degeneracy is a normal thing. There is nothing extraordinary about degeneracy. Even non-extremal states are degenerate there. So if you want to ask whether some state is truly degenerate or not, you better go to some description where it is not the norm. It's a non-trivial thing to have degeneracy. Also, the kind of CFTs we are mostly familiar with, like MSW CFT and so on, they're typically free. If there is a potential, you might expect interactions to be important. So for these reasons, I'll have a very different setting. I'll have not an effective string, but an effective particle. So I'll talk, okay, let's get to the black hole. The black hole will be non-supersymmetric, but still extremal. The challenge, obviously, is that I do not have any supersymmetry, yet I have to write down a Hamiltonian. Note that in the CFT description, of course, with conformal symmetry, you don't really need supersymmetry that much. But even there, the theory is supersymmetric. The states you might choose to be non-supersymmetric, but here even the theory is non-supersymmetric. The way out, what we do is that we start with a supersymmetric black hole, which has a bunch of D-branes. Now, D-branes are supersymmetric objects. The whole system it can preserve or break supersymmetry depending on the orientations of the constituent d-branes. So I'll start with a supersymmetric d-brane system, then I'll flip orientation of one of the d-branes. There's a trick how I do that. The point is that although the whole system will be non-supersymmetric, the constituents are still supersymmetric, and that fact can be used to write down a Hamiltonian to sufficient extent. Do stop me if you have questions. So first, let me quickly mention the supersymmetric black hole. It's some 1 decade old, the construction I'm talking about. So these are 4 charged black holes in n equals to 8 string theory. That is, we have the simplest theory, 32 supercharges. The compactification is over 6 torus, and we are talking about black holes in flat space, not in ADS. In the microscopic description, these 4 charges are, so these are Raman charges. So in the microscopic description, they come from, they're just the number of certain d-branes. For 4, I'll have 4 stacks of d-branes. 3 of them will be d2 and 1 will be d6. So 6 torus will have 3 disjoint 2 cycles. So 3 d2 branes will wrap those 3 2 cycles, and the d6 brane will wrap the entire torus, 6 torus. And for correct orientations, this system preserves 1/8 of the supersymmetries. So the thumb rule is that you add 1 d-brane, it breaks half of the supersymmetry. So to start with, you have n equals to 8, you put the first brane, n equals to 4, the second brane, n equals to 2, the third brane, n equals to 1, fourth one is tricky. You can make sure that it does not break any further supersymmetry, in which case you will have this supersymmetric black hole. Metric is not important. Okay, so here is a cartoon of that. One information that we will use is the structure of the Lagrangian. So first you have theories living on each d-brane stacks. Those will be there. Then there are strings stretched between different d-brane stacks. So there are pairwise interactions. There would be some such terms, these Lij's. And then like a triplet of stacks can also interact. There will be some terms corresponding to that also. We found that we can stop there for the purpose of explaining the entropy. So I'll stop here. Okay. Note that this system, there is no common direction in which all the d-branes span, which is to say that the final system is an effective particle. It's a point-like. Okay. Now comes the supersymmetry. Each stack preserves n equals to 4. One important fact is that if you flip the orientation of the d-brane, it still preserves n equals to 4, but a different n equals to 4. A pair, you add a second d-brane, it also preserves n equals to 4, a different one. Altogether, a pair preserves n equals to 2, third one n equals to 1. Now, if you just look at these equations, which tell you that which supersymmetries are preserved, just a few lines of algebra will tell you that from first 3 equation, you can get the last one with a definite sign. So the sign here is not something for you to choose. For one choice of sign, you will preserve this n equals to 1, this brown n equals to 1, and for another sign, you will fail to preserve it. Okay? So for the green case, we already know the theory. For the red case, we will figure it out. Okay. This you are familiar with. On, for example, for D3 branes, you know there is n equals to 4 super diagonals on each D-brane stack. That goes on. Then alongside that, for these strings, I'll just mention the degrees of freedom. You can quantize the open string and find out that the field content field, it fits with n equals to 2 hypermultiplet, that is 2 n equals to 1 chiral multiplets. Okay, this is the most important slide. So we want to make sure that the whole system does not preserve any supersymmetry, but at the same time, we have to make sure that every brane preserves supersymmetry. That's there by default. Every pair preserves n equals to 2, but different n equals to 2. every triplet of branes preserves n equals to 1, but different n equals to 1. So in particular, if you choose two different triplets of brain, so I drew this diagram where every node represents one D brane. Recall that we have 4 of them, so there are 4 nodes. So if you take first, second, and third D brane, altogether they'll preserve some n equals to 1. But if you take 1, 2, and 4th D brane, they'll also preserve another n equals to 1, right? So that altogether they preserve none. And you have to make sure that for every choice of triplets. Now, whatever these n equals to 1s might be, this one and this one, note that both these triplets have this 1-2 pair in common, 1-2 pair of branes, which will preserve n equals to 2. So it must be that these two n equals to 1s are already contained in the n equals to 2. They're like subgroups of this n equals to 2. Very simple choice is that they're related by SU to R symmetry. For writing down the Lagrangian, we need to know what this means for fields. That's textbook stuff. You can look it up. There are well-known actions. This is the essential logic of this. Of course, here I showed you for one pair. Now there are like 4 possible triplets, so 4 choose 2, 6 pairs of triplets, and it has to work for all pairs. It requires some effort to guarantee that, but the physics is this. These are standard actions of SU2, nothing illuminating. Again, you have to do a bit of a renomenclature to make things work. I'll skip this. One very important non-trivial consistency check is this, that for the supersymmetric black hole with same charges, recall that if we just flip a D brane, the sign of the charge change, not the magnitude. In the supersymmetric black hole case, since it preserved n equals to 1, that means that it broke like 32 minus 4, 28 supersymmetries. So you should have 28 goldstones, and since it is still supersymmetric, partner goldstones, 28 goldstones. Now, in the non-BPS case, you break all the supersymmetries, so you should have 32 goldstones. But since this flipping does not change any goldstones, you should have 28 goldstones. This is, it's not entirely obvious that it will work out because my building blocks are still superfields. It's just that I'm using different superfields in the same Lagrangian. This works out actually. Just one example with some terms in the superpotential. So, for example, in the for the BPS black hole, for interaction between first, second, and third branes, we had a term in the superpotential like this. Z's are these strings stretched from like first to second brane and so on. And a similar term for first, second, and fourth brane. Now we'll keep one of the terms same. Let's say this one, but in the other one we'll rotate the 1-2 field by some SU to R symmetry, which tells you that these both terms are supersymmetric but under different supersymmetries. Therefore, altogether there is no supersymmetry. This is how the whole superpotential looks like. So, yeah, this I think I have already gone through. Okay, after that we get some F-term potential which looks like this. The point to note is that you have some daggers here and there. This is because the SU2R rotation of a hypermultiplet, it exchanges the complex bosons of 2n equals to 1 chirals, but with a complex conjugation, I mean with a Hermitian conjugation. So this is a consequence of our strategy, not a random fact, and it will be consequential. So these are not holomorphic any longer. Okay, now the question. So once you have an explicit Hamiltonian, which is not supersymmetric, I suppose we'll accept the fact that the ground state would be unique in absence of any fine tuning. I have an explicit Hamiltonian in the sense I showed you the superpotential. There is no reason why there would be a unique ground state. So we do have an explicit construction where you have a unique construction of an extremal non-BPS black holes with a unique ground state. So the first question that I posed, this is the answer I propose. Now I come to the next question, but any questions till now from you? Okay, so in this brane construction, they will simply be like, for example, the whole system could move in the 3 directions. Those would be some goldstones. Some branes could move like this, one on top. Yeah, goldstone would be bosons, right?
You say there should be 28 massless bosons?
Yes, which will decouple.
And the Goldstinos will not be massless, right? Because supersymmetry is broken.
Yeah, they will also be massless. Goldstinos, so
they should correspond to a non-linearly realized supersymmetry. Okay.
Well, yeah, that would be another way to look at it. So this is how it concretely works out. For example, you see difference of certain superfields appear. So the center of mass kind of combinations will not appear.
That's always the case.
Yeah. So I'll have 32 such fermionic combinations and 28 bosonic.
Okay.
That's what I mean. Any other questions? Okay. Okay. Let me first point out a very well-known fact. Let me just quickly take you through this. So think of supersymmetric vacuum in a supersymmetric theory, where you have some chiral multiplets. Now, for every chiral multiplet, you have one F-term equation, right? But then on top of the F-term equations, you have D-term equations. So naively, you might think you have more equations than you have variables. How does that work out? How come you have supersymmetric vacuum? The potential, you'll recall, is that the sum of mod square of these F terms and D terms. So supersymmetric vacuum will require all these terms to be 0. That works out because the F term equations are actually invariant under a larger symmetry. You can complexify the gauge symmetry. So you can take the U1s to be C star, that is multiplication by non-zero complex numbers, and so on. So essentially, the number of extra D-term equations that you have in the F-term equations, there is that much extra redundancy. That actually cancels out, and you have same number of independent real variables and independent real equations. So it works out. The feature I want you to note is that here it's absolutely crucial that the F-term equations are holomorphic. If they were not, this thing will not work out. Now, I just need to point out that the nasty potential that I showed you, it was sum of mod square of terms which are not holomorphic, neither anti-holomorphic. They are mixed. So this enhancement of symmetry or redundancies will not occur. Therefore, generically, you cannot set all these terms to 0. We cross-checked it with numerics. We used some TensorFlow and feed our potential as the loss function, and indeed we found that there are no zero energy minima as expected. Note that it's not a like random fact, it's a direct consequence of the symmetry structure. This is what I meant by the spontaneous breaking of extremality. Now comes the obvious question, all that is very nice, but what about black hole entropy? If I have a microscopic description, I should have some explanation for entropy. Now, the standard way will not work out because you have a unique ground state. And even deeper problem is that it's not very clear what to expect. First of all, in absence of supersymmetry, it's not obvious how you should connect the black hole side with the de Broglie side, as nothing is protected. And then for the supersymmetric black hole, the indices were known from older works. We knew what to reproduce. Here, that is not the case, but you can note that the black hole geometry, just the metric part, it does not know about this it doesn't care about sign of charges. If you flip a d-brane, the metric and therefore the Bekenstein-Hawking entropy will remain the same. So one strategy could be that we look at the BPS black hole and we note that it is known that that black hole has 12 degenerate zero energy minima. So I look for the number 12 in this case. I try to see if there is anything that is 12. And it turns out that yes, the number of local minima is 12. I do not have analytic evidence for this, but we did numerics, and there are some parameters in the potential. We took various values of the parameters, we changed the learning rates and etc. But this fact was robust. Every time we found 12 minima. Now, this is not a very stringy thing, but this notion that number of minima being, log of that being related to entropy, it's not entirely unknown in physics. Similar notions appear in spin glasses, and I believe in complicated molecules. There also people have such notions. I'm still digging literature, but from what I saw, people call it configurational entropy, configurational complexity, stuff like that. It seems that I'm tempted to propose that in these settings, the black hole entropy is perhaps reproduced by logarithm of, so it is the configurational entropy of this microscopic potential. This is a side comment, really. It turns out that along with these minima, there are also some other minima, actually continuum of minima, but they are high up. These correspond to these are very simple. These correspond to d-branes being like separated in subsets. Like, for example, there are 4 d-branes. If all of them are free, strings, there are no strings between them, free to move, like a gas of d-branes. Those kind of configurations turn out to be minima. Okay. To me, this looks a bit like a gas of d-branes, and I'm a bit tempted to think of the situation where a system rolls down from such a high minima to a low minima. Kind of looks like a giant molecular cloud collapsing and then bypassing the intermediate star to form a black hole directly. Okay, I'm almost done. I'll just leave with some comments. First of all, I looked at the smallest possible charges, and the term black hole is anything but justified. I have to look at larger charges now to confirm this picture is true or not. Since it's non-supersymmetric, I wonder if somehow CFT1 arises in these settings. It's not clear to me how it could be. One observation I have is that, so we have this non-zero energy of this black hole, which means it's incompatible with having a AGS2 near horizon geometry, but so that AGS2 should be destroyed somehow. Since we worked with smallest possible charges and found this feature by standard holographic duality, you will expect that in the gravity side, it should show up as a quantum effect, because we saw it for small charges. So we did not need any large n, that is classical limit. Can have to look into it more carefully, but I guess it's conceivable. Lastly, I'll just end with something curious question. So this d-brane setting by construction has a positive minima, not only non-zero but positive. I wonder if one extends this d-brane system to the R3 so as to have a going to type 2b and then d5, 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 d9. That system, the Lagrangian density would be the same, so therefore it would still have non-zero minima. I wonder if one could look into more detail and somehow get a de Sitter space out of it. That's all I had to say. Thank you.
Any questions, Swapnamay?
In this model, can you also address the spectrum of excited states? That is, maybe to see that in the SUSY case you have a gap, and in the non-supersymmetric case you may have a continuum or very closely spaced states?
Yeah, so I would be very happy to see exponentially many low-lying states. It failed. Oh, okay, that's fine. So the potential, I had a cartoon probably. It's really like this in the sense that you have multi-well potentials, and so if you quantize it, what you'll have that around each well, at least to harmonic approximation, you will have low-lying spectrum would be harmonic oscillator-like. That would not be that picture, like exponentially many low-lying states. I suppose, I wonder what happens for large n. It's conceivable that all these minima will come down and probably will become very close, so it becomes, large number of states.
Thanks.
Well, I wanted to object to one statement you made at the beginning that the MSW string or black string CFT was free. I mean, it's not free. It's a non-linear sigma model in some modelized space of stable objects or modelized space of divisors and so on. Right? So it's true there's no potential, but it's not free by any means.
Right, but do people prove that non-linear sigma model is indeed a CFT? Like in MSW?
That's why it's strongly coupled, and it's expected to flow to a strongly coupled CFT in the infrared. So
yeah, in decoupling limit, I agree. It's a CFT.
Yeah.
So, okay, I guess it's.
Okay, I had another objection about the terminology spontaneous breaking of extremality. There's nothing spontaneous here. It's just explicit breaking of supersymmetry, right?
No, supersymmetry I'm not saying.
So, I mean, it's an explicit breaking that you do by flipping these signs. So the specific question I wanted to ask is, would you have ways to to interpolate between the supersymmetric and non-supersymmetric language that you've discussed, and in this way be able to follow these 12 supersymmetric vacua and how they lift? That would be kind of a useful.
I don't have answer to that question because I'm explicitly working in the non-supersymmetric setting, as you pointed out. But I suppose what one has to do is that rotate one d-brane to completely, change the orientation.
So just include write a similar quantum mechanics, but for arbitrary angle, and try to follow this vacua as the angle goes from 0 to pi or something like this. It's just a suggestion.
Yeah, I'll look into it. Yeah. Yeah, it's not a very good name that I agree. I couldn't think of a better name.
Okay, then let's come back from coffee at 5:30, last session. Let's thank Swapnamoy again.
90. हाँ, not okay. पर्दे पे नहीं आ रही ना, देख लो एक बार.
Okay, welcome back. So let's begin the final session. First talk is by Tim Raz on scale-separated vacua in string theory.
Another couple more people coming. Maybe let's wait 1 minute. Start? Yeah, okay, okay. So, sorry. Let me also start out by thanking the organizers for putting this wonderful workshop together. I know it's not easy with so many people, but so far everything worked very nicely, and I'm very happy to be here, in particular see Abhishek again. What I'm going to talk about it's not all these papers, but it's some work in collaboration with all these papers. Johannes Walcher, Katrin Becker, my former student Muthuswamy Rajaguru did a lot of work with now a postdoc at IFT, and a postdoc George Stringas. So my talk is more on the string pheno side, and that's why I thought I'd start with a very basic introduction and try to put not too many equations, but maybe I managed to convince you that there is something important that needs to be done, that needs to be studied better, and one can approach it actually from many different angles. So I teach a lot, sometimes introductory physics courses, and you often get this plot, which maybe you have seen before or not. But for me as a string theorist or string phenomenologist, what I take away here, and which maybe you can see from the back, there are like 3 families of chiral matter. We have abelian, non-abelian matter. And if I were to be tasked with constructing that in string theory, although I have never done it, I could come up with a couple of ways. We can do heterotic on Calabi-Yau manifold, toroidal orbifolds. That's how string theory kind of started out. We have F theory, we have intersecting D-branes in type 2A. We can put M theory with singularities on G2 manifolds. We can put D-branes at a singularity, and there are probably many more ways of constructing that. So for me as a string phenomenologist, I would say we are in very good shape, and we can kind of construct that in pretty much every string theory. You can do it in M theory. We really kind of get this. There's, however, one particle, which is the Higgs, which is the only scalar field, and that has potential. And if you ask, can we give masses, can we generate scalar potentials for all scalar fields in string theory? Can we make them massive? Can we make them unobservable? Things are much more tricky. But this is essentially what we need to do. It goes by the name of moduli stabilization. You stabilize the field. They have a particular expectation value. In string theory, all the internal dimensions, the string coupling, everything can be order 1, order 10, order 10,000. All needs to get kind of a scalar potential, and we want to kind of find a minimum. The reason we want to do that is that the massless scalar fields would induce some kind of fifth forces. They control parameters in the standard model, so we somehow want to fix them. And that was kind of a topic of the Swampland program in the last maybe 5, 6, 7 years, and it mostly kind of, I guess, got a lot of attention in 2018. There was a paper by Kumun Waffer, but previously also by Danielson and Thomas van Riet, that essentially said there shouldn't be any de Sitter vacua in string theory. And de Sitter vacua means positive cosmological constant, similar to the dark energy we observe in our universe. And that seemed to somewhat contradict what other people had been doing. So if you haven't been following the field closely, this might have come as a huge surprise. There is, since 2003, the seminal paper by Shamit, Renata, Andre, and Sandeep, and other people constructed large volume scenarios. So this goes by KKLT, where they constructed de Sitter vacua. They found isolated vacua. They stabilized everything. They found a small positive cosmological constant. But since then, some people have been asking questions, can we really explicitly do that? Can we really control each aspect of this? And if not, can we somehow improve upon this? So this is a difficult task. Liam has paired up with a mathematician, I think, at Cornell. They wrote new computer code. They developed new methods of calculating things for Calabi-Yau. They try to make it more explicit, and he will talk about this. There are also many other ways of trying to construct de Sitter. So I think Pramod has been working on supergravity non-geometric setups and other things, trying to construct this. But this is very much an ongoing debate that we are facing here. I will not talk about this de Sitter at all. I just thought it fits here nicely, because usually if you compactify string theory, you can either get a positive cosmological constant, you can get 0, or you can get a negative cosmological constant. So there are only 3 choices. I will talk about the later 2 in this talk. The second one is Minkowski vacuum without mass scalar fields. That would be a 0 cosmological constant. You could put string theory on a torus, then you have 0 cosmological constant, you preserve a lot of supersymmetry, and you have massless scalar fields. What I want is something without massless scalar fields. And as far as I know, if you go back into the literature, the only thing that people have here is kind of M theory in 11 dimensions. That's not a string theory, it's not a compactification of string theory, but M theory would have no massless scalar fields. So we have been working on this, and I think we came up with a way of finding an example here. Maybe it's wrong, it's a year old, maybe people have objections. If you have objections, let me know, but I would kind of introduce here an example that goes against these conjectures that say this shouldn't exist in the swampland. So this says de Sitter doesn't exist, this says in supergravity, so maybe don't go against this. But there are some conjectures that shouldn't exist. And lastly, there's a conjecture that there are no scale-separated SUSY ADS vacua in string theory. To a large extent, there's a counterexample, or there's a counterexample by Liam also. I don't know whether he will mention that in 2021, where they worked out explicit KKLT type ADS vacua. There's now a recent paper by Alec Bedroya and Steinhardt where they say actually holography is not compatible with scale separation. So if that is true, you would never get scale separated ADS vacua. And if you don't know what scale separated is, I will explain that later on when we get to this part. But the main takeaway in the introduction, in string pheno, you want to connect to our world and you say, absolute minimal goal, I just compactify string theory, M theory, I get a lower dimensional effective field theory, and I don't have scalar fields at all. And in this case, I don't care. It's 2, 3 dimensions, 4 dimensions, 5 dimensions, 9 dimensions. I don't care about the amount of SUSYs. 32, 4, 0, doesn't really matter. I don't care about ADS, Minkowski, or de Sitter. And I would like to say, can we do this? Can we compactify really string theory, which lives usually in 9+1, or M theory 10+1 dimension, and get a lower dimensional effective field theory? And I think it's fair to say there's not a single example the community agrees on. So this is like a super basic task, right? If you open textbook, you put on a circle and you think everything works, and we just put on a bunch of circles. I just added here one extra qualifier without massless scalar fields. And I think there is not a single example where you can get the string pheno community to agree on. So that's why I believe it's important to work on those things, although not directly applicable to our universe, but they put things maybe slightly more on a solid footing and hopefully help us to better understand the landscape of string theory vacua. So I call this M theory like vacua, but it's essentially string theory on a Landau-Ginzburg model if you're an expert. If not, I'll tell you more or less what's going on throughout this section. So in moduli stabilization, what people have been doing in the past is usually we study particular parts of string theory in the supergravity limit where the coupling is weak, where the volume of the internal space is large. Maybe we have a lot of supersymmetry, and there we have a huge amount of control. But it comes at the price that it's not really generic. If you put really the most generic ingredients, you probably would break all SUSY. You probably wouldn't be at really large volume or weak coupling, and then it becomes complicated. And that is kind of this challenge we have to face in this whole endeavor. in order to understand the string landscape better and see where our universe might fit in. In terms of these Minkowski vacuum, people have been going back and exploring two worldsheet approaches where one can actually try to obtain 4D or any dimension, but vacuum with Minkowski. So one approach was asymmetric orbifolds. Asymmetric orbifolds have the advantage that you can project out a lot of moduli, so you kind of orbifold by groups and remove a lot of these fields you don't want. So this was recently revisited by those people. I think they haven't been able to remove all scalar fields. I think they have even a vector multiplied n equals 2, then you have a scalar field in there. I don't remember all the details, but there's ongoing work. They haven't fully succeeded, so I will focus on these Landau-Ginzburg models from the 90s. They essentially use in 2,2 worldsheet theory with central charge 9 to describe a Calabi-Yau compactification. And at certain points in moduli space, these can be described by a Gepner model where we can really do the calculation, calculate the superpotential, and in principle, everything we want to know. These were revisited in 2006 or 2007 by Becker, Walcher, and Buffer, and they actually included O-planes, and they included fluxes. So once you start threading the internal space with fluxes, there's a G3 flux, which is F3 and H3 flux combined with the axiodilaton. You can start stabilizing moduli. And this, I guess, Giddings, Kaczor, Polczynski, they noticed that with this Gukov-Waffer-Witten superpotential, you can stabilize complex structure moduli, the shape, and you can stabilize the axiodilaton, which is in here. But you can't really stabilize the volume, and then KKLT, they built upon that, and they stabilized the volume and try to find de Sitter vacuum. But what these people noticed in 2006 and 2007, and most people didn't care too much because we had KKLT and other stuff, they noticed for certain Gepner models, like the 1 to the 9 mod Z3 or 2 to the 6 mod Z4, there are actually no Kähler moduli. So these are mirror dual descriptions of a rigid Calabi-Yau. A rigid Calabi-Yau has no shape, no complex structure deformations. H2,1 is 0. And their dual has therefore H1,1, 0. So we don't have these Kähler moduli, so they are gone. So what you can actually do then, in principle, you can stabilize all these moduli only with fluxes, and you can find vacuum that don't have any flat directions. In principle, just back in the case, nobody worked out that explicitly, so we revisited it, or we revisited it, and people in Japan, Maria Grania, Paris, and Harvard people. So many, many people have revisited these models with, I think, interesting results, and I wanted to kind of mention what we found there and then pivot to ADS. So the interesting thing is that we can really explore a part of the moduli space that you usually cannot. Usually in these string compactifications, you want to be at weak coupling somewhere at the border of the moduli space where you somehow have control. Maybe you can use a supergravity. You certainly want to avoid string loops and so on. Here, for Minkowski vacuum, we don't need the Kähler potential, which receives a lot of corrections, string loop corrections. We only need the superpotential. We only need to demand that the superpotential vanishes and its first derivative. And we need to know that this Gukov-Waffer-Witten superpotential is exact. If you're familiar with KKLT, there is Euclidean D3 branes. There could be Euclidean D-1 branes, sorry, D-1 instantons. They could all correct the superpotential. But back in this paper, they have argued the Gukov-Waffer-Witten superpotential is exact, and or they have provided lots of arguments for that. And in our specific models, actually, there's a more recent paper where just the symmetries within this model forbid corrections, and you can prove this exactness essentially for the specific models we work with. But there is a general argument that it should be exact. So you have the exact superpotential. You don't need the Kähler potential. You can study therefore Minkowski vacuum at strong coupling, which normally you cannot because there's an infinite number of corrections. So this is something we started to do, and the one concept maybe which is slightly unusual that we found there is a stabilized field versus massive field. So if you have a scalar field, m squared, phi squared, m squared is the mass, and this would be kind of the potential, and the scalar field would sit at its minimum, and you say, yeah, it's massive, I have an isolated vacuum, and you're done with it. But what could happen, and what does actually happen in these moduli, is that some fields are massless, but still stable. So I didn't put any numbers here. So this could have been equally phi to the fourth. If this would be phi to the fourth, you calculate the mass, the second derivative, at the origin phi equals 0, and you find the mass is 0. So there could be scalar fields that are massless but stabilized, and this is something we find in these models as well. Can happen at any order, so sometimes happens at the next order, but could in principle happen at any arbitrary higher order. Good. So the first model which I mentioned there, which we studied in 2024, the 1 to the 9 mod Z3 model, that has a relatively small number of O3 planes. So when we turn on these fluxes to stabilize all these complex structure moduli, we run into a problem. They are inducing a charge that needs to be canceled via the F5 tadpole or D3 brane tadpole condition. And then we need to see how many O3 planes there are. And the best orientifold you can do has an orientifold contribution here of 12. So we can only turn on a very limited number of fluxes. And within that limited number of fluxes, it seems impossible to stabilize all 64 moduli. So not all possible flux choices have been worked out, but all flux choices we found, and like hundreds of different choices, they never stabilize all these moduli. So this does not seem to allow for sufficiently generic, complicated fluxes. However, in this model, one could potentially stabilize all fluxes, something those people worked on. And what we also found in this paper is that there are massless fields that get actually stabilized at some higher order. So there must be some kind of symmetry probably that forbids a mass term maybe, but that doesn't forbid higher order terms. So this paper essentially argues if you have some zeros in your potential or something like a zero mass, then there should be a symmetry for that, but more like an aside. This is not that super interesting. I wouldn't have talked about that by itself, given that's 2 years old. What is much more interesting is the other model, which is the 2 to the 6 model. And then on the other axis, I put the contribution of flux, F3 times H, and that can be up to 40 in this case. 40 is a dotted line here. Everything here is in principle a physical configuration where you can add some D-branes to cancel the tadpole. Everything here, you're overshooting the tadpole already with fluxes. There's no way to make that physical. Here would be kind of the threshold. And then each dot in there is a particular flux configuration. So you create different fluxes, make sure they're integer quantized, you calculate how much they contribute to the tadpole, and then you ask how many moduli are massive. So here somewhere maybe you have 9 and 18. There is, I think, one at 16 and 52 massive fields. And then for the people that are expert on this, there is a conjecture that actually says you can never stabilize more than 1/3. It's a refined tadpole conjecture. You can never get the flux divided by 3 as the number of stabilized fields. That is clearly violated in our case. So we see maybe a slightly slope here, but we get a factor of 1 over 6.8. It's not super important, but it's a question people were asking, can you actually stabilize all complex structure in general if you have a large number, and people didn't really know. And here clearly, if you see at 40, if you go up, we can actually stabilize all these moduli. This was, so I didn't zoom in there, but there are dots up here. All moduli are stabilized. You can stabilize 91 fields. You can do it within the tadpole bound of 40. So there are physical solutions where all fields are massive. And this was done at the same time. We were kind of racing together with these people. They found this one first, and we found that there's something which is 86.5 massive fields, and then there are 5 which are stabilized by something like this phi to the 4th. So they are massless, but they are stabilized. So they're both classes of isolated vacuum where everything is massive, or where some are not massive, but they also are stabilized. So definitely at large numbers, you can stabilize in these models all moduli, and you get for the n equals 1 M theory like Landau-Ginzburg models. There's also a follow-up paper by the Harvard group where they just use symmetry arguments, and they say based on symmetry, this is exactly what should happen. So I think there is strong evidence that this might be true. There are some issues. We can't calculate really the masses, but on generic grounds, I think they have to be all non-zero. I don't know whether they are really much smaller than the string scale or whether they're at the string scale, and then you run into issues. But in principle, there should be, I believe, in these Landau-Ginzburg model scales separated n equals 1 for the Minkowski vacuum. So I said already scale separated because that's the next point I wanted to come to in the last few minutes. Yeah, perfect, thank you. So we had already a lot of talks about holography, ADS-CFT. So if people care about holography, ADS-CFT, this is for you. If we compactify string theory, right, to describe our universe and to get maybe gravity in 4 dimensions, we need a compact internal space. So you might say, okay, wow, I just say ADS5 times S5. ADS5 times S5 is maybe a compactification because S5 is compact, but there is no lower dimensional effective theory. You can do a consistent truncation where you somehow truncate to the ADS5 theory or theory on ADS5. But whenever you notice, hey, I'm living in ADS5, this is a negative cosmological constant, you immediately see the KK scale. You see a whole tower of KK states at the order of the Hubble scale of this space. So our Hubble scale is absolute tiny. We don't see any KK scale. We have no indication of any extra dimension. So this is completely different from our universe. Because LADS5 is exactly the same as LS5. There is no scale separation between those two scales, and that means there is no lower dimensional theory to talk about that is in ADS. That's not a problem for the Minkowski we just talked about before, because Minkowski space is infinite. So that would be infinite, that is larger. For ADS, we want this larger, but it's not the case here. Okay, there is actually very recently, or not recently, but 2-3 years ago, a conjecture that this is a universal property of ADS-CFT. So there's a lot of work going on right now in this area. Some people do the supergravity like me, but other people do CFT and holography, trying to understand this. So Yao, Buffer, they conjecture that this property is essentially universal for all compactifications. And yeah, they give a lot of examples, and I think there's also some mass literature that tells you how the curvature relates to this. I'll come to that in a second. But essentially, if you would have scale separation, there would have to be a huge gap in this operator dimension between the lightest modes and the next one. And they say this never happens because they bound this dimension of this operator. This can't be arbitrarily far away. And this means essentially, yeah, that the internal space has essentially a diameter which is related to the ADS. And this is somewhat separate. There's also a follow-up paper in November. They say essentially holography as a concept is inconsistent with scale separation. And that would be very dramatic to me, at least, because to me it doesn't really matter whether we're in a positive or negative cosmological constant. If you had a cosmological constant that is minus 10 to the minus 120 m Planck to the 4, we probably wouldn't notice much of a difference. It just happened to be positive to me. But if that's what they are saying, everything is completely different in ADS, if that is true. Good. So one reason which we discussed in this paper, why you run into these issues is the curvature. So if you integrate the S5, for example, over the Ricci scalar from the S5, what you find, for example, in ADS5 is that the Ricci scalar goes like 1 over the LKK scale, and then on dimensional grounds, the mass of the KK tower exactly scales in the same way. So if you put those together, you generically have no scale separation. If this curvature term is there and it's somehow relevant, that sets the Hubble scale. If the Hubble scale is 1 over LKK and the MKK is also 1 over LKK, then they're always of the same order. That tells you essentially you never have scale separation. You can maybe ask, can I get this thing on top super tiny? I think there are no spaces known. Unless you make this somehow moduli dependent on other scalar fields, then it becomes slightly more complicated. But generically, if you take any kind of brain stack and then you try to do the usual ADS CFT, where you have some kind of Calabi-Yau, that is some cone over some curved space, then you always run into this issue. And this is completely independent of the dimension. So whether we are 9 dimensions, 3 dimensions, 8 dimensions, doesn't really matter. Completely independent whether you're at strong coupling, weak coupling, or what the value of LKK actually is. So this is a relatively strong universal argument, and maybe that is the reason why it doesn't really work. I don't know. But same as de Sitter, there are kind of counter examples. So usually the ADS is obtained from this flux minus this curvature, and I put here absolute values just to make sure that the curvature contributes negatively. So, and I said the curvature essentially prevents scale separation. So the question is, how did we ever, can we ever obtain scale separation? I said Liam has a paper there, but I mean, in KKLT, in principle, the ADS vacuum violated this, and similarly other construction. They all do that by essentially not having any curvature there. If you don't have the curvature, you don't have the problem from the previous slide. There's a famous paper by De Wolf, Gerjavitz, Katshu, Taylor. As I said, Liam revisited and Pramod also revisited it. What I revisited with my postdoc is something which is actually ADS3. So it's a 3-dimensional solution, which is not our universe, but then it has the advantage it has a CFT dual, if there is one. And yeah, so there are these vacua that don't have this curvature. I don't know what it means for the dual CFTs. Can you construct out of brains something? For all of these examples, we do not really understand what the dual CFT here is. The way these get actually ADS is via O-planes. O-planes scale in a completely different way. If you calculate the Hubble scale, the O-plane play a role. You find actually that this ratio goes like the string coupling divided by the KK scale in string units. So the string coupling we usually want to have small in supergravity, and we want the KK scale large in string units to trust supergravity. So here we are doing right now supergravity, not string theory or Gepner models. But that is actually coming kind of for free. Whenever we are in the supergravity limit, we automatically have scale separation. So here, these examples, everything is kind of consistent. And the O-planes give a negative contribution. They have negative tension. Some people tried also to use Casimir energy. We need somehow to get ADS vacuum. We need a negative contribution, and the fluxes always contribute positive. Curvature we don't want. It doesn't give scale separation. O-planes seem to work. Casimir energy also gives negative, but all scale-separated vacua so far are kind of unstable. They are non-supersymmetric, so they are unstable. But there is a whole bunch of compactifications of type 2 on G2 spaces that give ADS3 vacua. And those we have recently revisited, in particular here with Muthusamy Rajaguru, and there we found that there are some examples where we can include O5 or 9 planes. We get an ADS3 vacuum, and these vacua are then S-dual to the heterotic string. So we worked out some explicit ADS3 vacua in the heterotic string where you have parametric control. So you have a flux, you can send the flux to infinity, or you have 2 fluxes, you get weak coupling, you get large volume, and you get parametric scale separation. So in principle, these examples go against these conjectures, but they use these O-planes. Once you add these O-planes, you can solve the equations explicitly. You sometimes smear them. You do some approximations. So we don't really know. Are these examples okay because they're in parametric control and we understand pretty much everything we do and we think they're okay? Or is there some kind of issue with holography, and how do we see that explicitly in these models? That is kind of the ongoing debate in ADS-CFT holography scale separation that we don't have a good answer to. But the hope is maybe these heterotic string theories solutions we found here, they don't have RR flux. So one can in principle study them from the world sheet. And since these are all ADS3, maybe one can also understand something about the dual CFT too. So I don't know anything about that, but if anybody knows the CFT and you can make the gap parametrically large, that would be truly amazing. If you have a proof that you can't do it, that would mean these vacuums are wrong, would also be very interesting. Okay, so this brings me to the end. So I said one can study N=1 Minkowski vacuum at strong coupling, and we found isolated vacuums, but they still had massless fields. What you really want is only massive fields. That was discovered by those people in the paper at the same time. And then the other interesting thing for me right now is this ADS-CFT versus scale separation. So can we really make the internal space small in any kind of ADS-CFT construction? If yes, how, and how does it work from this dual CFT? If no, why can't we do that? Why doesn't that work? Okay, thank you.
Questions?
Hi. So the supergravity that you have for ADS3, do you have the spectrum of all the scalars and the 3-point function? So can't you read the CFT states from there? You said that you have constructed a ADS3.
Yes.
So don't you have all the field config, the Lagrangian there? What are the fields and how do they interact, all the vertex contact terms?
I don't know. I have some light fields.
But can't you read the CFT scaling dimension from there?
The of those massless, massive, yeah, of course.
But there are massive fields too.
Yeah, no, sorry. So here essentially, so before you turn on all these fluxes, they are massless, right? We're looking at the massless modes, but then we turn on the fluxes, they become massive. And we can read off all the conformal operator dimensions. They are actually integers in some cases, which we don't quite understand, I think. We can calculate those dimensions, but I don't know whether that is sufficient to construct a CFT.
So in the known, in the known list of 2D CFT, you didn't find any such CFT with these.
I did not look for that. I just know for all of these constructions, whether it's 3 or 4D, people have never that know what they're doing. So I'm just a supergravity person, but people that know what they're doing have not been able ever to construct a dual CFT. So they have sometimes replaced the fluxes with branes, and then from the branes try to read off some properties of the CFT. And they often found things that they couldn't understand, and often they came to the conclusion there shouldn't be such a CFT or something like this. Yeah.
And just one more thing, in your ADS3, there is no D-brane. I thought it's just M theory with G2, with no, and just show planes. Is it correct?
There is no?
D-branes, just you are compactifying on G2 manifold and putting some more orientifold.
Yes. I mean, so here, for example, for the O9 branes, there would be D branes that would be dual to the...
In the last example. In the
here. In the last one?
Yeah.
Sorry. Here, yeah, this is a heterotic. This is only heterotic string theory. You just have the gauge field with the SO32 or E8 times the 8 group. There is no D branes or NS5 branes or anything like that. Yeah.
Okay. Because I was asking because you were saying that people are able to read off the dual CFT by looking at the brane web.
Sometimes when you turn on these fluxes, people have a way of placing D branes and then taking some limit where they turn into fluxes. And then, so essentially you can go backwards, remove the fluxes, and from there only have a D branes intersecting in a particular way and try from there to reconstruct the CFT.
Okay.
But our constructions do not have the D branes. Yeah.
Okay, thanks.
Yeah.
Hello. Yeah. Hi. Yeah. So thanks for the nice talk. So I have like a question and a comment. So by noise scale structure, we understand that, because we are considering the models which are mirror to the rigid Calabi-Yau, so they don't have any notion of geometric volume. So as we kind of name this so-called say noise scale structure, that means we don't have the volume, so we don't fix. So in that sense, isn't it confusing to talk about like scale separation? We don't have the notion of geometric volume. So that's something which I am confused with, because the noise scale is the root of this scaling. And the second part, which the question is, if we consider the open string moduli, do you think that the things would be different? Because for your case, you just have the complex structure moduli, and that's your dilaton. right? Fixed by the book of alphabetum. So in that sense, I mean, I would say the source of these moduli to be the same order of superpotential. So in that case, maybe the scale separation is not very much anticipated also, right? Unless you have different kinds of moduli, it may be accidental that they are getting the same order mass and no scale separation. So would you more comment some more on these two? Thank you.
So yeah, perfect. So I think the main goal I want to achieve is getting a lower dimensional effective theory. So scale separation in the sense that no KK tower, no string tower, no whatever complex structure, right? If I deform complex structure, I guess. For Minkowski, I think I always achieve that because I can always put my bound as low as I want because Minkowski has zero cosmological constant. For ADS, I can't make my cutoff arbitrarily small. So I would say in Minkowski, whenever I have a compactification to Minkowski, I have scale separation in the sense, doesn't matter whether it's really a KK tower from a volume or from a complex structure or from the string tower, they all can be decoupled. I'm sorry. And what was the other part of it?
So other was like if you include the open string moduli.
So I think in those cases here, where you really go to 40, there wouldn't be any open string moduli because you don't need any D-branes or anything.
Okay.
There shouldn't be any. So you just put fluxes, cancel 40, and they're only O-planes.
No, I'm asking if you include it. So it is like the simplistic allowed case in which if you don't want, you don't include. But if I want to include, for example,
yes, you can include
because
it.
the model may be oversimplified. I would say it's like, even DGKT is like oversimplified. You don't have any complex structure. So if I want to include, then you think that situation may change because
I don't know. I have no idea. It's a very good question. I don't know exactly how to include it here, but in principle, one can include the D3 branes, and in some of these examples here, definitely one can do it, and one would have to study their spectrum. It could be even massless. I have no idea. I wouldn't know what stabilizes them.
Okay. Thanks a lot. Thank you.
Okay, let's thank Tim again. Okay, let's have Renan now on a talk titled Four-Dimensional Spectrum Generating Algebra for the Superstring.
Hello. So thank you for the organizers for inviting me. My talk today about this four-dimensional spectrum generating algebra is probably the more old school one today. It's about first quantized string theory. And I'm going to talk about this work here that I did with a student in Prague, Aravinan, Sydney Vasan, and he's applying for postdocs now, in case you're interested. Okay, I didn't include references on the slides, but they're all here in this paper. So if you want to look at any reference, you can ask me directly or just look there in the paper. Okay, motivation. This is the outline of the talk. I will start with some motivation. I'll try to be basic without many equations until some point. And then from that point, there will be a lot of equations. But they're not going to be very important. They have to be there because they are the main result. But you just need to understand some of their properties. I'm going to do some connection to phenomenology, but of course, I'm not a string phenomenologist. I'm not specialist in compactifications or anything of the type. And then I'm going to switch to these DDF operators. I think some of you, if not all of you, have heard of it. And then I'll jump to this hybrid superstring formalism. You might know RNS, the spinning string, Green-Schwarz formalism, pure spinners. But this hybrid, as far as I know, is one of the least known superstring formalisms. In particular because it's more focused on 4 dimensions and 6 dimensions. And then towards these DDF operators, I'm going to discuss the massless vertex operators, how to build this string spectrum in these formulas, and then jump to DDF algebra. I'll show some partition functions. But the overall goal, I think, is to try to establish some systematic approach to investigate string scattering with 4-dimensional physics manifest. Okay, so we all know that superstring theory needs 10 space-time dimensions. You can believe that or not, but it's something that comes out of the self-consist of the theory. But we, of course, see only 4 space-time dimensions. And then there are different proposals to explain this mismatch, what we see and what we expect from superstring theory. And compactification is the simplest explanation. There are other large extra dimension scenarios, like these ones from Nimar Cunningham-Head, and then random pseudo models and so on. But definitely the simplest one is compactification. And if you are interested in phenomenology, you want some experimental constraints. They are very stringent, but the problem with these models is that they are very dependent on parameters and different ways of building them. So this kind of falls into this string landscape, which is huge. We have too many, let's say, parameters, too many different compactifications to build on to try to get some results that at least resemble our own universe. And then from this perspective, it would be very interesting to try to have some superstring model where the 4-dimensional physics is manifest. I'm still keeping some minimal supersymmetry because we don't want to make things too complicated. But the idea is to try to do superstrings with 4-dimensional physics manifest. So the problem with these formulas that I already mentioned, RNS, Green-Schwarz, and pure spinors, is that they are built on 10 dimensions, and anything going below that rely on compactification. And in these formulas, if you want to bring it to 4 dimensions, these compactifications, they bring extra ingredients that are a bit hard to deal with. I'll go back to it in due time. But in 1994, Nathan Bergwitz came up with, well, there are 2 papers. The first one was, I think, 1993, and then a follow-up paper with Kurumvafa, 94, where they describe a way to build a superstring formalism precisely with these ingredients in mind, 4 dimensions or 6 dimensions with minimal supersymmetry. And then another idea to have these 4 dimensions manifest is maybe to try and get some help from all these nice scattering amplitudes models that we have available today that build on 4-dimensional structures, like twistors and spinor helist. Okay. So one slide to get to DDF operators is that we have to kind of understand a bit that there is a huge difference between massless and massive states in string theory. If you do any study of scattering amplitudes, either in field theory or string theory, you're going to see that at least at 3 level, for instance, many of these results are for massless theories. As soon as you put mass there, most of these general structures that we see, very nice properties, they cannot break down. But it's interesting because in string theory, these massive states, they're all there, and they indeed can be obtained from the massless ones. So let's say if you take 2 massless vertex operators in string theory, and you just start computing OPs, you're going to see there the appearance of massive vertex operators. So if you know how to build, for instance, a 3-level scattering amplitude in string theory, I didn't put here the integration over the modular space. The integration over disease. You're going to see factorization channels, and you're going to get, at some point, massive states. So I'm just putting here very schematically. a bunch of massless states in some factorization channel, you get a massive vertex operator. So in principle, if you have an endpoint massless scattering amplitude in string theory, you should be able to get massive ones also. The question is how to do this systematically. I'm not going to give the answer, but that's the motivation. And regarding this operation that I kind of schematically wrote here, there's a very known procedure called DDF operators. So they're named after Giudici, Dweck, and Fubini. They are from the 80s, and the idea is very simple. Essentially to build a creation annihilation algebra out of these massless vertex operators. So I believe most of you have seen here the massless vertex operator in the bosonic string. So this is the one here. I have some polarization. I forgot to put the C ghost here, so that would be the unintegrated vertex operator. And if I put here the integral, that would be the integrated vertex operator. So I have here some polarization. It's transversal and it's massless. So this is the kind of the photon of the open string, or you can think of it as the left moving part of the graviton. So the DDF operators are essentially using this massless vertex operator in a gauge fixed form and in a specific frame. So here, out of the 10 components of my polarization, if I'm in the superstring, I have here only 8. These are the independent components, like 8 degrees of freedom. And I have here some specific frame direction. This is massless. I'm doing some light cone decomposition. So this is an integrated vertex operator associated to the photon. It's interesting that if you start working with it, these operators satisfy a very nice algebra. It looks like a creation annihilation algebra, as long as you're acting on a ground state that has non-zero momentum in the x minus direction. So it's something very easy to compute. You essentially compute the OPEs between the two vertex operators, and you get something here on the side that I forgot to write. It's an integration over dx plus. That's non-zero when acting on this vertex operator here, for instance. And this one, if you know, is the tachyon. Something that has a negative mass square. So it's the least exciter, or the ground state, if you want, of the string spectrum. And if you want to build higher mass levels, you just start acting on the ground state. So if you act with the operator 1, index n, here 1, you get again the photon. If you act with, for instance, V1, V1, or 1, V2, you get the second mass level, and so on. So any string state in the physical state, that means in the BRC homology, can be built out of these operators. So there's a nice decomposition. The drawback is that you're going to the light cone directions here. So it's a specific frame, and it's already gauge fixed. So if you want to do this in superstring theory, it gets a bit messier. And there are different reasons depending on the formulas that you choose. For the RNS superstring, you might have heard that if you want to build vertex operators in the R sector, that means that you want to include fermions, you have to deal with picture chaining operators, for instance. And it's a bit impractical to have these picture chaining operators built inside a creation annihilation algebra. So if you try to pile in this construction here of vertex operators, if any of the creation operators has a picture, you're going to build a vertex operator here with like huge picture number that you have to invert later on. So it's not very systematic. For the Green-Schwarz superstring, the DDF algebra doesn't really make sense because you're gauge fixing the worksheet action such that this x plus and x minus direction, they're not dynamical anymore. So even this DDF algebra doesn't have a meaning there. And for the Pierce spinor formalism, there is a DDF construction. We're using SOH superfields. But again, if you want to try to bring it down to 4 dimensions, you have to do all these decompositions to decos 4. But then there's another complication there, that's the Pierce spinor ghost. So if you don't know what it is, it's just some bosonic spinner that has some nonlinear constraints. Yeah, so it's a bit hard to deal with them when you do compactification. Yeah, so why do we care about these supersymmetric DDF operators? The bosonic ones, they work well. So why do we need more? I think one of the motivations that has been a recent revival of these DDF operators in string scattering literature. So there are some works from Rosenhaus, David Gross, Maximo Bianchi, and other collaborators, where they try to study chaos in superstring scattering, and they use precisely these DDF operators. And one thing that they do, for instance, is to define a new measure for chaos. They do this by looking at for instance, at the values of scattering amplitudes for these higher massive modes, and then if you map the distance between this minima or the maxima, you can see some kind of chaotic behavior. Another thing people are doing is these highly excited strings. Yeah, so these are very massive string operators. There are also coherent states, and okay, there's some nice examples that are getting more popular recently. But the problem is that most of them deal with the bosonic string or the NS sector of the superstring. Yeah? So there's not really a supersymmetric treatment of these results. And in addition to that, there has been an increase in gravitational wave scattering by black holes. People are trying to get some, let's say, some black hole scattering behavior by looking at scattering of massive states in string theory. Yeah? And these massive states, they have to be higher spin. So at some point, they're going to have some classical limit or the spin goes to infinity. And of course, these results are in d equals 4. Yeah, so these results are in high demand. Other applications I put here, just ADS, CFT, even string field theory. ADS, CFT, in ADS3, CFT2, people have used the hybrid string, but not the one that I'm discussing, is the d equals 6 version. Okay, so this is how why we care about these supersymmetric DDF operators. So if you have seen RNS formalism, I'm trying to, I hope I'm not being too basic here. So there are some matter variables, the target space coordinates of the string, the supersymmetric partner, the worksheet supersymmetric partner, ISM. Then you have these ghost variables. They come from fixing the super reparameterization gauge redundancy of the worksheet action. If you have seen the BRC charge, it's very similar to the bosonic string plus a supersymmetric part. Yeah? So this is the energy momentum tensor, and this is the supersym generating the worksheet plus ghosts. One important ingredient that I'm going to come back later on is that the B ghost. The B ghost is the quantity that you can say trivializes the energy momentum tensor. So these things are of course related. So the T that appears here is the same T that appears here. And it's because the gauge generators, they are BRC exact. And one thing that we have to keep in mind when working with this RNS superstring is that most of the times we're working on what we call the small Hilbert space. Essentially, any physical state that I build here, it cannot depend on the zero mode of the fermionized ghost Xi. Okay, this was just for reference, and what happens in the hybrid formalism. The hybrid formalism will pick the RNS formalism, do field redefinitions, similarity transformations, and a U1 twist. You don't have to know how they are, because I'm going to show how is the field content there. But you see, it's not something that you derive from first principles. So you get RNS, and then you start messing with it, but you get something nice at the end. So this field redefinition involves the d equals 4 spin fields. Spin fields, they would be, for instance, appearing in the R sector cohomology of the RNS superstring. And then similarity transformations, they mix matter and ghost fields. Yeah? So it's something very unusual. Here, this distinction is very clear. XM and psi are matter fields, and the ghost variables are these ones. But in the spinning string, this distinction gets a bit fuzzy. So here is how it breaks down. Yeah? So you have this field content, worksheet field content in the in the RNS superstring, and I put there the center charges. For each one, you see they add to 0, and this is what you get for the hybrid formalism. So you have here four dimensions x mu, then you have here 6. I goes from 1 to 3. So you have the 10 target space coordinates. I'm not doing any compactification yet. So you have these extra variables that if you have seen Bagger books on supersymmetry, you would recognize. So these are n equals 1 superspace variables. Then you have this psi and psi bar. They of course come from this psi's from the RNS, but there's a twist there. This is U1 twist that I missed. And then there's this extra Cairo scalar, which is a very weird ingredient. The other ones, they're kind of easy to justify if you know a bit of RNS, but this one here is a bit unexpected. So in this RNS formulas, these U1 currents that you see, the ghost number or picture number, they come from the ghosts. In the hybrid string, this U1 current is this one. You see that psi and psi bar, they appear there as matter variables. I mean, they were matter variables. Okay, so as I mentioned here, like because of this field content, you see at least the 4-dimensional physics, there is some hope to make it manifest, and this is indeed what happens. So again, I'm just trying to revise some of the questions from not really Bagger, but kind of a realization of the charges there. So I have here some supersymmetry generator, Q alpha. Alpha is just a spinor index in 4 dimensions. It's a Cairo spinor index. So alpha equals 1 or 2. In our case here, it's going to be plus and minus. And then they satisfy this supersymmetry algebra. Here is just the momentum operator. Yeah? And you have this invariance. Again, you probably have seen, if you have seen any pure spinor computations, you might recognize them. And this is how you get from those simple ones here, Q and B and eta, which are fundamental, you get to these quantities here. And these are the ones that you use to build the formalism. See here the BRC charge e to the whole d square. D is just d that you see here, d alpha, d beta contracted. B is not fundamental anymore. And I have also eta. So these things, because of the field definitions that you did, they are not fundamental fields anymore. I mentioned here, but we'll come back to this. That just like in RNS, the BRC charge and the eta ghost, they have a trivial cohomology, and so that's why I have to go to the small Hilbert space or define a combined BRC charge. Yeah. So in the hybrid formulas, the spectrum is defined like this. Yeah. So it's something that has to be annihilated by both Q and eta 0. This would be the small Hilbert space in the RNS superstring. Yeah. And I'm going to consider here this U1 charge that I wrote before, this one. So my physical states, they have U1 charge plus 1. Yeah. So I'm going to build them like this. So physical vertices are going to be eta 0 exact and annihilated by the BRC charge. Yeah. So there is some kind of gauge redundancy here because physical states they can define by a Q exact quantity. This phi here that I'm using to define the physical state can also be defined up to a eta 0 exact state, because otherwise it's going to be eta 0 square, which is 0. And physical states cannot be BRC exact. Yeah? And in order to make this 4-dimensional physics manifest, I'm going to boost all the momenta that I might have in the 6D dimensions to the 4 dimensions. Yeah? So momenta in the 6th dimension, they're 0. Okay, so now there are bigger questions coming. Don't be scared, but I have to show them. Yeah? So let's look at the vertices with the 4-dimensional matter variables explicit. So I take here some eta 0 exact state. This V here is just a superfield. And when I apply eta 0 on it, I get this whole expression here, which is very ugly, doesn't look very promising. But when you impose BRC closedness, you get these equations here. Again, if you have seen Vespagger, these are the equations for n equals 1 supermaximum. So you see there, in this state, it contains two bosonic and two fermionic degrees of freedom, which are the supermaximum, contain the supermaximum superfield. And you have here also the integrated version. So if I want the integrated vertex, I just put an integral here. And again, if you have seen pure spinor formulas, this would be very, very familiar, or even Siegel's construction from the 80s, how to define the vertex operator in superstring. See, there's the d theta times some superfield A alpha, there is d alpha, d bar alpha, and pi n. So these are only 2 plus 2. If you're looking at the superstring, you need 8 plus 8, so there are 6 missing. They come from the other directions that are say, non-singlets with respect to rotations in the I directions, in the 6 directions. So this U here would be the integrated vertex operator, no, sorry, it would be the vertex operator for the extra degrees of freedom. If you impose annihilation by the BRST charge, you get these equations here. And again, if you have seen Vespagger, these are the equations of motion for the chiral and anti-chiral superfields. So I here goes from 1 to 3. I have 2 sets, so I have 6 bosons and 6 fermis, as expected. Okay? And again, I have here the 6-dimensional vertex operator, integrated. For the DDF operators, as I said before, we have to go to a specific frame and a gauge fixed version. So I'm going to make this decomposition here. And this is what I get for the ground states. What are the ground states? Before in the boson string, it was the tachyon, unintegrated vertex. And these are the unintegrated vertex operators that I showed before. These one, U6D and U4D. But in a specific frame, already gauge fixed. So I already made here some state operator equivalent. So I have here the 2 circular polarizations of the photon, for instance. They're super partners, photinos, and then the scalars in the 6th dimension here, I and I bar, with their super partners. You don't need to memorize the equations, just keep in mind that these are the ground states for the RNS superstring. And these are the integrated vertex operators. Again, keeping the DDF framework in mind. I'm making a gauge choice, and I'm making a specific choice for the frame here. So these explanations here, I think the important part is I to the in x plus. So they are in a specific Latcon direction. And the other things are there because these are superfields. It's just a different way of organizing them. Theta plus, theta minus are just the 2 components of theta alpha, as well as theta bar plus and theta bar minus are the 2 components of theta bar alpha dot. Okay, so 2 things to emphasize. So the 4-dimensional structure here is manifest, and it's everything supersymmetric, so in terms of superfields, and it's kind of a helicity basis. So these 2 here, I come back to this later. Okay, and the nice thing is that these complicated operators that you have here, they satisfy a very nice algebra, just like the DDF algebra that you had before. So you can think of this as a creation-annihilation algebra when you're acting on states that have non-trivial direction in x minus. So this phi and phi bar is just the polarization that you had inside the integrated vertex operators. Nothing, they're just constants. If you want, you can decompose A bar and A into an operator times phi and an operator times phi bar, and then you can define the algebra as you would see traditionally in a creation-annihilation algebra. And any state in the cohomology can be written like this. So you just take powers of these operators here, acting on some ground state. This is very schematically written. So any superstring state, you can write in this way with the like this four-dimensional physics more manifest. Before getting there, I'm just going to show you some partition functions, and then I'll get to the point where I explain why these results can be relevant. So if you compute partition function for these states, the usual one, the one that you get from, for instance, to compute the vacuum partition function, the one loop one in the superstring, it's 0. It's essentially because you have not broken supersymmetry, so you have an equal number of bosons and fermions. Okay, so this is, of course, is expected to be 0. I haven't broken supersymmetry yet. But if you want to look at the mass partition function, you just remove this kind of Witten operator here, the fermionic number, and you get what you expect from the superstring. So there's a one-to-one correspondence between states in the usual superstring formulas and the hybrid string. But one that may be more interesting is the helicity partition function. So if you look at all these decompositions, you can assign helicity to all the operators, x, x bar, theta plus, theta minus, and so on. And this is a result you get. In principle, you could get this from, for instance, from the Green-Schwarz superstring, but again, the correspondence to the vertex operators would be a bit clouded. This is why here is just a variable that I'm using to keep track of the helicity. And if I want to get to the first one here, I just make y equals -1. Because this I to the 2h would correspond to the fermionic number. So you see when y equals -1, it's 0. These things, they might be more interesting when you have supersymmetry breaking. I'm presenting here only the kind of flat 6-dimensional decomposition, but of course we can try to, and this was the original motivation of Nathan, to try to understand the Calabi-Yau compactifications, for instance. And then you can have something more interesting coming out of this. But I think this result is already interesting because you're associating some helicity decomposition directly to vertex operators in the superstring formalism. So I might try to understand how these superspace descriptions fit into the helicity decomposition. Okay. So just some final remarks. There's a one-to-one match between these physical states, and you would expect that because, of course, they're coming from the RNS formalism. But it's nice because now you have these superstring vertex operators into some helicity basis for dimension. One thing that I would like to explore in the future is to try to covariantize this construction, but in the following sense. Instead of having these plus and minus directions that are just from the beginning, I can use two arbitrary vectors to parameterize the light cone directions, and this could be more useful in the construction of let's see, more covariant methods, but also in the connection to spinor helicity formalism. There you have also reference vectors, and it would be very nice to connect them and try to use the tools that you have there in also in the superstring scattering. One thing that I also like to explore later is some phenomenology in these models. Because, again, four-dimensional physics is manifest, and what to do with the 6 dimensions. So you might have heard, for instance, of these T6 over C3 orbifolds. They were very popular in the 80s. And there's a paper from, Harvey, Dijkson, Buff, and Witten, where they do this heterotic superstring in these orbifolds, and they get some very nice, not correspondence, but nice match with what you'd expect from like standard model multiplets, super multiplets. Yeah? And the interesting thing is that in these T6 over Z3 orbifolds, all this free CFT machinery is useful and can still be used in this DDF construction. And again, for references, please look at this paper here. And you can have all these basic references nicely pointed out there. And that's it. Thank you.
Questions?
Thank you for a very nice talk. Can you, so this is a remedial question perhaps. So how easy or difficult is it to treat different types of backgrounds with this formalism, in particular background RR fluxes?
Okay, it's a fair question. So all that I did here was for a 6-dimensional flat variable. So the way the formulas were originally built, you use different variables, not really this size that I'm writing here, but there are some other variables that are better suited to describe Calabi-Yau compactifications. If you look at one of the original references from Nathan from 1993, you're going to see that he doesn't mention flat space. It's all directed to Calabi-Yau. I decided to do flat space because then you can see the construction of the vertex operators more clearly.
Can one compute, let's say, spectrum somewhat explicitly or scattering amplitude somewhat explicitly for these non-trivial backgrounds?
That's a good question. So this is what's coming next, because in particular for that T6 over Z3 manifold, I still have the free CFTs. So I expect this machinery to translate more smoothly there. Again, because of the free CFTs. I have to use these twist operators because of the orbifold, but other than that, I think it could be very systematic.
But do you think the spectrum would change in a non-trivial fashion, or it would be projection? Because after all,
it would. That's a fair question. I'm afraid to commit to this answer. So I think you would reproduce what has already been done, but again, in a more systematic way. The question is what you can do about it, and then the idea would be to connect to these nice results that are popping on DDF operators. Thank you.
Any other quick question? Okay, then let's thank Renan again.
Thank you.
Okay, so the final talk of the day is by Shubham Datta Chaudhary on symmetry and causality constraints on Fermi liquids.
Thanks to the organizers for inviting me to this wonderful conference. So I'll be talking about this work which came out earlier this year with Luca Della Creta, who is at University of Chicago, and Umang Mehta, who is at University of Minnesota. So the plan of the talk will be like, I'll first provide a motivation behind why I'm doing what I'm doing, followed by a lightning review of Fermi liquid theory as an effective field theory, and then I'll impose symmetry and causality constraints on this effective field theory, followed by conclusion. And if time permits, I'll possibly also go over some sort of nonlinear constraints that also we get. So to motivate the problem, we know that conformal field theories are central to our understanding of both condensed matter as well as high energy physics. An interesting question that one can ask is that suppose you have a conformal field theory with a global Levon symmetry, and you consider states at finite chemical potential, okay? That is states at finite density. Typically, evaluating the CFT in such states leads to a spontaneous breaking of both the Lorentz as well as conformal symmetry, and you arrive at a plethora of rich phases in the IR. For example, you might break the U1 symmetry of the CFT might be spontaneously broken, and in the IR, you might have a superfluid phase with zero viscosity. You could also, and in such a situation, the low energy superfluid phase is described as an EFT of a massless Goldstone boson, which is the Goldstone boson of the spontaneously broken Yuan symmetry. You could also not break the Yuan symmetry, but you break the translational symmetry, in which the IR organizes itself into a crystalline structure with periodic lattice-like structure. And or you could not break anything at all, like you have Yuan symmetry, rotational as well as translational symmetry, and you recover a Fermi surface in the IR. Okay, so conformal field theories at finite chemical potential, therefore, like is a very rich lab to explore all these phases of matter, and all of these phases are described by effective field theories. And as we all know, effective field theories have Wilson coefficients, which parameterize our ignorance about the microscopic theory from which they arise. So my goal is, can we put any constraints on these Wilson coefficients, assuming very minimal things about the UV CFT? Okay, so that is the goal of the problem, and this is pretty standard in our community. For example, like it is well known that not all effective field theories have good UV completions. And this is manifest in the object S matrix, analyticity of the analytic properties of the S matrix, which should obey some standard axioms of quantum field theory, such as unitarity and causality. Okay, so if we have, like, if you vary the EFT parameters arbitrarily, you essentially end up violating some of these assumptions, some of these axioms of quantum field theory, and that's how one is led to these constraints. Okay, and so for this rich non-relativistic phases of matter that I just described to you that arise from CFTs, a similar question can be like, can any such IR phase be reached in this manner? And because it's non-relativistic, we don't have access to scattering amplitudes or S matrices as such, but I'll try to convince you that indeed there are observables which still can be used to put such constraints, and indeed the and symmetry and causality definitely constrain the EFT parameters pretty strongly. Okay, and for concreteness, I'll focus on CFTs which enter a Fermi liquid low energy phase in 2+1 dimensions. Okay. Yeah. Yeah.
And when you say causality, you have a different notion of causality?
No. These are non-relativistic, but the Lorentz invariance is spontaneous. I mean, it's spontaneously broken, so it's non-linearly realized. So it's usual causality. It's just that you are using. It will become clear in a moment that you're just using the usual notion of microcausality, but in a since it's an operator statement, but you are using it in a finite density state. That's it. The UV is still, yeah. Okay. Okay. So Fermi liquids represent one of the most robust finite density phases of matter, and they occur in many places, starting from liquid helium to interior of neutron stars, which is synonymous with low temperature, high density QCD. And they are often characterized, and basically like despite strong interactions, they can somewhat be modeled by free electrons with renormalized properties, and that leads to robust predictions for transport and like thermodynamic properties. Okay, they are characterized by certain peculiar features such as linear in temperature, specific heat, some anomalously large entanglement entropy, and also the symmetries are, it has an unbroken U1 symmetry, it also has translational and rotational symmetry. Okay. Okay, so let me briefly review Fermi liquid theory. The starting point is you start with a system of non-interacting free non-relativistic fermions, and from our quantum mechanics course we know that once we start solving the many-body wave function, we start filling up the Fermi sphere with a definite Fermi momenta, which is given by Kf. Okay, and instead of working with the many-body wave function, the object that one looks at is the phase space density, which is denoted by this, and it takes the value 0 if momenta is greater than if it's outside the Fermi surface. It's 1 if momenta is inside the Fermi surface at 0 temperature. Okay. And excitations of this system correspond to excitations of this excitations around this spherical ground state, which you can visualize as like perturbations of this spherical shape, basically. Okay, and there you can write down the equation which governs the time evolution of these excitations. This is given by Landau's kinetic equation, which is this, where H is composed of the energy of the excitation, and Vx is some external potential that you apply. Okay. Now this is all for free fermions, but Landau's key insight was that, well, when you turn on interactions adiabatically, some amount of this picture still persists. You still can, you still have, you can still model, you can still think of this as free electrons, but with modified dispersion relations, okay, which take into account the effect of the surrounding medium. So for example, like these excitations are now, they now make sense very near the Fermi surface. It's only a very small slice above the, around the Fermi momenta. And this, if you look at the Hamiltonian, this quasi-particle energy, the particles are now labeled as quasi-particles because it also, their dispersion also involves the effect of the surrounding medium as well. Okay, so one can think of this f function, which is a function of momenta p and p prime, as the Wilson coefficients of our theory. Okay, so they encode the interactions of the surrounding medium, and this is the quantity that we want to constrain. Okay. Any questions so far? Okay. So now this feels like an effective field theory. So the way Landau interpreted it, so efforts to actually elevate it to the status of a proper effective field theory in form of an action has, people have been looking at it for a while. It starts with the seminal work of Polchinski and Shankar, and a more recent viewpoint of this, is to parameterize the deformations of the spherical Fermi surface directly in terms of some sort of field phi. Okay. So in pictures, you have this spherical Fermi surface, and then like this undulation, this deformed Fermi surface, you can represent as some sort of deviations from the spherical Fermi surface in terms of this field phi. Okay, and it's easy to write down a quadratic or Gaussian action for phi, which reproduces, for example, the Landau's kinetic equation given by this. Okay, here n is some sort of it's the normal to the Fermi surface. F20 is the same function, the F2, 0 p and p prime, which I showed you in the previous slide. Okay. Now, this action is manifestly non-relativistic. It's rotationally and translationally invariant. The first question that we need to answer is like, how are the broken symmetries, which are the Lorentz and the conformal symmetries, non-linearly realized in this action? And also, like, how does causality feature in this story? Okay. Okay. So first, I'll present how we impose symmetry constraints on this action. So the observables that we are looking at are, sorry, yes. Yeah. So the higher order terms will be suppressed in 1 over kf. It's an expansion about the Fermi momenta.
I see. And this F kernel has to be non-local, or can we not have the derivative suppression for that?
There are like generalized Landau parameters also which involve derivatives on F.
Okay.
I'm looking at the least irrelevant term. So this is marginal here. But there are irrelevant corrections also. If I have time, I can show the nonlinear action that has all of it.
Okay.
Yeah.
Thank you.
Sorry.
What's non-relativistic about this? Is this? I mean, does this have? It does not have Galilean invariance. Right?
Sorry.
Galilean invariance is not here, right?
No. It is the most general action that you can write down without any with just rotational and translational symmetry.
So you don't have boosts in this yet.
No, not yet.
Okay.
So right in the next slide there will be boosts.
No, I'm saying if you are saying that something is not non-relativistic, usually you would also have Galilean boosts in the game.
You can also have no Galilean boosts.
That's Aristotelian. Yeah. Okay. Fine.
Yeah.
So you just want translation and
yes.
Okay.
Yes.
Thanks.
In the spirit of effective field theory, I just exactly. Yeah.
Sorry. So since this permiliquid theory you got from a CFT with some chemical potential, can you see some imprint of conformal symmetry? Like if you place in a background curved spacetime, then wild symmetry will also possibly constrain this some way of this thing.
Yeah.
Right? So do you see some feature and you are not using those constraints?
Yeah. I don't know how to couple it to a background metric. We can come back to that later. I'll tell you like what we have done and like what can more be done. Like okay. Okay. So So let me first impose Lorentz invariance. So the observables which we want to look at are correlation functions of conserved operators, because these are the sort of operators you can precisely match in the IR and the UV. So there are two conserved operators. One is the charge density because it has U1 symmetry, and then we also have the momentum current because it has translation symmetry. Okay. So the quantity first that we want to look at is the retarded Green's function of the momentum current in this static limit, where I take omega going to 0 and then q going to 0. Okay. We now compute it in two ways. One is the Gaussian, one is we turn on sources, background sources in our Gaussian action, and then we compute this correlator, and it takes this value. The other thing that one can do is, since we have a we are considering a relativistic UV completion, okay, we can now consider word identities of our relativistic theory given by these, okay, and then like compute the correlation functions using these ward identities and take a low energy limit. And this can be done, and it fixes the momentum susceptibility to be of this. So since these two should be equal, because it's these are essentially the same subjects, same objects, we recovered this bound on the first Landau parameter. Okay, so the by first Landau parameter, I mean the following: that this was an this f2, 0 was a function of like these angles between 2 points on the Fermi surface. You can actually decompose it in harmonics like this. Okay, so Lorentz constraint just fixes one out of these entire tower of Wilson coefficients. Okay. Okay. So now coming to scale invariance, what we can do is like we want to look at the this following correlator, which is the retarded Green's function of charge densities. And similar to the previous case, we turn on sources in the linearized action. We can compute this susceptibility, charge susceptibility. And now, because we are in a scale invariant theory, where we can scale in this following manner, I keep Z to be some sort of dynamical exponent, but usually it's Z is equal to 1 or 2, 1 for conformal symmetry and 2 for this Schrodinger-like symmetries. Okay, so using the fact that mu is the only dimensionful scale in the problem, you can actually completely fix this charge susceptibility in a CFT. And that leads to this following constraint on the 0th Landau parameter, like this. Okay, so that is essentially like that's how this gives you the spirit of how we fix like the Landau, how symmetry can constrain the Landau parameters. Okay, now to answer Arjun's question, you can also impose Galilean symmetries in a similar manner, and you recover the usual constraint on like Fermi liquids in terms of effective mass and stuff. I impose these relativistic ward identities.
So, I mean, a priori, what do I do? I mean, do I impose this? Do I impose a non-relativistic symmetry? What do I want to do?
So, for Galilean, you mean?
No, I mean, is that up to me?
Yeah.
What I want to impose on, but, okay. But if I want to impose non-relativistic stuff,
right?
Then notions of unitarity, causality, etc., like was being asked earlier, it's not clear, right?
Yeah. So here we demand that the UV theory is Lorentz invariant,
and it flows to a non-relativistic.
Right. Theory. It's like the symmetry is nonlinearly realized in the IR. So this is how the symmetry is nonlinearly realized in the IR.
And your flow will break the symmetry somehow.
Yeah. Yeah.
Okay.
The flow breaks because you are considering finite density states. Finite density states typically break Lorentz invariance and conformal invariance.
Okay.
If you, for example, want to impose Galilean invariance, instead of these kind of ward identities, what you would use is like the momentum current is related to charge current through mass.
Okay.
That sort of a thing, like, yeah.
Yeah, okay, thanks.
Yeah. No. Yeah. So
so I'm just wondering where does the factor in the second line come from?
Yeah. So this you can actually fix from a different correlator, which is the susceptibility of J with T0I, the moment, Ji with momentum current, okay? So you can compute it again in this relativistic setting. It gives something proportional to rho, and then from the EFT, you can do it, and then you see that rho, 1-point function of rho gets completely fixed.
Okay, okay.
Yeah.
Yeah, because this chi pi pi is typically, it's the thermodynamic coefficient, right, at the end of the day.
Yeah.
So, okay. And you're saying that you are also going to determine that
Yeah.
by using some other relation.
Yeah.
Okay.
So if one way to argue this as well is that, like, you know, there is this thing in Fermi liquids, it's called the Luttinger's theorem, which tells you of that the 1-point function of rho is like essentially the volume enclosed by the Fermi surface. So you can also convince yourself that for Fermi liquids, this is the right quantity. Yeah. Okay. So so now moving to causality constraints. So causality implies that for local operators, we have for a space-like separation, they must commute. Okay. So yeah. Yeah. So well, so one of the ways you can think about this is that, okay, so there is another way of imposing this kind of symmetry properties, which is directly using operator identities. For example, like for Lorentz invariance, you use that you have a conserved stress tensor, as well as the stress tensor must be symmetric in its two components. Okay. Now, if you have, like, you know, one can show that, like, if you have a conserved stress tensor, it's symmetric in two components, as well as the trace of it is 0. That's a necessary and sufficient condition for full conformal invariance. And one finds that this pedestrian way of imposing this conformal invariance is the same. You don't get any.
Okay.
Yeah. Okay. So we have, so the causality constraint is this. And now, the way one leverages this is to look at the Fourier transform of the retarded Green's function, which has support only in the future light cone. Okay. So now, when you do Fourier transform of this, let's consider like imaginary frequencies and imaginary momenta. What turns out is that, like, if this Fourier transform has to exist, it implies that this retarded Green's function as a function of imaginary omega and imaginary momenta must be analytic in this forward light cone. Okay. So in the summary of all of this is that someone hands you a momentum space Green's function, all the non-analyticities that you have in your momentum space Green's function must obey this kind of a relation. Okay. Okay. So the non-analyticities that you get in the charge density retarded Green's function, for example, can be directly obtained by solving the Landau kinetic equation. Okay. The poles of yeah. And there are usually two kinds of non-analyticities. The first one is called the particle hole continuum. So these physically can be thought of as like very small excitations of particle hole pairs about the Fermi surface. And in the Green's function, if you compute it, it appears as some sort of a branch cut in the Green's function. It's somewhat like, you know, this kind of two particle continuum that you see in scattering amplitudes. And then there are other pole-like singularities which are basically like some sort of collective excitations of the Fermi surface. They are known as zero sound, shear sound, and I'm showing you just two of them because for simplicity, I have taken this following condition where all the higher Landau parameters from 2 onwards has been set to 0. Okay. Now, demanding this constraint that the non-analyticities must lie outside of this imaginary momenta light cone leads to these following conditions, okay? All of these modes are linearly dispersive, and it boils down to a very simple condition on the velocities of these dispersive modes, okay? All of these are completely fixed in terms of the F0 and F1 Landau parameters, okay? Once you plot this, this is the exclusion region that you get. Let me explain this. So the gray part is basically due to the fact that this VF must be less than 1, which is this particle hole continuum. Then what you get is that if you demand that the zero sound collective excitation is also subluminal, you get this region, this entire region, which is allowed by this condition. And then if you further imply that zero sound and shear sound are both causal, you have this further reduced zone, okay? And I must point out that people usually study also thermodynamic stability constraints on these Landau parameters just from the fact that the ground state is stable, and these are stronger than those stability conditions, okay? Okay, so, well, I have told you about a lot of constraints and like a lot of EFT constraints, so now it's time to test it. So we do two tests. One is some sort of a perturbative test of Lorentz constraint using this kind of a 4 Fermi interaction. And we find what we do is again compute the relevant EFT observable, which is the charge-charge correlation function, and one can extract the Landau parameters from it, corrections to Fermi momenta from it, and we find that the Lorentz constraints are satisfied. Then we do a non-perturbative check, which is basically one has to find a conformal field theory which enters Fermi liquid phase at low low energies. And one such example is these kind of matter-Chern-Simons theories. These are fermions which are charged under fundamental representation of SUN with coupled to a gauge field. Chern-Simons gauge field. These theories can be solved to all orders in the finite 2 coupling, kappa over n. And luckily for us, these authors had already worked out the Landau parameters for these theories, and we find that they actually satisfy our constraints as well. Okay.
So can I ask a question?
Yeah.
So with the first example, you consider there is a psi-bar-psi whole square interaction. So how should I think of it as CFT? Do I really?
No, this is not a CFT. This is
not the bounds you derived are for CFT in a chemical
correct.
potential.
So I am here checking just the Lorentz constraint.
Okay.
So this is just the constraint involving 1 plus F1 equals this. Okay. That's the thing. Here, for example, I can do the full thing because this is a CFT. And this is the structure that I get. Like in this exclusion region, this is the place occupied by Chern-Simons matter theory. Okay, yeah. Okay, so summary is the following. I want to study the phase space of CFTs at finite chemical potential. What we have done so far is constraints on just 2 Landau parameters from symmetry and causality. And we also have constraints on the nonlinear EFT, which are like higher order. Because this is an effective field theory, there are other irrelevant couplings, and you also can constrain them. So some future directions. So one of the not so satisfying things about our construction is that we start with a non-relativistic theory and then kind of impose Lorentz invariance on it. Probably there is a more elegant way of doing it where you have manifest Lorentz invariance and which also allows you to couple to background metric as well. Okay, we have not been able to figure that out so far. I predominantly worked in 2+1D Fermi liquids. If you go to 3+1D, a natural question is what is the imprint of the relativistic spin in this system, right? In 2+1D, one can argue that well, one of the, I mean, it's basically some spinless fermions that you recover in the IR. So, so that's one important question, and both of these are kind of tied to like actually describing high density QCD in some sense, okay? Or describing interior of neutron stars for some, for instance. And of course, like, you know, one can write down dispersion relations and like constrain FLs even further, more refined bounds on FLs, okay? This is the final slide, I promise. And so one can also ask, like, well, you asked for a, you assumed a CFT UV completion, but if this is to be of some help to condensed matter physicists, like they don't work with CFTs per se, they work with lattice models. So one can ask, like, whether there are these notions of causality. Here, Lorentz invariance is explicitly broken, so you don't expect any sort of usual notions of causality to appear, but it turns out that there is still some notion of causality, which is imposed by how fast operators can spread in this kind of lattice systems. And based on similar ideas, one can also impose bounds on the spectral weight, that is the imaginary parts of the Green's function. And these can be used to put constraints on transports in metals and non-Fermi liquids, okay? And so, yeah, with that,
Any more questions?
Hey, thanks for the nice talk. I wanted to ask you, you constrain these Wilson coefficients F with F0, F1 by looking at first the Rho correlator, then this spin 1 correlator and so on. But if you keep going to higher spins, is that
yeah, but
give you all the Wilson coefficients?
right, but you know, like, I mean, the higher spin currents, like the correlators are not fixed by in terms of universal quantities in the low energy theory. Here it was like charge density, energy density. There is no analog of that for these higher like spin correlators. Maybe in some specific theories, like this large N Chern-Simons theory, they can be explicitly fixed. In fact, that is one thing which one can do, like that the Landau theory of like this matter Chern-Simons theories at large N perhaps can be worked out completely. But yeah, in general, no. In general, no. Yeah.
And I also wanted to ask you, so there seems to be some choices in the sense of what you start in the UV, right? So instead of a CFT, if I started off, instead of a relativistic CFT, if I started off with a non-relativistic CFT, and then did the flow, would I get something?
Yeah, you could get something. Yes, indeed.
And do you get, are there cases where you flow down to the same theories in the IR so that you would get more constraints by starting off in the UV, you know, in the IR have the same theory, but in the UV I might have different ones, and so they might give additional constraints when I...
Yeah, so the strongest constraints I think you obtain by assuming relativistic, like the more symmetry you assume in the UV, the stronger constraints you have in the IR. Okay, so for example, like, you know, what we tried, what I tried with some people was like, what if you start with lattice, for example, okay? The results, the results, like, it was not so constraining as conformal symmetry. Conformal symmetry here was enough to even constrain marginal EFT parameters, which in this H-matrix bootstrap program, you actually cannot, like, unless you do non-perturbative bootstrap or something. Okay, so yeah, like, as much symmetry as you assume in the UV, like, I mean, that will give you more constraints.
But on the same theory, couldn't you start off with something else in the UVs, which would give you maybe some other constraint?
Sure, like, yeah, that's what I said, like, that you could start off with a lattice UV completion. You'll get some constraint on the on my Gaussian action.
But you're saying it will be a subset of what you...
Yeah, or weaker constraints.
Okay.
Like, you know, yeah.
Thanks.
So, hi.
Yeah.
I'm here. To the bottom, to your left.
Okay. Hi.
If you would turn on collisions, now there'd be two frequency regimes.
Yes.
One at small frequencies and wave numbers, where you should recover hydrodynamics.
Yeah.
But if you don't impose any kind of boost symmetry,
Yeah.
so say Lorentz or Galilean, then the hydrodynamic theory you get is extremely complicated. There are many, many, many transport coefficients.
Right.
Somehow I don't see, maybe, I've not really thought about it, but at a technical level, why all hell should break loose? How are you going to recover all of that complexity just by turning on, I don't know, some collision kernel in the relaxation time approximation?
Yeah, I must admit that I've not thought about this, like that, how to, I thought about this and I don't have a good answer to it. Like, I don't know how these things will work out if you have a collision kernel, for example. Like, I'm not sure. I don't think their coadjoint orbit formalism, like, which is what, like, the full nonlinear EFT is. Yeah, I'm not sure how.
But here somehow to constrain the Landau parameters,
Yeah.
you never needed all of the formalism of the EFT that you described. You
Yes.
could have simply solved
some Gaussian,
the
yeah.
Boltzmann equation,
Yeah,
and looked at linear excitations, and
Yeah.
you would have gotten the exact same constraints
No,
by
but-
requesting that chi pi pi matches onto what you can derive from Lorentz symmetry. You didn't need the EFT of shapes.
Right. That's true. That's true. Yeah. That's true. For the Gaussian action, indeed, like, I don't have a good answer to it. Yeah. Okay. That's a good question, actually. Yeah.
Sorry, I was asking also about this non-Gaussian kind of thing, like you don't write, or let's say the 3-point functions correlator,
Yeah.
they're not going to give you any constraints?
So here, I was not planning to show this, but like I can now show this. So you can actually uplift this into a full-fledged EFT where you also have 3-point functions. There are symmetry constraints on the 3-point functions, but causality constraints, I'm not sure how the nested 3-point functions, how I don't think it has been worked out. There has been very preliminary study by Lam Hui very recently, but I'm not sure if it's anything useful. I did not immediately see, but yeah, symmetry constraints can be done, but I don't know about causality constraints.
But at the level of 3-point, at least there is one more constraint at the CFT. Those are Watt-Takase identities, right? They have to be satisfied. Like conservation is no longer true.
Yeah,
but they will also play a role, right?
Yeah, but these are again symmetry properties, not causality properties. Causality would be like some sort of like this nested commutators, analyticity properties that you derive from some nested commutator or something like that. That I'm not sure has been done. Sure, symmetry properties, yes.
Yeah. So would it be also possible to study constraints on BCS theory using this Migdal-Eliashberg approach and together with this one?
So BCS theory, I'm not really in the regime because I'm assuming that we don't have some sort of superconducting instability.
Yes, but in principle, could you do something similar? With
I think so. I think like this sort of, if you have an effective field theory, these kind of approaches are very general. Like this, especially the sort of thing which I showed regarding computation of susceptibilities. It's super general. I think it can, yeah.
And would you be able to also extend to some finite temperature and put some bound on some, say, critical?
Yeah, that's a good question. Maybe for low temperatures, maybe one can do it. Yeah, therefore, at least for the EFT that I'm looking at, it's it's actually 0 temperature. It's defined in 0 temperature. So yeah, for this EFT, I don't know, but but it should be possible. Yeah.
Okay, I have a related question because
maybe we can take questions right after. Sorry, because we are running late. Let's thank Shubham and actually all of today's speakers once again.